Okay, so good morning, everyone. Welcome to this 131st edition of the Zak World of Façades conference series. My name is Ahmed. I'm part of the organizing team here at Zak. I quickly introduce the Zak World of Façades conference series to those who have not attended it before. So we've been organizing this conference since 2012. We started this as a small networking event, and then it's grown from country to country, city to city, all across the globe. We've finished around 130 editions in 37 countries. In Australia, this is our 6th edition. We had our first edition in 2018, Sydney. 19, we had Melbourne and Brisbane. This year, earlier in February, we had Melbourne and now Sydney again. 2 editions in New Zealand also. So it's been all across the globe, the spread from New Zealand up until Canada. This is, okay, I think right. So this is our schedule for 2023. We finished almost 80% of them. Still got few events left. Yes, it's been a fabulous journey organizing these events in different parts of the world. Facades are organized and facades are designed and installed very differently in different parts of the world. It's a great challenge for us to adapt the agenda accordingly to that respective city, that respective region. Australia is also no different, very different ways of procurement here, ways of designing and engineering. So for us, it's always an exciting time to produce such events. But these events are not possible without our event partners. I'll quickly introduce them, then we'll get into the agenda. We've got 25 associate partners. I'll run through them as quickly as possible. AGC Glass. So AGC is a Japanese Belgian company. They've got a lot of products for high performance glass, for BIPV and other stuff. Beijing Tianbua Glass, WHTB Glass is the English name, value-added glass processor out of China. Cementel, a part of the CSR group, Australian, they've got fiber cement cladding. Cosentino, a Spanish company, they've got an interesting cladding material called Decton, non-combustible. CRE, Climate Ready Engineering, they are an Australian company. They have solar shading solutions for facades. CSG, China Southern Glass, another value-added glass processor out of China. DCF Facade, local Australian company, distributor of many European and international cladding products. DC Tech and Envelope, so they've got membranes, they've got rain screen systems, and a lot of other products. This is a local Australian company. Equitone, they are a European company. They've got fiber cement cladding products. Guardian Glass, one of the world leaders in coated glass product, an American manufacturer. Kingspan, Irish, they've got rain screen cladding products, insulation, and a lot of other stuff. Lysag is formerly known as Blue Scope Steel, steel cladding solutions. We've got Metz and Onyx Solar. Metz is a distributor of a lot of cladding products, GFRC, ceramic, and Onyx Solar is a Spanish company. They've got BIPV solutions. North Glass, another value-added glass processor out of China, specialty in large and curved glass, jumbo glass. They can do up to 23 meters now. They'll be talking about it later today. Obex, British manufacturer. They've got tapes, they've got membranes, they've got cement boards, a lot of other stuff. Quandat is a Vietnamese manufacturer of aluminum door, window, curtain wall fabricated products. Saint-Gobain Glass needs no introduction, one of the leading coated glass manufacturers. Serge Ferrari, French manufacturer of fabrics which are used in architectural applications, facades, roofs. Schildan Group, an American company, distributor of terracotta from Germany, very popular in the US, just launched in Australia. Siderise, British manufacturer of cavity barriers and perimeter stop fire protection. Technofrom, German manufacturer of polyamide strips and warm edge spacer bars for thermal performance. Technorail is an Indian manufacturer of modular aluminum railings. Vector Foil Tech, ETFE Solutions, German manufacturer. Vitro Architectural Glass, Mexican-American, formerly known as PPG, again, one of the leading coated glass manufacturers. And our next event, our next big one is New York City. Of course, we've got 2 events in between that. Little bit in the extended region, Ho Chi Minh City in Vietnam, end of next month. Our biggest one in the series, London, close to 1,000 delegates with a black tie dinner with the Society of Facade Engineering. And of course, we return to Australia next year. We've got a event in Brisbane in February, and then Melbourne in September. So this is what we've been doing with the conference series globally. We've been organizing them, talking about different solutions in facades. Of course, we've seen the event evolve in different ways. When we started off, for us earlier, the gold standard in curtain wall was double skin facades, and now there's talk of reduced glass, less glass is better, carbon and all that stuff. So that's the theme globally, at least in the Western countries, in Europe and America, where people are talking about opacity, people are talking about low carbon solutions, people are talking about recycled materials. We've tried to bring that in today's theme. There's a lot of talk in the initial sessions on embodied carbon, which is what is going to be derived by people, recycled glass, recycled aluminum, and a lot of other stuff. And of course, it's just not that. Glass is still not dead. There's still a lot of use of glass, and it's also evolving. So you'll see a lot of structural glass applications, the future of how glass might look from now, how we look at glass, and a lot of other stuff. So we've got a packed agenda. So it's just not about design, it's about materials. And of course, you've got your FP 1.4 code, you've got the RAB, DBP acts also being discussed. So we've got a nice mixture today. I hope you will understand, you will enjoy today's event. Those who have the red color delegate badge, you will have a USB stick on your lanyard. The USB stick has the brochures of all our 25 participating partners. So we are not giving the delegate kit anymore. So the USB has the soft copy of all the brochures. You can access them. We've also recorded today's event. So a week from now, you'll get a YouTube link, which will have all the presentations which we have been given permission to share with you. You can access that in case you miss anything throughout the day. Right at the end of the day, we've got a 1-hour networking cocktail session, which will be held in the exhibit area. So I think I'll take leave now. I'd like to introduce our two event hosts for today. They're filling in big shoes. We had Mr. John Perry hosting this event last time around. We thought we'll do something different this time around. We have Claire Wu and Natalia Flaibam from BG and Façades, a dual hosts for the day. They've promised to keep it humorous and interesting for all of us. So they'll be taking you through until the end of the day. So that's it from me. Thank you.
Thanks, Ahmed. Thank you. Good morning, everyone. I'm Natalia, and it's my absolute pleasure to be here today presenting, co-hosting this event with my good friend and work wife, Claire.
Oh, thanks, Natalia. Oliver, we do real work as well, just saying. We don't just talk about random things at work. Thank you, everyone, for being here today. I'd first like to acknowledge the traditional custodians of the land here, the Gadigal people of the Eora Nation. We acknowledge their long relationship with the lands and the waters and pay our respects to the elders past, present, and future. I'd like to call Mal, the building manager, if he's in the room. He wanted to give a safety briefing of the fire escape, but I think he's not in the room. So I believe it is through the doors at the back and the side.
The green sign.
Maybe he will join us a bit later.
Well, if he's trying to grab him, just a few announcements. Please make sure your phones are on vibrate or silent mode, please. And during the presentations, there'll be no time for questions, but you're more than welcome to ask the speakers during the break. And last one, very exciting one. If you'd like to win 2 Australian Football League tickets and an AFL ball, please make sure you visit OBEC's booth over there during the breaks. There will be a draw at the end of the day. Yeah. It's more here? Okay.
Okay. Let's just wait a couple of minutes until we get the safety briefing from Mal. So we're going to have to ad hoc this. We didn't plan for this. Anyway.
There are no more cards.
I'm Claire. I've been with BG&E for 3 years now, and I've studied civil engineering with architecture, and I love how Façades kind of melds the two together. So I think I'm really lucky that I found Façades right outside of university. and it's something that I've really enjoyed.
Yeah, same for me. I come from Brazil, where we don't have disciplines like here in Australia and the rest of the world. Okay, cutting short. Perfect. Great. So let's kick off the day with our first speaker. I would like to welcome to the stage Simon Barnes from Arup, who will be presenting decarbonization of the building envelope. Simon.
Hopefully the feedback will stop in a second. So thank you both very much, and thanks to the conference. It's a real pleasure to be here today in Sydney. Been looking forward to the presentation for a while. I'll get started. First of all, acknowledgement of country, which is obviously extremely important. We acknowledge the traditional owners across all lands, waters and skies our firm may reach. We acknowledge their wisdom, resilience and rich cultural heritage. We pay our respects to the elders past, present, and to all Aboriginal and Torres Strait Islander people. We recognise the ongoing journey of healing and reconciliation, and we commit to walking alongside First Nations peoples to acknowledge their teachings and foster a future of unity and respect, which, look, I think it's probably quite relevant to the topic of today, which is broadly about sustainability. But first, I'll just introduce myself. Let's see if I can I can walk. This is good. I'm not tied to the thing. Great. So I'm from Arup. I lead Arup's Façade team in the region. Most of you will know Arup. Arup's been around for a long time, 77 years. I think it was first established in the UK in 1946 and has been present in Sydney for the last 60 years. So it's almost as Australian as it is British, which is a bit like myself. And today we're going to maybe travel a little bit around this map of the globe to discuss the subject of decarbonisation, but also the subject of what we mean by the building envelope and what is what I'd like to look at this subject through, which is the subject of curtain wall. We're also, are we going to travel in time a little bit? I've been at Arup for quite a long time. This is when I started. I think it's 27 years ago. It doesn't feel like 27 years, but it is quite a long time ago, 27 years. And what's interesting about that time period is it's also the amount of time between now and 2050. And why is 2050 important? Well, it's because of the subject I'm going to be talking about. So we're talking about decarbonisation in the building envelope. First thing I want to talk about is why is decarbonisation important now and wasn't important maybe 27 years ago or whatever. I'm going to be talking about what is embodied carbon, because I think there may be a bit of confusion about what embodied carbon is. There certainly was in my head when I first started thinking about this subject, so I think it's important to cover. And then more broadly, the building envelope. The building envelope obviously can mean an awful lot of things. For me, it's really about curtain wall, which obviously has lots of aluminium in it, and it's been around for a very, very long time, proven itself to be a very flexible system. And then I'm going to talk about a case study. And the reason I'm talking about this particular case study is partly to do with the year of its construction. It was completed in 1998, and it's one of the very first projects I had a slight involvement with when I started at Arup all those years ago. And I'm going to be talking about it in the context of embodied carbon, which is upfront, operational, and end of life. And if we get time at the end, I'll maybe have a summary, but let's see how we go. So, first of all, climate change, decarbonisation. Why do we have decarbonisation? If I can just quote very briefly from the 8,000-page sixth assessment report by the IPCC, it says something very, very clear, which is that the world must rapidly shift away from burning fossil fuels, which is the number one cause of the climate crisis. Now, these are all headlines just from last week in the paper. So we had the world environment reaching its environmental limits, which is a very broad subject, but includes climate change. We have the tragic events in Libya, of course. We had heat waves in America, and we have loss of the sea ice in Antarctica. So obviously things are happening. And it's an extremely important issue to address. But what are governments doing about that? What are our governments doing about it? Well, what our government is doing about it, along with many others, is setting zero carbon targets. zero carbon targets are happening relatively soon. They're happening in 2050 in different countries around the world. And Australia has declared a zero carbon target in 2050. Why is that so important to us? Well, it took me a while to figure out this graph when I first saw it, but it's not that complicated. What we do is we design buildings, they get constructed, and then they're in operation for a really long time, preferably more than the sort of 27 odd years between now and 2050. And we're looking to hit a 50% reduction in 2030 or thereabouts. Therefore, clearly buildings that we design now are going to be operating in a net zero environment very soon. So it's an important issue for us all to address. So what is embodied carbon? Embodied carbon has three principal stages. I'm not going to step through every single one, or we'll be here all day. But essentially we have the embodied carbon, which is up front. That is from the extraction of material right the way through to construction. Then we have what we call in use, which includes the operational carbon, but it also includes maintenance, repair, replacement, refurbishment, which actually makes it a much broader issue than just energy efficiency, which is of course really important, but it's not the only thing driving it. And then of course we have end of life. So embodied carbon, it's more than just the upfront bit, although the upfront bit is obviously very important. What's the building's impact on all this? You've probably seen these numbers or very similar numbers previously. 39% of global energy-related carbon emissions are from buildings. Now, if I can remember what was on the last slide, there was hundreds of billions of tons of CO2 as the current levels of global carbon emissions. So if we're talking about 39%, we're talking about quite a few hundreds of billions of tons of carbon emissions. It's an awful lot. So obviously, as an industry, we need to address this issue. And then breaking that down, sort of 28% from operational and 11% from the materials involved in the construction of the buildings. That data is obviously, to some extent, historic, and therefore that operational emissions component is based on energy grids which may have had a higher carbon content than in the future. So what's the carbon breakdown? What's included in the building, and does the facade contribute that much? Well, it's an interesting question because it's highly variable, and this would be a really major component for a facade. In reality, I suspect the proportion in a typical building is somewhere between 11% and 19%. It depends upon a whole load of different factors. It depends on the design of the facade. So, we were talking earlier about, recycled material, sources of material, energy efficiency, and so on. And then we were talking about design. Well, of course, they are one and the same thing. We cannot think about these issues without thinking about design. And the proportion of the upfront carbon in a building within the facade is a highly variable thing. So if, for example, the facade has lots of external aluminium and several layers of glass, and the building has a form factor which creates lots of external envelope to a very limited amount of internal area, that proportion is going to be much bigger. So we can make that proportion smaller simply by changing the shape of the building, but obviously that's not going to be necessarily enough. So what do we mean by the building envelope? And I sort of touched on this a little bit earlier. Clearly, the building envelope can be lots and lots of different things. It could be CLT, it could be a steel stick system, it could be a unitized curtain wall, it could be masonry, it could be all sorts of stuff. And of course, each of those different things has significantly different consequences in terms of upfront carbon, but also operational carbon, end of life, et cetera, et cetera. So it's a huge, very broad subject. And to be able to talk about it in the space of roughly half an hour, hopefully within half an hour, I think we need to try and contain that to one particular type. And so what I'm going to talk about is mostly unitized curtain wall. And I thought to sort of guide me to that, I'd take a look back at some of the projects that I've worked on over the years and take a quick kind of straw poll of what they are. So this one, unitised curtain wall, unitised curtain wall, unitised curtain wall, same. This is a window wall with a stick system with some terracotta baguettes in front. This was a major glass replacement project. This is my first project in London, a bit of stone cladding, bit of big sliding Schuko windows, 2-edge supported glass, not curtain wall. Another curtain wall in the middle, another curtain wall at the end, glass screens, more curtain wall, another double skin facade there on the end, and so on and so forth. So basically the vast majority of projects, I think, as a discipline that we work on, tend to be prefabricated, unitised curtain wall, and therefore it seems like a fairly relevant lens through which to look at this particular issue. So, unitised curtain wall, here it is. Again, we talked about facade being a different, potentially different magnitude component of the overall upfront carbon in a building project based on its design and its materiality. And of course, curtain wall, as we saw from those photographs, can be quite variable. You know, designs of curtain wall can be quite different. And that's one of the reasons why it's so successful, is that it is so adaptable. In this particular case, a curtain wall with that much aluminium in it would have to have fairly hefty external aluminium sunshades to get to that level. It's more typical for a unitised curtain wall to have, say, between 50 and 60% of aluminium. And the glass component, of course, would vary quite significantly depending on how many layers of glass we have in the unitised curtain wall. And then there are many other factors which would cause some variability there, which I'll come to talk to in just a moment. So one of the major aspects of curtain wall, though, and I'd like to talk a little bit about its history, is this significant component of aluminium. And is this somehow an obstacle to it being used in the future because we're so concerned about upfront carbon? And it was really just an excuse to put a picture of an aeroplane up, which I thought was pretty cool. The aluminium industry in the US is a serious topic for discussion in terms of the history of curtain wall. So before the end of the 19th century, so we're going to go way back now, way before I even started working in this industry, the process of smelting aluminium was invented, but before that, aluminium was more expensive than gold, so there was no chance of it ever being used as a construction material or indeed for making anything much bigger than a piece of jewelry. After that invention, which was created by one of the founders of the American Aluminium Company, which is Alcoa, there was a rapid rise in its use because it's an amazing material. It's lightweight, it can be formed into complex shapes, it's very stiff, it's fantastic. And so in the emerging aviation industry, which emerged at the beginning of the 20th century, Alcoa actually made the engine block for the Wright brothers' first aircraft. It was cast aluminium. And by the Second World War, the US was chucking out, I think, 11 aircraft, was it an hour? Something like that. So 100,000 aircraft a year at its peak during the Second World War. This one's made, the reason I put this one up is because its airframe is entirely aluminium. After that, aluminium needed a market. You don't make 100,000 airplanes a year and then all of a sudden revert to making the same number of commercial aircraft. So the building industry in the US became a potential source for this amazing capacity to produce aluminium. Now, one of the reasons the US was able to produce aluminium in such quantity was because it had access to super cheap energy. So an abundance of energy and an abundance of material. And this building is possibly the first, one of the first, applications of aluminium frame construction in a building. It's the Equitable Life building in Portland, Oregon, and it was designed by Pietro Belluschi, whose practice was eventually acquired by SOM, I believe, not long after this building was constructed. This building actually had double glazed units in it, which is incredible. So 1948, aluminium frames, double glazed units, amazing. But then it went even further. 4 years later, probably the most sort of archetypical curtain wall building, and the one that really set it going, is this building, which is, of course, Lever House in New York City. This set the tone for the all-glass building, and it established unitized curtain wall as the delivery mechanism for the all-glass building. And really, since this building was constructed, the way in which we construct high-rise, large-scale commercial buildings has not changed that much. It's changed a little bit. Obviously, curtain walls evolved quite a bit since then. These were very simple frames. There was actually quite a lot of steel in these frames to make them strong enough. It was single glazed. There were some serious problems with this building over its sort of 50-year life, and it has been extensively refurbished relatively recently, or at least the beginning of the 21st century. So curtain walls evolved. It's evolved to include pressure equalization, thermal breaks. We structurally bond double glazed units to it. We integrate sunshades. Sometimes we integrate additional layers. And this is all in the interests of improving its energy efficiency and its performance. And we've all been involved in this over many, many decades, these gradual improvements. And they have been done in order to address energy efficiency regulations and comfort in buildings. So let's have a look at an example. And let's have a look at that example that we were talking about earlier, which is 1 Triton Square, which is a curtain wall building. And how did it address those 3 phases of the embodied carbon assessment? So here's the building. Triton Square, a classic 1990s office building. Actually, it's quite an unusual office building in many ways, in that it was purpose designed for the banking sector at the time in the late 90s, which was it was built to house trading floors. Now, trading floors were heavily reliant on technology, and technology was probably the thing that was changing the fastest in the 1990s as mobile phone technology and the internet emerged. And therefore, the market for this type of building evaporated relatively quickly. Purpose-built building for something that was in a very rapid state of change. What was the design? Okay, so I'll try and run through this as quickly as I can. It was a very big floor plate, 75 by 75 meters. It had corner cores, it had a huge atrium in the center, and it had a double skin facade on all 4 sides of the building. And it was one of the biggest atria in office buildings anywhere in London at the time. What were the key interventions? Key intervention to make the building more marketable and occupiable for the client was to increase its floor area. So part of the atrium was filled in. The corner cores were retained and extended upwards, and 3 additional floors were added to the top. And part of that process involved bits of facade being moved up the building. There was some new facade, and an awful lot of facade was retained. And that's why I guess I'm so interested in this project. But also I'm interested in this project for the balance between upfront carbon and operational carbon, which is a really interesting topic for discussion. So let's have a look at phase A, upfront carbon for the building. So the original facade I mentioned just a moment ago, it's a double skin, wide cavity. It had unitized curtain wall panels supported off steel strongbacks. Steel strongbacks were attached to the floor slabs, had integrated steel brackets, and these funny looking external ducts which were insulated, all part of that design. And then spanning between the strongbacks, there was a vision panel. That was a double glazed unit. And there was a blind in the cavity, the classic externally ventilated double skin facade, very popular at that time, extremely high performance. In fact, much higher performance than was required at the time just to comply with regulations, and that's an important factor. Then the cores, the main other component of the external facade, the cores were stone-clad, French limestone on precast concrete. So what do they look like in terms of upfront carbon? So before we do that, just having a look at the carbon intensity of those different materials. Now, this is based on UK data, and One thing about carbon intensity data that we need to remember is that it's a constantly moving feast. It depends very much on procurement. It depends very much on what's happening in the energy grid. So it depends on where we get materials from. So these things would have been averages for the UK. As you can see, the carbon intensity of aluminium is off the charts compared to the other materials. Now, that's not the same as its contribution to a facade panel per square metre. And quite clearly, there are a lot of different kilograms of glass and aluminium and stone and concrete as we build up a facade system. It's not the same as the carbon intensity, but that's just to represent the intensity of the materials. And of course, the double skin sits across here. Aluminium, steel, glass, lots of those things. And the solid component, albeit it's very much heavier, has got a much lower carbon intensity. Now, don't look at all these things, okay? I promise there's only one more graph after this. So, just look where the red arrows are. So this one here, that's our double skin facade. That's its upfront carbon at that time. And it's important to say it's at that time because that's based on the carbon intensity of the procured aluminium for that particular project at that particular time. And I'll come on to talk about that in just a second. But what you can see very clearly is that the double skin curtain wall is roughly 3 times, if not more than 3 times, the intensity of the opaque wall. So if we looked at that project through this lens of what's the upfront carbon for this project, we would see that the high-performance facade part is fairly carbon intensive, fairly obviously, but the solid wall part is correspondingly not particularly intensive. And the balance between those two materials was something like 60-40, somewhere between 60-40 and 70-30. But also the form factor for the building, because it had so much internal area, the facade's contribution to the overall embodied carbon was relatively small. Actually, I'll just quickly go back, can't resist. These things in here are all different types of curtain wall with different add-ons and degrees of opacity and materials for the spandrels. So this is all work that Arup has done based on UK databases, but we're also doing it for Australian databases as well. And as I said earlier, it's a constantly changing picture. So procurement, the importance of procurement. Procurement in 1998 versus 2023 versus 2030 versus later on, it's going to offer us lots and lots of different opportunities. So this diagram here, which is from Mccleery, I won't talk a lot about that. I know there are others talking about that today, but just very quickly, this represents different carbon intensities. So back to that first graph I was talking about, which is per kilogram of material, how many kilograms of CO2. You can see there are dramatic differences, and these dramatic differences are happening in relation to the decarbonisation of our industry and our supply chains, and that's really, really important to consider. Also, local suppliers, Caprol, have introduced low-carbon products, low-cal, 8 or 4 kilos per kilogram. That is dramatically less than, let's say, a Chinese average, an Australian average, global average. These are all heading down, and they're all heading down at different rates. So how did we do for upfront carbon for this project? Well, one thing I'd like to talk about, which I haven't much so far, but structural efficiency. Structural efficiency is something that we've been doing forever because nobody likes to throw aluminium and material at a project for no reason. Aluminium is fantastic for that because we can tailor the profile to exactly suit our structural requirements. We can be very, very precise with it. But if we think of structural efficiency as also an architectural design driver, it might dictate how widely spaced we place mullions, it might dictate how high above the floor slab we place a stack joint, and in doing so we can reduce the amount of material we use. That wasn't really a consideration for Triton Square, but what you can see is the window component, which obviously spanned considerably less than a typical mullion, had much lighter frames. So in some ways it was already happening, but not really as a major driver. Multiple layers, well, again, if we're thinking about upfront carbon and we're thinking about trying to reduce that, multiple layers in and of themselves are not a brilliant idea. irrespective of where we get our materials. Multiplying up the amount of material isn't necessarily a fantastic idea when we think about that just through the lens of upfront carbon. And then we talked about material selections, so we talked about stone and we talked about glass. So phase B, operational. And the important thing about this is it's not just the operational use, it's also maintenance, repair, replacement. And that speaks to good material selection, long-term durability, and things that we don't normally consider in terms of reducing carbon footprint. So the classic dilemma is reduced operational carbon driving us towards more material, potentially, and reduced embodied carbon driving us in the opposite direction, driving us back to leave a house, you know. So what was Triton Square? Triton Square was this one. It was a double glazed unit, and it wasn't a laminated out of paint, it was monolithic. So its intensity, its embodied carbon per square meter would have been up close to this level, which when compared to a double glazed unit is quite a lot more. So what does that look like? The obvious question, the big question is, what does the payback look like? Well, I don't have data for Triton Square, but we have done some research into this for just looking at a double glazed unit versus a triple glazed unit. And that's what this graph is, and it's the last graph, I promise. So this represents the additional carbon that comes from the extra layer of glass in a triple glazed unit in a notional building. So that's all this extra carbon. These lines represent different scenarios, i.e. a mechanically ventilated building that's heated with gas, a mechanically ventilated building that's heated with electricity, a naturally ventilated building that's heated with electricity, and it's in two different locations, and in this case it's London and Glasgow. What's fairly obvious from this is carbon-intense energy sources give us really rapid payback. Of course they do. If a building's heated with gas, then obviously we're going to pay back this carbon real quick. But the reality is that our grids are decarbonising and most of our buildings are moving towards all electric, and therefore the repay time for that extra layer of glass is getting longer and longer and longer. And it's kicking out, in some cases, to over 30 years, which is really significant. Now, that's not to say that we shouldn't design energy-efficient buildings. Of course we should, because there are other reasons for designing energy-efficient buildings. For example, we don't want to put extra mechanical services into our buildings that we don't need to. They take up space, it would be better not to have them. And of course, there's the whole question of buildings that are comfortable versus buildings that are uncomfortable and difficult to maintain at comfort conditions. Now, if we looked at Triton with this graph, we would have a much more carbon-intensive grid because we were building in 1996. And this point would be way up here because this only represents one extra piece of glass. But within the 20-year life of the original life of that building, that would have been repaid, let's say. Okay, so durability. This is a Rover P4, and it's got coated metal on the outside, and it's been poorly maintained, I would say. It's not my car. I would have looked after it much better than this. So the coatings have degraded, they've come away, there's corrosion happening to the metal. Now, why am I pointing to a picture of a car in relation to Triton Square? Well, I suppose the thing about Triton Square is because it had a double skin, the inner skin was very well protected from the environment, and therefore its operation, its maintenance, and its durability was potentially a lot better than it would have been if it had been left exposed. And I am running out of time. So when we look at that, three key things really to think about in terms of those phase B emissions. So performance, obviously, endurance. So endurance, what I mean by that is selecting the right materials, selecting durable materials, and thinking ahead. What do I mean by thinking ahead? What I mean by thinking ahead is thinking about how we maintain things, how potentially we replace things. And of course, we do think about that in our designs, but do we think about it enough? Maybe we should think about it a little bit more in terms of looking at things through a low carbon lens. And then finally, not too many slides to go, and I know I'm going to go over a tiny bit. The last phase, end of life. So let's look at the project very broadly. What was retained and what was refurbished. So there was a huge amount of material retained. And obviously, a lot of that was primary structure. That's the grey-brown stuff. The blue stuff is the new structure. So this project did fantastically well because it had retained an awful lot of structure, but it also retained an awful lot of facade. Now, this is a picture of a kit home from the US in the 1940s. And I put it up because it illustrates just how many components go into making a very simple building. The buildings we are involved in tend to be a bit more complex than this. Now, if we were to take a mindset of disassembly to our buildings and think about end of life and how we refurbish and look after the facade components in our buildings, we might take a different approach to the design. Now, disassembly in the case of Triton Square was made much more possible for a number of reasons. One is the original architects, Arab Associates, were involved in the refurb, so there was a huge amount of documentation and history of the components freely available. And also the facade contractor who was originally involved in the refurb as well. So all of the construction information, all of the technical information was available, which meant that components could be confidently disassembled and reused because their properties were well understood. So what do we actually do? The double skin facade, very briefly in cross-section, was removed. So the outer panel, the unitized curtain wall, was taken off the steel brackets. The original idea was to take it back to the Netherlands, to Schelderbouw's factory, and refurbish, inspect, clean, potentially renew gaskets, etc., and then bring it back to the UK. In actual fact, this was done on a site 20, 30 miles from the construction site, which was in central London. It didn't have to go back to the original factory because there was very little done to those external unitized curtain wall panels because they weren't forming the full building envelope. They were dry glazed, they were single glazed, and they were easy to unbolt and take off. So most of them were simply inspected and cleaned. Then, just coming back to this cross-section, sorry I don't have a better or less blurry diagram. The strongbacks were retained. So as I mentioned earlier, this idea of protection and looking after the coatings of the mild steel, the galvanized steel brackets, were, I'll finish in just a sec, sorry, were well protected by the outer skin, and therefore they were inspected, cleaned, and retained. These elements, which is the vision glass, there was an attempt made to reuse the frames there. The double glazed units were reaching the end of their lives, and the gaskets had deteriorated in those windows, and therefore the air tightness for the building wasn't quite as good as it needed to be. Unfortunately, because they were structurally bonded to the frames, that was completely uneconomic. The amount of time it took to deglaze them was extreme. So just thinking about headlines from that phase C in that project, we have obviously proven that curtain wall can be detached and reused, which is fairly obvious, but it's very rarely done in my experience. I haven't seen it done in very many projects. Exceeding minimum performance targets actually assisted in that strategy of reuse because it made it very straightforward to reuse the panels and to comply with present standards. So that was an important factor. Structurally bonded systems are labor intensive to deglaze and therefore largely uneconomic. So structural sealant acts as a bit of a brake on reuse. Really good data of the existing materials was very, very helpful, and refurbishment makes the most sense when undertaken close to the site. And finally, just some vital statistics about the project. It won the SFE Project of the Year for Sustainability last year, and I mean, yeah, very interesting project. And I've run out of time, so thank you, everybody, and enjoy the rest of the conference.
Just before I call out our next speaker, just circle back to the emergency exits. So please notice we have 2 emergency exits, one right behind you and another one to my left. If the fire alarm rings, we're gonna hear first a beep beep, and there's nothing to do except to prepare to evacuate. And the second one would be a boop boop, and they're going to say evacuation. And then very calmly, we would go through the doors to the outside, where they're going to guide us to the meeting point that is on the corner of Kessler Street and Liverpool Street. That's it. Now, next, we have Jeff Morgan from Hassel to talk to us about the future of aluminium low carbon.
Good morning, everyone. I also would like to start today by acknowledging the Gadigal people of the Eora Nation and pay my respects to their elders, both past and present. I'd also like to extend that respect to any Aboriginal or Torres Strait Islander peoples here today. So yes, I'm Jeff Morgan. I'm a principal in architecture at Hassel in our Sydney studio, and I'm also the chair of Mccleery's Aluminium Working Group, which is really the focus of my presentation today, and thank you for Simon for giving us a bit of a plug. I'm going to dive really into aluminium specifically and only, and talk about it in the Australian context. So my journey in aluminium started just over 14 years ago. I was working with Foster and Partners on Masdar, sustainable visionary master plan city for 40,000 people in Abu Dhabi. And there were many interesting things that came out of Masdar. And I know that many may kind of look at it now and go, it was a bit of a project doomed from the start. But having been on the ground for 3 years and kind of really seeing this kind of amount of change that was brought about, and really physically feeling the tangible difference in the built environment was really rewarding. The other thing that really stuck with me was the fact that the project became the first in the world to use fully recycled aluminium for its structural facade solutions. Prior to this, recycled aluminium had really only ever been used in sheet or panel cladding. And so how did this happen? As a large owner and developer, Masdar used its own ambition and influence to attract like-minded companies to push their own bounds. And in this instance, Alcan, now owned by Rio Tinto, teamed up with a small remelt partner in Belgium called Emax to develop the particular strength alloy required for the extrusions. So that was just roughly around 14 years ago. And recently in my work with Stockland on 110 Walker Street, I found myself asking engineers and contractors around the industry about the possibility of using recycled or low-embodied carbon aluminium in the facades. And really, much to my surprise, I received a lot of very confused looks. So something that I thought would have advanced quite substantially in that time apparently had not. Oops. So working with actually Simon's team at Arab, Façade and ESD teams, we estimated the potential embodied carbon savings if we were to use the same billet that we used at Masdar. So this particular product, at the time around 3 years ago, was one of the lowest embodied carbon products available on the market, sitting at around 1 kilogram of carbon dioxide per kilogram of aluminium. So when we compare that to a likely billet intensity out of Asia, there was really a substantial difference. And that was quite an eye-opener for me, but also for the client, and ultimately led me to Mccleery. So Mccleery was founded in April of 2021 to accelerate the decarbonization of the built environment. Mccleery is really all about collaboration, and collaboration across the entirety of the supply chains to find solutions quickly. We currently have over 120 members and counting. And understanding the challenges and opportunities for a low-carbon aluminium future in Australia is complex. Our ecosystem includes contractors, fabricators, engineers, architects, LCA consultants, miners, remelters, recyclers, researchers and financiers, and many others. And so therefore, much of our focus in the working group has been on engagement across this ecosystem, sharing our lessons and our learnings, and to help educate each other, and ultimately to send a clear and strong demand signal to the market that low embodied carbon aluminium is a must for Australia. What exactly do we mean when we say what is low carbon aluminium? Well, essentially it is aluminium that has a low embodied carbon content compared to global benchmarks. It can simply mean that it's primary or virgin aluminium produced using renewable electricity supplies like hydroelectricity, rather than fossil fuels, or it may also refer to recycled aluminium, which again can be made using either fossil fuels or renewables. So the ideal scenarios you see there on the right would be to have a fully recycled content produced using renewable electricity. Globally, Australia is a really large player in the aluminium market. As you can see, we are the world's largest producer of bauxite and second largest the largest exporter of alumina. Yet we are only the 6th largest producer of aluminium globally. And one of the well-known facts about aluminium is that it is infinitely recyclable. However, currently the linear economy really dominates the value chain here in Australia. We extract more bauxite than anyone in the world, and we export it. We produce more alumina than anyone in the world, and we export it. We do, however, import nearly as much aluminium as we produce locally. And at the end of its use, you've guessed it, we export it, approximately 95% of it back overseas. I'll touch on this a little bit more later in the presentation. So why are we talking about embodied carbon of aluminium? Simon also kind of touched on this a bit, but typically it's the 3rd largest contributor to a building's embodied carbon footprint after concrete and steel. And compared to many other primary materials used in construction, it is by far the most intensive. And why is that? I think this image probably gives it away. There are a few challenges around producing low carbon aluminium, the first being that it takes enormous amounts of energy to make it. And to give this some context, we have 4 smelters on the east coast of Australia. Those 4 smelters consume nearly 10% of the national energy capacity alone. And in Australia, unfortunately, the majority of our energy still comes from our coal-fired power stations. And yes, our grid is decarbonizing, or not in some cases, but so just how fast really remains to be seen. The other challenge really is a bit more complicated. The majority of our large-scale buildings and even many of our medium-scale projects have their facades procured from Southeast Asia or China. And over the past decades, Australia has really lost a significant portion of our manufacturing capacity and capability as a result of our current view that cost outweighs all other metrics. And finally, the last challenge is really ourselves as a development and construction industry. Advances and opportunities in concrete and steel are much more broadly known, but the conversation in aluminium, like we're having today, is really just the beginning, and I think we've got some ways to catch up. But I'm pleased to say that there has been quite considerable and noticeable increase in awareness and media coverage over the past year, from federal and state ministers visiting key smelting plants signaling the importance and policy shifts on climate change, to research initiatives on circular aluminium from leading circular economy consultants and our own working group members, Corio. And just more recently, within the past few weeks, plans, very early plans around establishing a dedicated large-scale remelt facility on the back of some of the focus we've helped create through Mccleery. And just to highlight a few of those other important developments, Tomago Aluminium, our largest smelter in Australia here in the Hunter Valley, has recently committed to running fully on renewables by 2029. And Rio Tinto has also recently announced plans to develop over 4 gigawatts of diversified renewable power sources with firming solutions to supply its Boyne smelter in the Gladstone region of Queensland. And as Simon touched on, I've got to give a plug to Capral Aluminium, who have been really fantastic as working group partners. They recently announced last year an industry-first example in Australia to supply over approximately 550 tons of clean production scrap back to Tomago to be remelted into aluminium. This is the first agreement of this kind in Australia, but we're really hopeful that it will be a strong area of growth and opportunity. And again, with Capral, they announced last year the availability of Local, which is the first low-carbon aluminium supply to the Australian market. It is now standard on all of their door and window systems, and their super green product, sitting at around 4 kilograms of carbon per kilogram of aluminium, is available at a small price premium. So I would like to talk a little bit about that price premium. It's probably one of the biggest myths out there that's presenting challenges to the procurement of low-carbon aluminium. And believe me, as an architect, I know what it's like to stand up and have a conversation with a QS or a client and say, surely it can't be that much. So when I presented this to a large group of contractors and facade subcontractors just last year, Many of them happily took the opportunity to take themselves off mute and have a bit of a go at me, but I'm going to do it again. So aluminium, like all metals, is traded on the market per ton. Well, maybe gold's not traded by ton, but most of the heavy metals are. So this graph shows the fluctuation in price over the past year, which ranges from about $2,250 per ton to $3,750 per ton. That's roughly a 60% variation in price over just 1 year. As you can see from the quote in a recent article, looking at the price premiums between purchasers and suppliers, an average of about $30 per ton, or slightly more, up to around 50, was the expected price premium that you might have to pay. Now, I'm not very good at math, but interestingly, that just represents about a 1 to 2% uplift on the base cost of the raw supply of the material. So this has been backed up not only by Capral's products, but also by a case study shared by Lend-Lease through our working group, where at the end of it, they confirmed that the price premium they paid really didn't even touch the bottom line. Now, I'm sure it's not going to be as simple as on your next project to say that Mccleery said that this doesn't really cost anymore, but I do hope it does assist in making everyone think twice and ask again the next time you hear that low-carbon aluminium is cost prohibitive. And there's lots of available options on the market for low-carbon aluminium, and here are just a few from around the world. But unfortunately, it's not as simple as nominating a particular product or a supplier for two key reasons. Our facades supply chains are very complex. The first reason is that the supply from smelters is often tied up at least for a year or two in advance. So if you're trying to specify any of a specific supplier, it's very likely that whoever's procuring your facade may not have an agreement with one of those, and it's very difficult to get your hands on. And the second point is that with the majority of our facades coming from Southeast Asia and China, you would certainly struggle to secure aluminium from these suppliers who are outside of China. So the question is, are there any options for low-carbon aluminium coming out of Asia? Now this graph demonstrates the world share of aluminium production, with China's 57% far outweighing any other country or region. So not only do they often make our large-scale facades, but they are also, unsurprisingly, sourcing their aluminium locally. And thinking back, actually, I thought I had it in my presentation, but I didn't, but Simon luckily did, to the graph that Simon shared. When you looked at the carbon intensity globally, China was at the top of that graph for a reason. And that is that currently over 80% of their aluminium production uses coal-fired power. And many of those are captive coal stations, which are primarily for the smelting of aluminium only. However, there's good news. The Chinese government, over the past decade, has actually recognized the importance of this and had a massive shift in their smelting production. So they decided to shift an enormous amount of millions and millions and millions of tons, far more than we would ever produce here in Australia, to southern regions of China, where there's greater supply of hydroelectricity. So you really shouldn't let, we know that this is available, so you really shouldn't let the fact that we've got overseas procurement or procurement from China be an obstacle. So what can you do? The first thing is really to create a strong demand signal to the market that low-carbon aluminium is a priority for decarbonizing our built environment. We can create that signal simply by asking questions to our clients and contractors. Do you know where your aluminium comes from? What options for low-carbon aluminium exist in your supply chain, for example? And of course, by specifying it on projects. In the Australian context, we're really just beginning this journey to a low-carbon future. It's never really easy doing something for the first time, so one of the key things is to start asking questions early and often. Don't put it in the too hard basket when someone tells you it's too expensive or it can't be done. And finally, as consultants, we really sit in a unique place, often working for both owners and developers, but also under novated agreements with contractors. I think a lot of what we can do is about advocacy and education on both sides and starting that conversation as early as possible. So the more people we have in our built environment kind of ecosystem asking questions, pushing clients and supply chains, understanding really where our stuff comes from, the quicker we'll be able to bring about this change. And to help in this advocacy and education piece, Mccleery has produced a resource on aluminium for the development and construction industry, which is a short 10-pager that really acts as a primer to begin these conversations with your clients and teams. But apparently 10 pages was too much, so due to popular demand, we produced a one-pager of our top 5 key learnings from all of our engagement and research over the past 2 years, which has been quite well received. And finally, we've also published a 2-page specification guide to help you understand how best to specify and the kind of questions you need to be asking on your projects. So I'd now like to wrap up by sharing something that really made me think about the importance of all of this, and is the title of my presentation today. For What It's Worth is the title of a series of artworks by photographer Dylan Marsh. Dylan is a South African photographer and artist, and he was captivated by the landscapes of his home in South Africa, and in particular, the many disused gold, copper, and diamond mines that speak to a combination of sacrifice and gain. So this particular example was taken at the Palabora mine in South Africa, where 4.1 million tons of copper were extracted. And with the help of a CGI artist, Dylan had a representation of that 4.1 million tons of copper represented and photomontaged into his photograph. That really got me thinking about aluminium and the work that I've been doing with Mccleery. So in aluminium's case, it's produced by extracting bauxite from the earth. And you will recall that Australia is the largest producer of bauxite in the world. So we typically scrape it off the ground. They're surface mines. They don't typically dig them deep. We load them into massive trucks like this. We process them with big machines like that. We dump them onto trains that are even bigger. We take them to the shore where we load them on boats and we ship them offshore for production. And Australia has the world's largest bauxite mine in Weipa, Australia, up there in the Northern Territory. You can probably just see the box at the top, which is where I'll zoom into. So when you start to zoom in closer, you first start to get a sense of the vastness and the extent of the mine in the Northern Territory. Zooming in yet again, the kind of picture starts to become a bit clearer. And zooming in yet again to the square. This is where you can really kind of see the vastness of the operations, the movements, the machines. And then highlighted, I'm not sure if you can actually see it at this resolution, but highlighted in that tiny box is one of these, kind of where we started. And all of that really got me thinking that the next time you enjoy one of these, if you do, or we work on one of these together, we really do need to remember what it's worth. Thank you.
Thank you very much, Jeff. If you're interested in low carbon aluminium, which I trust we all are now, check out the booth next door in the sponsors hall, or you can visit the Mccleery website. Next, we'd like to invite Glenn Carlton from Guardian Glass. He will share how the glass industry is keeping up to date with sustainability.
Thank you very much for having me. Well, hello everybody. As was just announced, my name's Glenn. I'm the Architectural Design Manager for Guardian Glass, based here in Australia and looking after the Australian and New Zealand markets. Just a quick snapshot in terms of what we're actually going to be looking at today. So we'll be looking at we'll give you a quick introduction into to Guardian Glass, because some of you may not be aware of who we actually are. We're looking at the product circularity and recycled glass content. We're looking at the difference between operational carbon versus embodied carbon and some of the factors from the glass side that influence that. We're looking at the changes from moving from Green Star design and as built to the new Green Star buildings and how glass fits into that. So we're looking at the introduction of the responsible product framework. I'm looking at potential new supply chains that help support facades that go into those types of projects. A quick little snapshot into the new NABERS embodied emissions framework that's due to come into effect mid next year, and a quick chat in terms of the product transparency that are likely to be key players in this sustainability space moving forward. So as we said, a quick introduction to Guardian Glass. So Guardian's been manufacturing glass now for the best part of 90 years. We're an American business. We have around about 24 float lines spread all over the world, particularly North America, Europe, Middle East, a couple in South America, one in India and two in Southeast Asia. each one of those float lines produce somewhere in the region of 20 kilometres of glass per day. So 20 kilometres of glass multiplied by 24 float lines is a hell of a lot of glass. We're one of the world's largest glass manufacturers, but we're also one of the largest manufacturers of what we describe as architectural coatings. So things like our low-E coatings and also wet coatings like mirror. So we'll start off looking at the transition to a circular economy. So what we mean by this, if we see the image on the left-hand side there, that's typically the supply chains that we're working with at the moment. It's a linear economy. We take a product out of the ground, we make a product, and we dispose of it at the end of its life cycle. We're going through this transition at the moment into a circular economy. Instead of disposing of products at the end of their life cycles, we're looking to recycle those and turn those back into usable products again. And from a glass perspective, glass is one of the ultimate sustainable products in that sense. It can be used and recycled endlessly. A little bit like aluminium with our previous speaker, glass has an endless life cycle. The other added advantages to doing that from a glass perspective is that the increased nature of recycled content in terms of glass production has a significant impact on the CO2 emissions of the glass we use as well. So what kinds of glass can actually be recycled? So we've always recycled clear float glass, glass in its most basic form. But things like laminated glass and coated glass have always been deemed as hard to treat. And it's only been in recent years as many of the Western manufacturers, let's say, have started to drastically increase the proportion of recycled content in their products, that we're actually now starting to recycle laminated glass and coated glass as part of that process as well. If we're unable to recycle those glass products in terms of recycling them back into architectural quality glass, at the very worst case, they should be downcycled. So that's taking our waste product, turning it into cullet, which is a raw material, and then downcycling them into sort of lower quality, for lack of a better term, glass products like glass fibre insulation, road signage, enamels, etc. So we should never be seeing waste glass, go into landfill. We're pretty good at that here at the moment, particularly on the east coast of Australia. If we go over to Western Australia, not quite so good. Many of our customers are actually disposing of their waste product into landfill. So we're actually undertaking a few test cases at the moment, and working with our customers to see what we can do to actually take their waste product, bring it back to one of our facilities, and actually look to recycle that at one of our manufacturing plants. The end-of-life recycling is something that we're actually not particularly good at here in Australia, and probably also globally as well. There's a lot of labour components in terms of taking an end-of-life product, breaking it or disassembling it, and then recycling it. So that's probably the next stage of that development that we're likely to see over the next coming years. And if there are any developers out there that would like to go through that process and look to recycle end-of-life products, we'll be really, really excited by any opportunities to explore those opportunities. But as it currently stands, that the infrastructure really isn't in place to do that. But we'd like to try and develop that if at all possible. Operational carbon versus embodied carbon. So we're probably fully aware with these terms these days. They're spoken of quite regularly and a lot today. But operational carbon is the carbon that's effectively emitted during the operation of our building. So the running of our heating systems, our cooling systems, and that's largely controlled from a facade perspective under our local building code. So here we're talking about the NCC. Particularly in commercial construction, we had a significant change to the NCC in 2019, the Section J component. We had drastic steps forward in terms of improvements in terms of the energy efficiency of our facades. The embodied carbon is the other side of that equation. So the embodied carbon of the CO2 emissions that are emitted during the actual physical manufacture of the products that we use that go into our buildings. And that's the component that we've never really considered too much in the building industry, particularly here in Australia. So looking at operational carbon, the solutions exist, and we're starting to adopt many of these solutions. Many years ago, we were sort of talking about SHGCs, somewhere around about the sort of 0.55 being pretty standard on a commercial construction. Under the new NCC 2019, we're sort of talking more likely around about the sort of 0.2s in terms of SHGC performance, reducing our air conditioning requirements in buildings. Similarly, in terms of U value, many years ago, if we're using monolithic solutions, we're having a U value around about 5.8. Typically these days, under more stringent building codes, we're operating somewhere around about 1.32. But there's still scope to improve those further still. So if we look at a little graph here comparing operational carbon versus embodied carbon, and what we anticipate the proportion of each being over time, you can see that because of the changes to our NCC in terms of Section J, our operational carbon emissions are looking to decrease over time. But you'll notice that our embodied carbon values are staying relatively constant. So we're seeing that's clearly the portion of the building, certainly the next, once the changes to operational carbon take place, that the embodied carbon is really going to be a key focus in order to reduce the emissions associated with our built environment. From a glass perspective, how do we drive down that embodied carbon? And we're really looking at three key areas. So furnace efficiency, so having more efficient furnaces that use less gas and less energy to manufacture our glass. Looking to increase the amount of raw recycled content, which has a significant impact in terms of the embodied carbon or the emissions associated with the embodied carbon of those products. And we're also looking in terms of the energy mix. So older float lines may have used something like a fuel oil fuel mixture, which is quite dirty. Over the last sort of 30 or so years ago, most of those facilities have now transitioned to natural gas, for example, which is by no means perfect, but significantly cleaner than fuel oil. And most manufacturers are doing a lot of work in terms of what's that next step. Are we talking about hydrogen? Are we talking about biofuels? Can we electrify? So there's a significant component there in terms of that fuel mix. In terms of Green Star, there's been some significant changes in terms of the way that Green Star works. So we're transitioning from Green Star design and as built, which from a glass perspective really only meant a slightly more onerous energy efficiency requirement. We're now transitioning to Green Star buildings. Now, Green Star buildings still has those energy efficiency requirements, but we've also seen the introduction of what we call the responsible product framework, which does start to have an impact in terms of the facade. So as you can see there, we're breaking the building down into structure, envelope, systems, and finishes. Envelope is clearly what we're focused on from a glass or a facade perspective. And what we need to do to achieve the 4 points under the envelope category is have around about 30% of the products by spend with an RPV score of 10 or greater. Now that RPV score is attributed by the Responsible Products Framework, where the Green Building Council effectively attribute a value to different products based upon their sustainability credentials. We can actually achieve a further bonus point if we go down the leadership challenge, whereby 10% of the responsible product value of 15, and also 60% of the products having a responsible product value of 10. That actually enables us to get a further 1 point, enabling us to achieve 5 points under the envelope category. You can see here in terms of the roadmap moving forward for the responsible product framework. Currently for the envelope, we're talking 30% with an RPV score of 10, but the aim is to actually start to increase that over time. So the next iteration is likely to have a requirement of 60% at an RPV score of 15, and beyond that, 80% with an RPV score of 20. Now, from a guiding perspective, we can achieve these RPV values and achieve compliance under the Responsible Product Framework. I believe we're the first glass manufacturer that's actually been able to do that, but we can only do that by utilising our European products. So this is going to require a slight shift in terms of the supply chain required to deliver that. We have to use European products. So we're looking at incorporating production facilities in places like Turkey. Is quite easy for us to use our European products using Turkey's sort of low-cost labour and manufacturing environment. We can also combine our Green Star compliant systems out of Europe with aluminium systems also out of Europe that also comply to produce a fully compliant unitized system. Many of these systems will also have a much lower embodied carbon value as well. There's also an introduction of a national framework for embodied carbon that's being introduced by neighbours. So previously there's not been a national standard when we're actually assessing embodied carbon within our buildings. And neighbours are actually putting together a framework at the moment. There's a consultation process taking place as we speak. And that's actually due to actually physically be released mid next year. Particularly for you guys here in New South Wales, that's going to be really, really important for you guys because as part of your Sustainable Buildings SET timeline, actually as of the 1st of October this year, it's going to become mandatory for all buildings to record the embodied carbon emissions of various projects at DA stage. Now, as of mid next year, when the neighbours embodied carbon framework is actually released, they will then transition to that neighbours assessment. So it's going to be really, really important moving forward, and the questions are going to be asked, how are you physically recording that data? Many of the facade systems that are typically used in Australia at the moment don't have embodied carbon values attached to them. They don't have EPDs or any other embodied carbon values as part of those systems. What you'll find under the neighbours assessment is that they're likely to use a default value for any product that doesn't have, say, an EPD or some kind of recognised embodied carbon data. So I've taken here a default value from the EPIC database using 6mm clear flow glass as a reference. So you can see there that under the EPIC database, you're talking around about 31.4 kilos a square metre for a 6mm clear flow glass. From a Guardian perspective, our European 6mm clear flow glass that's been third-party verified as part of an EPD, we're actually achieving a value of 16. So there's quite a significant difference from one manufacturing site, or particularly regionalised, to another. One of the introductions that Guardian have introduced in the last few months, many people may be familiar with our glass analytics software, which has traditionally been used to generate performance data. We've also added an embodied carbon calculation as part of that data as well. So you can log into our software, put together your glass configuration, which can actually give you the embodied carbon value of the glass components of that. And that stems from our EPDs, which is third-party verified as well. Product transparency. So as we mentioned before, EPDs are going to be becoming far, far more common, particularly within projects that are having to comply with some kind of embodied carbon assessment. The neighbours' embodied carbon assessment is likely to be drawing their data from EPDs. But also other product transparency certifications. So we currently use a cradle-to-cradle certification, but there's many other certifications out there, whether you're talking about Green Tag or Declare or many, many others out there, and we're going to start to see those utilised far more widely. So thank you very much for your time, and hopefully there was some interesting information in there for you. If anybody has any questions, I'm in the hall later today. Please feel free to come and see me and have a chat.
Thank you very much. And for those who don't know, Glenn has a whole library of technical resources, a great person to ask questions. Just before I call next speaker, just want to remind our speakers for session one, to stay behind so we can have a photo. And our last speaker for session one is Angus Macleod from Vector Foytech, and he'll be giving us some case studies on lightweight roof design.
Thank you, everyone. Good morning. My name is Angus Macleod. I'm from a company called Vector Foiltech. We're specialists in something called ETFE technology. Now, don't worry, I'm not going to talk too much about ETFE. If you'd like to learn more, please come and see me afterwards. What I'm here today to talk to you about is lightweight structures and possibly some case studies where I've applied some of the principles that we use on a daily basis in order to achieve lightweight style buildings. So if we start at the top, material efficiency, that's the holy grail. That's what we're trying to do. We're trying to maximize our efficiency of materials around the place. Now, that's not necessarily the same as minimum weight for span. You have different materials, different types of technology that you can apply in order to get material efficiency. These days, as the previous speaker was saying, embodied energy, sustainability is a big thing. So that's part of the process as well. We like to get in there and try and communicate what the technology is doing, not just for our own systems, but for other primary structure as well to support our material. Operational efficiency can be whatever you really want it to be. Usually client-driven. They might be saying, for example, the project in the top right there, which is a 30-meter diameter dome at Auckland Zoo. They might be saying, it's going to get really hot under here. For operational efficiency, we require louvers in the top or for smoke or whatever. So it could be, I want a column here, I don't want a column there, that sort of thing. So operational efficiency is a prime driver for any type of lightweight structure. Form versus function. I could spend an hour or two talking on that topic, but basically it comes down to shapes and using shapes to get your function happening. And then tension versus compression versus bending, that's really just a realization that different materials are better in different circumstances. Steel is better in tension than concrete is, for example. But we run the full gamut of materials these days. We use GRP, carbon fiber, whatever we can to achieve the outcome. Now, if I was going to pass on any tips to the room, I'd probably say define your constraints early. Lightweight structural design is a journey as much as anything else. So by defining your constraints early, you minimize the time you spend going down different pathways later on down the track. We're also at a point in time now where calculation and modeling software is far more advanced than it ever has been in the past. So back in the bad old days, and John here will remember them, we used to physically model lightweight structures, build them in-house to try and figure out what the best shapes were. It was great fun, but it used to take forever. If you were wealthy enough, you could afford a microstation computer or something like that, and you'd analyze it. It would take 3 days, and woe betide you if you got your structural constraints wrong. These days, you can parametrically design things and have answers out in a couple of minutes. It's great. So, tip: experiment, play with your shapes, and that will really reap benefits for you down the track. The project on the bottom left is a nice little 28-meter span porte cochere that we did for a shopping center in Phnom Penh in Cambodia. So around about 3-meter wide ETFE cushions in that case, to give you some idea of lightness. So case studies. How do we apply some of those philosophies? This is a rather nice project I did in Penang about 3 years ago. The client came to us as a business park developer, a bit of international backing. You can see the big blue box of IKEA in the background. They wanted a roof over their business park, trying to shelter it from the rain and stuff like that. But the concept that was given to us as a DNC contract was a very rectilinear solution, stepped with lots of returns around the place to stop wind-driven rain. We took the client on a journey, ended up with a very different style structure to what he originally envisaged. Banana-style trusses spanning around about 38 meters, about 2.75 meters deep, ending up with about 55 kilos of steel per square meter and about 12% embodied carbon of an equivalent glass structure. One of the material efficiency arguments that we used was to look and work with the local steel fabricators who were finding it very, very difficult at the time to get box sections or CHSs of any size. So they'd invested heavily in robotic welding, which meant that they were able to do box girders, custom box sections. So that enabled us as designers to get in there and say, well, you know, we can use that. We can start putting plate, which is very easy to get, thicker sections where we need it, rather than where we don't need it in mid-span. One of the nice things about ETFE is that we don't really care about deflection so much. So I can afford to be a bit more laissez-faire with structural movement. But by doing that, it gave us an enormous amount of material efficiency in the scheme. We also mucked about with the shape, introduced a wave-style form instead of this stepped rectilinear type form to try and promote airflow through the building, trying to get rid of some of that vehicular smoke. Again, some operational requirements that the client had to try and improve the livability of the space. Got rid of the vertical returns by having an overlap style system, and that also gave us the ability to concentrate water flow, which we were then able to collect and then push out to the rest of the park. Painted the steel in a sort of dark grey colour, goes very well with the sort of black and white philosophy of that part of the world. And just so you know, this isn't photoshopped, here's a nice little sort of drone fly through, just showing what it's like to be under the waveform roof. Quite a nice response. Another quick case study. This one's in Canberra. We completed this in December. This is at Canberra Centre Shopping Centre. So the client came to us, retail client, D&C contract, although in this case, the client decided to take on board the steel fabrication himself. So we just did the design. Introducing two 20-odd metre square grid shell style roofs. The eagle-eyed amongst you will see that it's actually a compound curve, so a bit more creative than just a plain arc. Around about 60 kilos of steel per square metre, including the columns for this one. And again, around about 13% of the embodied energy. And the main reason for that is because ETFE doesn't have a lot of heat that goes into the manufacturing process. So it's quite a sustainable material, it's 100% recyclable, and et cetera, et cetera, et cetera. We try and take care of it. One of the design avenues that we went down was to get a wind tunnel test done. Now, I regard this as an almost mandatory thing to do on most of my projects. Australian standards, wind code, said that I was getting around about 1.35, 1.5 kPa local wind pressures. Got a wind tunnel test done, $25,000 in 4 weeks. Money well spent. Getting peak pressures of only 940, two-thirds of what the code is saying. Great. And you'll see that it's concentrated in various different localized areas. This enabled us to really dial up the efficiency of the structure through design. And for, like I say, $25,000, money well spent. Same project from above during the day versus night, controlling the solar heat gain. This particular one, it's an external canopy, so I don't really need to control the solar gain that much, but we want to control glare. But then at night, it becomes nice and transparent. One of the other operational constraints by the client in this case was the tree trunks. He wanted some visual mass there. But again, going back to the idea of availability of sections, getting large diameter sections was enormously difficult. So we created the tree trunks out of smaller diameter sections, which were a little easier to get, and then branched them off in different directions at the top. This also gave us the ability to make them work compositely, which gave them a bit of extra stiffness, and also a space that we could run the roof drainage down the center. So it was a nice little architectural design feature. Now, you can do lightweight design on the gross structural members, but then you get down to the nitty-gritty and start to get to the details, and that's where it starts to become alive. But there's no point going to the effort of doing finite element analysis on each and every joint to try and maximize the efficiency if you can't communicate that philosophy through to the steel fabricators and the steel detailers. If they don't get it in the shop, then you are not going to receive it. So we spent an enormous amount of time trying to make sure that the steel fabricators had both the capacity and the understanding to be able to do this type of structure before we delivered it. Another quick case study. This one is Garden Lane down at Botany Town Centre in downtown Auckland. Some of the Kiwis in the group will probably recognise it. Again, a nice little steel grid shell, this time supported by glulam arches. This is an example of some of the EPD information that we give out on any project. We work a lot around the world, so we're familiar with LEED and BREEAM and all that sort of thing. And I know that there's some people in the audience here today who are from the Green Building Council and those sort of places. We try very hard as a company to communicate exactly what the process sustainability criteria are from ETFE throughout the system. So you can see here that we're getting using around about 17% of the primary energy of an equivalent glass system. We've got carbon is about 12% down here. We've got ADPs, all sorts of things going on. Another client-defined requirement on this project was that he had a lot of sensors down the spine of the roof, including active lightning protection, weather sensors, and so on and so forth. So he wanted to be able to get out there and maintain them, monitor them, etc., etc. So we had to put in well, we do anyway, but a man-safe trafficable walk system along the ridgeline. Have I just lost? Hello? We're back. We printed the north side out of a slightly darker frit pattern than the south side to control the solar heat gain on the retail below. So we have that capacity as well. But it doesn't really compromise what the visual aesthetic is at night. Nice little drone footage taken during construction. You can see the cushions here are highly warped, three-dimensional elements. It's not mirrored down the center line, so every panel was different. You can see the person there for scale. Trafficable netting, which we use in lieu of scaffolding. It's meant to be reminiscent of an eel net. And lastly, because I can see I'm running out of time, one of my personal favorites, I've spent far too long over the last 18 months or so designing this project in Singapore for a company called Sabana Jurong. Sabana Jurong are a very large engineering consultancy. They do a lot of government work, high-rise, high-density building style projects. And they came to us with Moshi Safdie Architects and said, Angus, we've got a bunch of buildings here. Please put a transparent, lightweight style structure in between them all. Yay. So we did this up to LOD 350 or thereabouts. We used a cable truss system. Now, cable trusses are pretty rare. I think I've only done about 3 or 4 over the last 25 odd years. They are visually stunning, very, very lightweight, but enormously tricky to try and design. And you know, one of the things I love about this is it's in Singapore, so low wind loads. Thank God. Oh, sorry, back. So you can see here that we have around about a 1 or 2 story difference in height around the sides. The idea is that we drain to a central gutter style system and then pick that up at the bottom and then use it as a water harvesting system for the internal space and also the roof garden on the right hand side. Some of the structural drawings here. Top chord, 2 28mm diameter cables, just over 1 inch thick. About 100mm wide, so I was able to nest my extrusion profile down inside, in between them, so it's nice and svelte. Bottom chord is 1 32mm diameter cable and 16mm vertical tie rods. And these are at 4.2 meter centers, so you can get some idea of how lightweight this thing is. We have to design for lots of different circumstances with ETFE, but one of the things is what happens if the power goes out and we start to get water ponding. Cable trusses hate point loads. terrible at them. So we have to design for that situation and minimize that. So we have something called a water ponding valve, which will limit the amount of water that's able to build up in any particular space, and that affects the engineering as well. But again, it's a design journey that you have to go through. We decided, for material efficiency's sake, if we're going to have a gutter in there, we might as well make it structural. So we have a structural gutter, which is acting as a lateral support mechanism. This is actually embedding itself between the top chord of the truss and the bottom chord of the truss. So we have a nice instance where the cable goes through the gutter, which is always fun. Man-safe anchor points. These are the water ponding valves that you can see on the left and right here, embedded in the cushions themselves. And custom designed stainless steel clamps using lost wax techniques for the picky amongst us. You can see my extrusion nestled in between the cables there on the right as well. The clamp on the right we call the football, for obvious reasons. Cable structures are also very prone to movement, so perimeter detailing becomes very, very interesting to try and do, because the cable trusses do move a lot. So you're dealing with rotational movement all over the place. End result. This is shortlisted for the World Architecture Festival, which is being held later this year. But I think you'll agree that it's quite an interesting space. You can see the custom designed print pattern here as well, with stripes on the roof. Special commission by the client. Big green space underneath. Anyway, thank you very much for your time. I believe coffee is served next. Thank you.
Thank you, that was great. And thanks again to all the speakers from session 1.
Yes, I just wanted to say I have to agree that lightweight steel design has always been a journey. We are running a little late, so short break now over in the sponsor booth. Don't forget to visit OVEX particularly if you want freebies. They've got free AFL tickets if you sign up for their competition. Yes, I will see most of you back, hopefully all of you back, just before 11 o'clock, if that's okay. The speakers from session 1, could you please come back so we can get a photo, please?
Thank you. Welcome back, everyone.
Great to see you all walking in. Sorry, I've just had a cup of coffee. Yeah. A quick reminder for those who are just joining us to please turn off your mobile phones or set them to vibrate so we don't disturb the speakers or the panelists.
Right.
Also, if session 2 speakers can stay back for a photo afterwards, that would be great. Plus, Glenn Carlton, I did remind him, so hopefully he'll stay back afterwards as well.
Cool, great. So we start. The first speaker of the session 2 is James O'Callaghan from Mccleery O'Callaghan, who will be talking about our favorite contemporary material, glass. Please welcome to the stage, James. Thank you.
Yeah.
Thank you very much, and thanks very much for everybody for your time here today. Good to be here. I'm going to talk about a number of things today about transparency, as might be suggested in this slide, and the conflict that we have in terms of energy. But first, I'd also just like to acknowledge the traditional custodians of the land in which we meet, the Gadigal people, for their care and looking after this beautiful place, land and water. So just a little bit, for those of you who may not know who we are, Mccleery O'Callaghan was a practice of engineers, which I've co-founded in 2004, nearly 20 years ago now. And we've been working on various different typologies of work, both in building structures and facades, with a focus on materials, and in particular, the reason I'm talking today is a particular passion we've had for glass over the years, and where we've taken that in our various projects. We've now expanded our network to 11 offices around the world, one of which is here in Sydney in Surrey Hills. And it's very nice to be back here in the good weather, so you'll see me as much as you can in the winter when I'm not in the UK. So I'm going to sort of talk about two things. One is really a journey of transparency and the evolution of transparency, also almost a sort of a maniacal chase of transparency, which has been the last 20-odd years of my life, and how that's manifested itself in building structures and typologies of glass itself, along with how that is, in fact, in many ways in conflict with what we now need to deal with, or what we're dealing with in terms of building envelope and performance. And although that's been a transitional period, it's clearly most pivotal today, given the importance of our building envelopes as it relates to sustainability and sustainable buildings. But going way back, glass has been something that's been around for a long time, and in fact, this rather evocative picture of Chatsworth Conservatory, which is no longer there, but it was a point at which glass was very much used and understood as a material to create and develop, to allow light. But in many ways, it was also kind of partially used as a structure. It wasn't really understood as a science at the time. But you can see here in the very filigree nature of these beautiful old Victorian greenhouses how glass played that participant role in actually creating this shell. So this always sort of focused and fascinated me as I then, many years later, embarked on a journey with Apple, who were able to find opportunities and effectively sponsored the development in ways in which glass has been used today in many ways, and that whether that's through size and scale and connection and the like. But just taking back, some of it was about this sort of march towards transparency was about how do you join bits of glass together. It was about connectivity. It was about materials and understanding the latest innovation in materials. So this, for example, was way back in 20 years ago when we were discovering the benefits of century glass and how that might be used to be weaved into not only the lamination of glass but also the connectivity of glass, and that led to these kind of ideas about making glass as well detailed as possible, as rigorous as possible, as limiting and minimizing the connectivity of glass, the connectivity being very important given that in glass, generally speaking, as it relates to transparency, we are looking always for reducing and minimizing the amount of connectivity, and if at all possible, eliminating it. But certainly where it exists, its focus on and the rigor on its detail becomes a very important part of that, a very important part of the language. And of course, these structures don't necessarily integrate them, are not always integrated in the similar materials. You've got to deal with different conditions, historic and the like, and different forms and different materials, which then, and different techniques of creating glass, whether it's in this instance, the adoption of chemically strengthened glass to ensure that we get much smoother curves and the like. So this sort of journey was marching along for the last 20 years in developing transparency and increasing the ways in which we could integrate structure and glass into the overall envelopes of buildings. I mean, I quite like this idea of being able to use much less material. So why have a staircase that is a staircase and an envelope when you can combine the two and seamlessly have two things doing the same thing, which then on different scales, when you then ramp that up to 20 odd meters or something, as it is here, and then integrating all of those elements that were part of that connectivity within the glass itself. So distilling things down to a sort of as pure as possible and as transparent as possible, and evolving each one of those details iteratively each time as each project came along. And I think that was an important part. It was never a static development. It was always a continual refinement of detail as one understood the material, the behavior, and of course the fabrication technology that was existing and evolving at the same time in parallel to many of these projects. But it was ultimately about maximizing transparency, which of course is a deeply questionable subject when it comes to energy and light. And this, for example, in Sydney, which is still here looking great, was the first of the projects we ever used where there was singular 15-meter pieces of glass. At that point, the glass was splice laminated, so it was made out of 8-meter pieces of tempered glass and laminated to create 15-meter pieces. But it was at the start point where the size of autoclaves had shifted from 6 meters to 15 to 20 meters, to allow this to happen. And you might sit there and say, well, it's not particularly practical to have bits of glass that big, and there's questions about maintenance and replacement and et cetera, and of course, and its cost. But it was really about, at that point, the drive was about transparency. It was about eliminating elements and eliminating joints to maximize that transparency. So in context, that was what we were looking to achieve at the time. Similarly with the project in Fifth Avenue, which became a sort of iconic in its nature, I mean, creating this lobby space to create an underground shopping location was quite difficult, so it needed to be a sort of beacon, something that announced its presence. But in first building it in 2006 with the technology we had at the time in terms of how to put the glass together that we understood at that point, the limitation on the sizes of pieces of glass, over a period of 6 years, by 2011, we were able to then replace that with something that then went from 90 panels to 15 panels of glass and increased that transparency. Not the most sustainable move we've ever made, given that the first iteration of it was perfectly fine, but we were able to demonstrate, I guess, through its refurbishment, the embodiment of that development in glass technology and transparency. Integrating these connections, etc., and reducing and increasing the transparency of all these elements. So I think it is, certainly with glass, it's all about the detail, it's all about what you're looking at, because your eye is attracted to that relative to the transparency of the glass itself. So that was something that was sort of a core to our thinking and a core to our evolution of these kind of ideas as they developed further into larger typologies in Hong Kong, and through the work with Foster and Partners later in China, where in fact it's distilled even further to have even less in terms of its connectivity or its visual noise in terms of that transparency. So it was always a journey. It involved various different ideas about different materials and a willingness to explore different materials. And this particular concept in Istanbul, which we're like, how do we create something that's literally 5 sides with the least amount of material possible? We clearly understood the glass. We started getting quite interested in what composites could do, and in fact carbon fiber, and how that was weaved into the sort of sports industry. And you can see here in this sort of performance yacht how that was being developed. These kind of high strength materials, lightweight, high strength materials, which could achieve much more with less in a way. So this very simple idea. Simplicity comes with a great deal of complexity in terms of its resolution, but accommodating this kind of 5-story element, 5-sided object with 10-meter span, with 50 millimeters at the edge and 150 millimeters in the middle, and creating it such that it had a sort of seamless, almost dematerialized nature to it. It did win the Structures Award in 2014, I think, which was interesting because it doesn't seem to have any structure, so much to the chagrin of the engineers who didn't win that year. But it was part of this kind of ongoing journey of reducing and to the point at which we could, less is better. And I suppose in a way, from a structural perspective, this idea of doing more with less, and I've always been fascinated with the idea that we can use our envelopes in a much more practically to be more of our structure, and therefore, rather than this idea of building structures and wrapping them, there seems to be much more about how things are integrated into be one performance in a way. And of course, there's limitations, and nothing is ideal in this particular project, which was the Steve Jobs Theatre, which was part of the larger, wider development that Foster and Arup had developed in Cupertino for the headquarters for Apple. This was something that we worked on in terms of taking those ideas that we'd seen in other projects and distilling it further into something that was on a larger scale. Similar idea, let's try and find some better way in which we can use the envelope to support this roof, therefore creating the most open space within it possible for the place to be used and utilized appropriately, and kind of exploring what those ideas might be. So it landed very much in having something that was using carbon fiber and using it on a much bigger scale, so creating these 44 pieces of carbon fiber wedges, bolting them together and sealing them with gaskets between it, and then lifting that in one piece on top of what was essentially 6-meter pieces of glass, 44 of them around the edge. So quite a simple idea, but in order to actually achieve it, you can kind of see from this little video how slender this structure is, given its scale and the scale at which it sits, and he's sort of slowly placed on top of the glass. We use the word dropped, but that's not a particularly good one in this instance. And then from that, you create this incredible sort of space that, in fact, is serviced by its electric conduit and the like through the silicon joints that allow the power and water to be reached from the ground to the roof, which, in itself, it's and I remind people it's got a stainless steel ceiling, which has got the ceiling, in fact, is heavier than the roof, so it's not normally that way around. So. And then from that, other things have evolved, and they're sort of addressing this idea of transparency. And I think this just introducing the idea that, of course, big glass structures that have lots of ability to let in light and energy aren't really the future in terms of a sustainable envelope. But that's not to say that those ideas about how the glass has been used and how the glass has been integrated into structure aren't important. I think this is a particularly good example that we recently finished with Foster Partners in Marina Bay Sands, where in fact the glass is quite largely actually fritted, and it's opaque. So from an energy perspective, it actually rejects and controls quite a significant amount of light and energy that comes into this space. It's also double glazed and thermally insulated, and then within it, it has a series of louvers and shades which then diffuse glare and deal with glare as well as reject energy to some extent. So it's a much higher performing envelope, yet it still embraces all those ideas about how glass can be integrated with the structure. All of these vertical elements are in fact very, very slender columns which are braced by all of this glass panel. So the whole thing works together. It can't work without each other. You can't, the frame won't sit, the frame would collapse without the glass, and the glass would collapse without the frame. So it's all kind of an integrated piece, which I think ends up being a way in which we can get things really, really refined. So there we have the last few years, or many years, where the sort of, the chase towards transparency is in fact somewhat in conflict, as I say, with the energy and the performance of buildings, and how, as we look at things today, how things change and how things need to be addressed in different ways. And of course, we've all seen that glass has had a very bad rap to some extent with some of the stories that the press has given over the recent years as sustainability takes a grip on it, and the industry's had to respond to that. And we as researchers and as engineers and as the industry have to find ways in which glass remains relevant in our building envelopes, because it's something that, of course, we love and we dearly enjoy the performance of. We want to not necessarily end up in a world where the 60-40% window wall ratio is defined, or even less so, because that seems to me to be going backwards from where we were and have been, and what we've been able to develop in terms of the way in which glass is used in buildings. We understand its benefit. We understand that its future is very dependent on how it responds to the demands of sustainability and the demands of how building performance needs to go. And this graph is kind of somewhat quasi-indicates the fact that, we're now in a place where we've had to, codes are demanding such that window wall ratios are somewhat less, and therefore the glass has to perform much higher, which is all entirely reasonable and sensible. So how is glass going to respond to that in systems over the next few years? And I quite like this slide because it was something that I noticed in a photograph. If you look to the right, the sort of Singapore, as it reclaimed more land, it went from this kind of original sort of 60-40% glazing right the way through the sort of green phase, which John was telling me about yesterday was actually because of the efficiency of green glass, which I hadn't fully appreciated, right the way through to more neutral colours that you see and more neutral performance, as higher performance has happened today. The question is, are we going to slide back in that direction, or is glass going to meet the demands necessary to be able to become and remain relevant? And there's that, along with the other aspects of sustainability and how one has put that together in terms of its future use and how glass sits in the supply chain. This project in Hong Kong is something we recently finished. It's for Swire. It's a tower which has achieved a high-performance energy envelope using 70% window wall ratio, which is very nice. Nice 3-meter wide unitized system. Super fantastic views of the surrounding landscape in Hong Kong, and it's a real eye-opener from that perspective. not dissimilar, very recent building we finished in London with 53% window wall ratio, which of course is much more the sort of punch window idea. From the inside you have this. Again, the glass, your connection with the outside is somewhat muted by the internal, by the framing, etc. Not that there's anything wrong with this, but it's clearly an understanding of how that would be. And in Norway, this particular project is a very recent project, which is now meets pretty much is the demands of the code. The code is dictating that buildings have a very similar aesthetic to this, with a 33% window wall ratio and triple glazed. Now, at that point, we're sort of getting to the point where the glass has, in many ways, a decreasing amount of connectivity to the outside. So that's fine, and that's all good, but we need to understand what that means in terms of those the places where light and glass and architecture and connectivity is important, and how that then works together. So we have to have this situation where the facades need to work harder. Do we need to compromise on that? What are the systems that we're all aware of that we need to think about in terms of getting those facades to work harder in a more sustainable environment? And we've heard a lot about that this morning, all of which is incredibly relevant to the materials that we choose and the processes we choose. But it's not new, right? I mean, it's a question of how it evolves. We want to have daylight views, and we want to have we don't want overheating and we don't want glare. There is a conflict between those two. We have to think that the demand of the facade is to do more, and that demand is only going to increase, and therefore the systems associated with it to avoid this kind of conflict become important. There's lots of things we can do now. We all have great tools, parametric tools, which allow us to look and study things in a much faster, more real-time environment. So we can understand the impacts of orientation of facades as it relates to solar gain, thermal performance, etc., wind, structure, etc., which we had before but took time. Now we can do this much quicker, and that helps, I think, not only significantly increase the potential performance of an envelope, but it allows us to see the opportunities that it can do that more in a more real-time thing. And I think a real-time pace in the collaboration with the design team itself. So that feedback becomes that much more important. And these projects that we in continually developing end up embracing some of those things. And of course, you then get different facade typologies that start to evolve, whether that's shading, whether that's dynamic solutions. And we've seen some great examples of closed cavity facades here in Sydney, one of the centres of, in fact, that particular technology really globally. But also other things that are sort of have emerged, are emerging, are re-emerging, or are developing, such as dynamic glass and shading, and all of which is important for us to be able to understand or moderate that energy transfer and that comfort as it sits against the envelope and our occupancy of the buildings. So, natural ventilation with these other elements that we are used to in terms of different technology. I mean, all of which is fairly standard, but using frits, etc., is using shading. We see it all around the place, as I've shown in Singapore, and ways in which we can adopt these technologies, which become increasingly more perhaps sophisticated and combined within this envelope, which is key to embodied carbon. As Simon was pointing out, this idea of having more performance within the envelope is great, but it also comes at the cost potentially of embodied carbon. So how do we rectify, or how do we correct that such that we have these higher performance systems which do great things to allow more transparent glass, but don't necessarily, but require more demand and material in the facade itself. This is actually the first closed cavity facade that we just recently finished for Google, which is in a all mass timber building. So things like this, it's a fully mass timber building, full closed cavity facade, great. So in terms of its embodied carbon, you get some really great ratios out of this kind of thing. It's limitations in other ways, but there are examples, I think, of how thinking starts to evolve. Biophilic facades, with Collins and Turner's project here, and that's not, or in Central Park, Sydney. These ideas of using other materials and other organic and inorganic ways in which we can enhance our envelopes to do more. And even on responsive glass like dynamic glazing. In fact, this research that we've been doing at TU Delft, actually where the glass is responding to your your emotions. So if you're struggling from glare, then your facial recognition starts to trigger the way in which the building will work or the skin will work. And I think those ideas that the envelope starts to react more in the way that you as a human and the envelope you have react to temperature and the like starts to become a bit more dynamic and a bit more interesting. And it's that sort of interface to ensure that we have thermal comfort. The thermal comfort technologies in terms of natural ventilation and the like are important as it starts to infiltrate the building itself. You'll hear more about this, I'm sure, from Viggo and this project in Henderson in Brisbane, which we're working on, which actually brings in some of those ideas as it transitions through to the lower levels of the building, and it starts to integrate more natural ventilation into a tower architecture, which it wouldn't have not been done before. This is, to Simon's point, this is actually, I did spend a lot of time looking at this graph, Simon, actually, and I think it's an incredibly useful piece of information which gives us some real guidance in terms of, systems and understanding our systems and what that means in terms of embodied carbon. We've got to be conscious of that. We've got to be very conscious of the procurement routes, all of which was touched upon before, and likewise, I've been quite astonished at ways in which, depending on where you're sourcing your material, and the nature of that energy grid in which it's sourced has a massive effect. Atlassian is a good example of that, where these becomes quite important in terms of the decision. We have a tool which it's open source tool which you're welcome to write to us and download. It plugs into Revit, in Revit allows you to in real time understand your embodied carbon of any elements within your structure that you tag and nominate within itself. So over 1,000 people have downloaded this. I believe it's not too buggy. It doesn't have any spyware in it, don't worry. And you're welcome to, if slightly confusing, ECO@EOC Engineers. If you write to us on that, you'll be more than welcome to look at that. I'm going to do 2 quick case studies. One of which is the project at Atlassian at Central, which we've been working on for 3 years now with Dexus and Atlassian, but of course with other consultants, TTW in particular, our partner that we've been working with. But just to go back, we were given a brief way before the design competition by Atlassian themselves to look at ways in which we could create a building, a tower typology that had 50% less embodied carbon as a primary goal. Operational carbon reduced by 50%, and how renewable energy would be integrated into that idea. So a very simple idea, but quite a complex problem, very complex site. We came up with this idea, which was basically saying we wanted to make a timber tower. You can't make a timber tower that big, so how do you put as much timber as possible into a building, given that floor plates are the majority of your embodied carbon mass. So very simply, we created a bookshelf idea and plugged in 5-story timber buildings, which was pretty much the limit of the fire code for non-performance rated timber structures in Sydney at the time. In very basic terms, that was the concept. That concept went, and 5 architects did a competition. They didn't have to follow the reference design. They all chose to follow that reference design idea. That project was then won by Shop, who've now been developing this, and this is the team that's been developing it over the last 2.5 years. It's now being built by Built, an Obayashi joint venture, and under by Dexus being the developer of it for Atlassian, who will obviously be ultimately the end client. But it's stood the test of time. It's managed to. It's been from a building that has pretty unusual concept. Difficult site, and it's great credit to all of the team, particularly the Dexus and Atlassian, who've driven this through to ensure that these super important sustainable ideas have been maintained through the process. And this is just an example of how that has actually made its way into the final design, and some statistics in terms of where we are in terms of material volumes, how we've kept that on track to be close to a 50% less embodied carbon relative to a benchmark, which I'm not going to show that now. We did a benchmark design in steel and concrete, which we could then measure and compare this against. But you can kind of see, just diagrammatically, when you take out the rest of the structure, the majority of it seems to be timber, and that timber clearly massively drags down the embodied carbon. The envelope itself is pretty complex in that it has, in many places, to span these 3 floors. You've got these big open park spaces onto the north and to the east of the building. which creates these buffer zones, naturally ventilated spaces, so the facade has to work with the natural ventilation. It also has to be the sort of primary envelope, as well as having a secondary envelope on where we have the timber habitats, as we call them, these inserts. So it's a complex kind of approach, but it does create these buffer spaces. It creates these naturally, dynamically ventilated type spaces in certain times of the year where that's possible, and it gives much more connection between you and the outside of the building. So I think from that perspective, it's pretty experimental, but it's it embraces all of that idea about thermal comfort and comfort itself, as well as natural ventilation to put less demand on the facade itself as well. So we're not asking just the envelope to do everything. We're creating these kind of spaces that work with the people that are in it. So it's got this kind of diagram that kind of explains some of the complexity. You've got some of this outside space. You then get these buffer zones where you get combined transitional type spaces between fully mechanically ventilated and naturally ventilated. So it's a kind of hybrid around the building itself, but all of which reduces the demand on the MEP equipment that's needed, reduces the demand on the energy that's needed to run the building. So these are all key metrics weaved into tower architecture, which of course is quite tricky from a natural ventilation standpoint to create these kind of innovative cooling habitats, as we say. The envelope is pretty tricky. I mean, we're now at the point where it's pretty much designed, completed. It's been through its performance mock-ups and its visual mock-ups, and it's now getting to the point of its final sort of detailing. It clearly has some challenges in terms of its geometry. We had to do an awful lot of work to understand how it's stacked, how those movements are accommodated within in the building and any one of these joints. So there's a lot in the envelope itself in terms of its performance structurally, as well as it is obviously in terms of how it works. This final project I'm just going to show you because it's a combination of some things that we've been talking about this morning and in other talks, and also it's a reflection about how perhaps we should think about our building envelopes. It's UNESCO in Paris, and if you think about the sort of stages that we look at in terms of ABCD, in terms of sustainable circularity, we're generally looking at the areas of A, which is where we're building stuff. But in this particular instinct, I'm going to focus on D, which is where we're reusing things, or things can be reused as a circular economy. So thinking about ways in which buildings can be put together such that they can be deconstructed and reconstructed and refurbished by using the same materials, not just recycling and putting it back into the mix. So this building, remarkably, I mean, it's quite an amazing opportunity to have worked on this. It was something that Jean Prouvé, a system that Jean Prouvé designed in 1969, I think, the late 60s, for UNESCO. And it's a fully detailed, you can kind of see it's very similar to a lot of his work in terms of his buildings and his furniture. It's very much about parts that came together, the sort of engineered elements of this facade. And it was with that in mind that actually, whilst it reached the end of its natural life, and it was no longer able to perform for many reasons, it was something that could actually be quite relatively easily, completely and totally refurbished, because it could all come apart. So the main problem with it was the fact that it got a timber core that had rotten. We looked at then saying, well, okay, when we take it apart to create the sort of put it back together with the majority of the structure being the structure within it being replaced, we looked at different materials. We looked at aluminium, we looked at steel, and actually decided that we would be best to rebuild it and reclad it using the majority of the heart of it in timber. So a heritage building, so it's very important, very strict rules about what can be done and what can be changed. I mean, all the glass was single glazed, so the first things we needed, higher performance insulated units with proper solar coatings, as well as being able to take everything apart and clean it and replace all those timber cores and timber structure. And this is a diagram creating these kind of mega panels of timber, veer and deals essentially, and then being able to refurbish and replace all of that glazing itself. We talk of the glass. The glass got 100% recycled, which is unusual these days in buildings, with less than 5% of our glass being recycled on buildings, which is almost criminal. So everybody's working on that pretty hard, I guess, for the future. That's important. But this was one example where we were able to take recycle it. We weren't able to reuse it, but perhaps in the future ways in which we can do that. And that resulted in some fairly significant savings in terms of the embodied carbon by taking that timber core and rather than replacing it with an aluminium stick system or something inside it, we were able to make quite significant savings and reductions in what would have otherwise been the embodied carbon cost of the refurbishment. So here's the sort of mock-up and back to its true self, and you can kind of see from what it was before being put back on the building. It's identical to what it was, and it'll last another 50 years. And I think that's, it might have been somewhat coincidental that the refurbishment of this came at this time, but I think it's a very important project for us all to be thinking about as we build facades, how the importance of this kind of demountability and replaceability and reuse becomes a part of it. And I think that the work we've been doing with Google over the last few years on developing a kit of parts, such that you can have a selection of different typologies, but within a restricted set of typologies, those typologies all being understood from the supply chain, from the opportunity to refurbish, recycle, reuse, and from that then selecting different typologies within it to create your facade design, be that whatever it is. So this kind of is somewhat theoretical, but it follows through a complete kind of process of supply chain. And if we can kind of together as an industry start to think more like this and have the data necessary on any of our particular systems we're selling or in procurement, and being able to pull those together would be I think a brighter future in how we can think about building envelopes. So that's covered transparency and lack thereof, and the challenges that our industry faces as it relates to energy and transparency. So thank you.
Thank you, James, for your cool presentation. Next, we have Sreenivas Narayanan from SideRise, who will be presenting the hot topic of managing fire risk.
Thank you. Good morning. Good morning. Good morning. Managing fire risk, after hearing to James, I think I can change the topic to mitigating or mitigation of fire risk, because he spoke about a very important topic, which is a global issue of floor-to-floor glass and external facades. I'll try to cover that, and let's see how I go, and then we'll decide whether it's managing is better or mitigating is better. One slide which I have to do, just to introduce SideRise. We are a company organization established in 1972, been in the field of fire, thermal, and acoustic insulation, and specific to facades. That's what we do. And we have had many milestones, and one of the hot topic in Australia, or especially in New South Wales, is the remediation piece of our existing buildings, where a topic of cavity barriers is coming. So we did that back in 2008. So I'm going to see how I can present this to you and see how we can introduce these into the newer buildings or refurbishments. We have various value additions that we offer, but one of the core that we as an organization say is the services that we give from the end-to-end service, it should not be charged. So we build it as a package of our products and our services, and our main proactive drive for the industry, it's to have a betterment in the industry process. Why are we here? Global codes and standards have gone towards these routes. So we know what a fire triangle is, 3 important components, what you need for fire. But the other 3 important things is when you look at a building and you write down, you have a deduction system to say that you have a fire in the building, to detect it, and tell the audience, tell the occupants to say that you need to exit the building because there is a fire. You have a suppression, which is basically to suppress the fire, but compartmentation is key because it's the one which stops the fire from spreading. So compartmentation is real key. One of the biggest challenge also in the global industry in facade is always fight for price. We have the challenges because of the products which are not here, and when they have to do value engineering or when they have to get a better system in place, it's always fight for price. Or else we have seen historical projects which have had specifications which are going down, being adopted into multiple projects, which have the specifications for the previous codes or previous standards, which has been also a challenge in the industry. So I'll just have 2 slides in relation to fundamentals. It's key. We have used lots of terminologies, but there are only 2 terminologies that we need to use. One is called as a reaction to fire, and another one is called resistance to fire. That's it. There is nothing called as fire rating. So these are the 2 main terminologies that we use in the industry as a fire engineer. Reaction to fire, basically how a product reacts, and resistance is how the system works. For example, if you have a fire-rated door, it should work for certain hours to stop fire or smoke passing through the door or the full system from where there is fire to non-exposed side or the outside. So that's the resistance property. Do we have standards in Australia? Yes, the National Building Code, the NCC also says there are 2 main standards that are widely referred. You have the 1530.1, which is basically to see what is the combustibility of the products. And you also have a resistance to fire property, which is evaluated through 1530.4. So we have standards, Australian standards, which we need to comply to, other than international standards like EN or ASTM standards. So I'll split my presentation in next 10 minutes. I'll split it 5-5. I'll go with curtain wall, which is basically our glass facades, and then move into cladding, which is our which is a hot topic of discussions. So when we say facades, curtain wall, this is where the products are, fancy. So this is where the product is based within floor slab and the external facades, or you can see another image here, which is between your floor slab and the spandrel zone. The 1530.4, which is the current route to compliance, it cannot be considered a good practice, or it cannot be viewed as a right practice, because this is how you test the product, or we test the product. But what we use in the site, or the previous image you saw, is that we are installing between a floor slab and an external facade, which is non-fire rated. So what you test in a laboratory is not what you use in the site. So it cannot be considered as a good practice. So what do we have? The main challenges, as I said, you have the 1530.4, where you install it between a non-fire rated floor slab and a non-fire rated. But in Australia, we do not have a standard to test a floor slab and a non-fire rated curtain wall. There are no standards yet, which is what we need as a development. Why do we need it? Because that is what we use inside. That is what we install. So you have a challenge of leapfrog, where a fire can break through the vision glass and come back inside, which is a serious fire. That is how it spreads. And you also have an internal spread of fire. So you can manage that or mitigate that internal spread through a 1530.4 test, but you cannot manage this because you do not have a test, we do not have a test configuration to test the product. Again, a leapfrog from James' previous presentation. This is what happens to the fire. When a fire breaks out of a window, it curves back, it comes back inside. And these are images from the test. So you can see how the fire works when it comes back. Or this is how a fire starts in a building, just an animation of series. As a fire engineer, at this point is when I expect my fire sprinklers to work. This is where I expect my fire sprinklers to start cooling down the building. If we pass over to a flashover, the glass breaks, the fire is already out. And then if we do not have a spandrel, or if we do not have that configuration to test and use that in a project, then your fire is leapfrog, because your glass is going to break and your aluminum melts at 400 degrees. So that is what you have to test and what we need to test. So in international market, we have an EN standard, which is a harmonized test standard to test the configuration of floor slab and spandrels, where you test it in a furnace, where you use a spandrel arrangement, and you use it in a closed furnace. It's the same time temperature curve. It's the same test as 1530.4 what we have, but only thing is it introduces a curtain wall, which we use on projects. Also, the test standards allows us to do cycling. We all have been speaking about testing for the future, life cycle of the buildings. So you test the product, and somebody, yesterday when I was showing this video, somebody told me it's a shake and burn. So you condition the product for an equivalent of 60 years, for example, or to seismic movements, and then test the product for fire, so which is a very important requirement which the global industry is looking at. So, as I said, we test for a configuration that we use on a project. So you have a floor slab, you have a non-fire rated curtain wall, and test that configuration by protecting the transoms and the mullions in the spandrel. Which brings back us to the previous image or the animation where, so if you have a spandrel in the building, when you have a fire and it develops, what the spandrel does, it does not allow the leapfrog effect. You do not have the fire which is going to come back, because that 900 mm of spandrel is going to protect it. Where is the 900 mm coming from? It's coming from the NCC. The NCC has clearly written that if you have a building, you should have a spandrel of minimum 900 mm. It's there in the NCC 2022. This is right picked from there. It also says, if you're having a curtain wall, and what should be the rating of the perimeter barrier and the spandrel. So you have a standard, you have a written clause within the national NCC, which is given by the Australian Building Code. But there are also exemptions within the code, which says that you don't need a spandrel if you're having if you have an automated sprinkler in your building. So it's a bit contradicting of two clauses between each other. But again, it's us who has to decide what we have to use for the future, because do we want to use a clause which is going to be challenging on what we are using in the projects, or how safe it is for the future. So again, there are various products that are available in the market. All the products are tested and applicable. Only challenge is on how you install it. That is the configuration which is different. Plus, how much human error you can eliminate for the products, for the installers in the site. Compliance is a big issue overall globally, because if we test for a product with A and B components, and if we go back to the site and change one of the components, for example, if we change the safing material to another manufacturer which is not tested, then you lose the full system performance. So it's very key that we follow what is being tested, components that are tested, and utilize it. The second bigger issue is the fire risk in high-rise facades, where we have seen so many facades fires. And one of the challenges is the cladding, on how the fire spreads. And various projects, so me coming from Dubai, based in Dubai, the New Year's Eve in Address was one of the largest fire that we ever had, and then few in Turkey and an Asian Pacific country. So how do we mitigate, how do we manage this is by the rain screen principles that we use, which are the first principles on how we design the cladding, where it is designed for circulation of air and drainage of water. So we have a large-scale system test. We have an Australian standard pathway for compliance, which is the AS5113, which is a large-scale system test. So this is the compliance pathway today. Is irrespective of the building type, you test the product as an external facade, whether you get it combustible or non-combustible. And if it comes as non-combustible, you go ahead with the project. And if it comes as combustible, then you have to go and do a large-scale system test. When we look at global global standards and codes. For example, Singapore was mentioned. In Singapore, you cannot do that. You have to do the component test and the large-scale system test. UAE, Saudi, or come to Hong Kong, for example, you need to do the large-scale system test irrespective of what the cladding type is, because that is what is going to give you documentation to say that the system is going to perform. Also, you have two types. I'll leave it. It depends on the design of the projects, whether you want it ventilated or non-ventilated. But you compartmentalize this by introducing a cavity barrier at every floor, which is like a fire break, stops the spread of fire from between the cavity. So a few tests, but again, as I said, this is a snip from the UAE Fire and Life Safety Code, where you need to do a component test and a large-scale system test, irrespective of whether it is combustible or not. You also have the approved document B, which is the guide for compliance in the UK market, where they introduce where are the locations of these cavity barriers. I've had projects where they say you can install a cavity break at every 3 floors, which is a question, because you don't know which floor to start, which floor to not start, for example. Also, this is how you mitigate. This is how a ventilated system works. It continues to perform, but when it comes in contact with fire, the intumescent in the face, intumescent is nothing but graphite, which would expand and close the void. So it restricts the passage of, it re-establishes the resistance and stops the spread of fire and smoke within the cavity. So the large-scale system test that you do, which is the AS5113, this is an image of a large-scale system test. Irrespective of the insulation which is used, the system was overall pass, and you can see the cavity barrier has expanded, and you can see how the insulation is protected below and above the cavity barrier. So it is key that you break the cavity and to protect the asset as well. Another image, we have been told that, we all think that a non-combustible material like stone would pass a large-scale system test, but this is an image to say that even introducing a large-scale test with the cavity barriers and without cavity barriers, what would be the result? 2 more slides. We have some large-scale system test data that we can share, which we are available to share. We can discuss this after the presentations. Also, third-party certifications from Warrington is becoming very popular in Australia, where they audit our materials and then certify our products. So you have a traceability of products. And also, through an inspection app, you can get what is being installed. You can get it signed off by the manufacturers to say that what has been installed is as per tested, and what is being supplied is also as per tested data. So a QR code, which is our OPD, a knowledge center, lots of information in relation to what we want to share with the audience. It's all there. So thank you very much. And if you have any questions, we are out there to give you any answers. Thank you.
Thank you, Sreenivas. Don't forget, Siderise also have a stall outside in the sponsors booth. Let's pivot a bit and have Viggo Haremst from Henning Larsen, who asked some questions about harmonizing data and design.
Thank you very much. And thank you, Zak World of Façades, for inviting me. It's fantastic to be back in Sydney and to see all of you here. I will use the next 30 minutes or so and invite you to our design studio, our global design community. I think what we are currently focusing on, how we work and what the tools we have developed and how we are working with those, and also just some examples on how that comes to life in the architecture that we design. I think we have a lot of colleagues here, or I have a lot of colleagues here, and I think the collaboration that we can do in order to kind of make this a better world is extremely important. So I will try to kind of convey this and just invite you for a bit. At Henning Larsen, we have always talked about designing for people. It seems quite obvious and a bit banal, but when you start to think about it, it's highly complex. 15 years ago, we started our sustainability department, and basically then it changed a bit and became extremely data-driven. So we started to kind of investigate, like, how can we do evidence-based design? How can we get the information needed in order to create a more sustainable footprint, and also have information to inform the design that we are doing. Recently, this kind of pivoted to a life-centric approach, because for all the reasons there, and also to kind of take a more holistic approach to the environment that we are designing for. So it didn't become easier, it became fairly much more complex, but also to some of the points that James made, there are some tools that are starting to kind of give us some data that actually then makes it a bit easier. And I think you already kind of seen this and understand this, and we've have a lot of different talks talking about it. In 2050, more than 70% of the population will live in cities, and that means that we need to make basically a new city for 1.5 million people every week. That doesn't seem super sustainable either, but of course that is pushing us and questioning what we are doing all the time. Taking Sydney, for example, that I started working heavily with in 2017, is an amazing city to be working with, first of all. I think that there is a richness in terms of how, for example, First Nation consultants, and how rich that kind of discussion of how important it is to design with country, for example, in combination with a highly sophisticated professional environment. But I think 2019, when I came, there was, of course, a lot of, in the CBD, it's highly focused on office. 2020, COVID came and everything just kind of stopped. And right now, there's a lot of questions like, is the commercial market pivoting to what end? And, for example, this project here by MVRDV in Sudias is in Europe is a residential building. So what we are looking at and what we are questioning, I don't know the answer where this is going, but I would much like to hear your view on this at some point. But this is just to kind of recognize that the market is changing rapidly. And for one thing that, and I will go through maybe 4 different points on our view on what's going on at the moment, is that this is an image from the Blue Mountains, and one question is, how can the office become better than home? Because a lot of people are not actually getting back into the office, and they discovered that there is a different way of working, and that's all good. But how do we work with that? So I think one thing to be extremely mindful of is this is not working properly, but that doesn't matter. Is to be conscious about how we future-proof business cases and how to future-proof business in basically the business case of the client. And I think, of course, that has to do with an environment that attracts new talent. It has to do with designing and to work in collaborative environments. This is an innovation hub that we've designed for MIT, full timber building. It's about finding kind of the balance between live and work closer to nature. In an environment like Sydney CBD, that can be a bit challenging. And also to be conscious about how we curate a diverse range of experiences. It's about kind of making an attractive ground plane to that curation. And what that actually, from my point of view as an architect, the kind of goal with that is to create a sense of community. And this seems perhaps a bit kind of banal in a bigger context, but is this the way that we actually can create spaces that you actually come back into the office? Is this the way that we are being more conscious about the built environment? Because there is a bigger diversity to things. I think it's also about long-term solutions. Finding ways when it becomes a focus on strong mobility strategies, because if it takes 1.5 hours to get to the office or get to where you need to be, of course there is a challenge in that. So I think what we are looking at is working really carefully to with the designs that we are doing, and I think you have a super sophisticated end of trip kind of tradition in Sydney and in Australia specifically, is to create the convenience around end-of-trip facilities, or the convenience around travel, the convenience around mobility, in terms of how that relates to, for example, a human scale environment, or what you are coming to that creates then that sense of community. What we also are working with is to understand and the integration of and the support of biodiversity. So the human scale should be enhanced by nature, and where like neighborhoods and buildings perhaps are true support to local biodiversity. And is that also then maybe to look at how can roofs be 100% accessible, or can we work with different levels within the buildings that we are doing that is creating these kind of wonderful spaces, not only for the people that are in the buildings, but also connecting biodiversity on a larger scale in the city, because you have a park here, you have a green thing here that goes up, and is it possible that these 10 buildings then are actually looking at that holistically to see how can we connect these green corridors in a city. This, and you'll find out if the sound is too loud. This is me coming to Sao Paulo in 7 years ago. So it's quite a long time ago. It was 6 in the morning, and it was raining quite a lot. And it started raining much more than I thought it was. Okay, this is enough. And you could see the eeriness of people that started to kind of run, and there was a lot of people, and there was like, okay, there's a bit of panic. I never really kind of experienced that before. This was 1 year after in Copenhagen. So this is like the first 100 years flood rain in Copenhagen that totally devastated the city of Copenhagen. And I think, of course, this has changed a lot in terms of, and this might not, actually it's not that long ago, but right now, we see it all the time, but at this point in time, it was just like, what is going on? So, of course, designing with resilience in mind is in the driver's seat. So we recognize also the value of water and how this can also be changed in terms of how will the built environment around these areas be when the water is not there? How will it be when the water actually comes? How does the building actually respond to that? And maybe more importantly, how does the public domain connect to that? So microclimate is always a starting point for us with regards to the summer, autumn, and winter time, and the different seasons, which is, of course, different from where you are. I think we look at the priority on low carbon materials, and looking at the most adequate structure and having that in mind, even though that we are architects. This is an image from the world of Volvo in Gothenburg, which started out with this kind of maybe highly important for us, but maybe kind of really kind of archiding-dong way of looking at, okay, the storytelling about this project is hyper important. This is Sweden. You can go anywhere. You can put your tent up anywhere, and so on. So it was very much to kind of see the nature of Sweden, and that became an architectural expression, and then it went from a digital craftsmanship in our studio, optimizing the structure and so on and so forth, throughout prototyping, and then basically to real craftsmanship. And this is a render from the last renders that we did, and this is a couple of months ago when the structure actually stands there. Now it's actually closed off and so on. Very large spans, very big and large span glulam columns and structure. So, of course, we're looking at a lot of different things in our studio, but I think it circles around understanding the business case, understanding how to emphasize and enable mobility to be part of how it connects to the buildings and so on, the biodiversity, how we integrate that, and how resilient can we be when we look at what the performance of the building is and what the carbon footprint is from a large perspective of different kind of parameters. So we do that with our sustainability department. This is our main office in Copenhagen, by the way. You're all welcome. We have pretty good coffee. Not as good as Sydney, of course, but please come by when you're in Copenhagen. And our approach is really data and knowledge driven before we basically do any design. And also to work with a collaborative environment. And I think that the first thing, as I mentioned before, is to look at the microclimate, to actually understand what is the comfort of things around the buildings that we're designing, which is also becoming much more sophisticated. So when we're looking at sun, wind, shadow, and so on, that is kind of compressed into a comfort diagram, which we usually put on the surface of where we are working. So we can actually monitor live where it's cold, where it's hot, where do we have shadow, where don't we have shadow, where do you have rentable spaces, where do you have openings for metro stations, whatever, which has a significant impact of how the public domain is orchestrated around enhancing the business case. So this is usually something that we use when we are discussing that with the client, because of course this is much more fun to look at, but it needs to relate to the numbers. And then when you combine that, there's a different way of how the dialogue is with our client and with all our collaborators. So we do a lot of applied research within the topologies of architecture, microclimate, facade design, shared spaces, big data, materials, and so on. And within the urban design, we also have kind of piggybacked a lot on engineering tools and kind of reconfigured them so they are much more focused in terms of what we are looking at and from our perspective. Within the studio, I'm just going to go through some of the tools, so bear with me. This is from our intranet. You don't have access to this yet, but within our organization, you can go in and you can see what are we able to actually provide you with. How long time does it take? Basically, what is the cost and so on and so forth. And it basically kind of we give you a goodie bag in terms of how can we support you from day one before you start designing to get the information that you need and the constraints regards to the environment, regards to where you are working. We've developed the food pyramid together with MIT. You all knew not the food pyramid, but the material pyramid, but you all know the food pyramid. So basically you are what you eat and you are what you build, you could say. And we use that as well in collaborating with our clients and so on to understand what materials should we use up here. Glass, unfortunately, is very high. Hay and other biomaterials are very low. So that can be a discussion with the client. Should we use this for the facade? That's not good. So we then kind of shift it, and where are we then on the scale and so on. We also use a lot of digital twin and augmented technologies in order to do that collaboration. For those of you that have a phone, you can scan this now. And it's, again, another way of, okay, so we've had a meeting, we leave you with this. This is what we've been discussing, what you now just scanned. And you can take that on with your team. You do snippets, you do comments, you send it back to us. And in a way where you have all these kind of complex challenges, we find that this is a great way to kind of continue the dialogue, also to give some privacy to the discussions that's needed in order to get the right solution. We've been trying to kind of combine technologies. This is looking at the CFD simulations, which is the simulation of wave movement together with the VR gaming industry, or the VR headset. So we develop actually this script that is measuring sound in the space. So why would you do that? You do that because we today have very large spaces. I don't know if there's sound here, then you would understand it much better. But this is our client looking into the space. What she is then doing is changing the material on the surfaces. The acoustic changes. Is this a space for a lot of different people? How do we cope with, for example, in the university world, there's a high level of suicide, loneliness, and so on? Is this space too big? So there's a lot of ways that is kind of heightening the discussion and understanding of the spaces, and especially also the materials that are used in these spaces. We developed something we call GeoPlant, and that is monitoring a lot of different, and this goes into the biophilic aspect of design and planning. We do it because we didn't understand, like working globally, how our plants and what can we use in different spaces and so on. What is the impact, and how can we kind of understand how nature is performing. So we've created this data bank, which we found out that some of our landscape architects, they do the roosters in Excel sheet, but they don't share it. So we found like 3 or 4 or 5 landscape architects that had these kind of Excel sheets, and then basically said, okay, what happens when we combine it? And I think that the biggest plant bank in the world is in Norway, and it's 2,500 species or so on. We have 5,600 plants in our data bank, out of 6 sources it was, which then gives us 62 different kind of features of how can this be worked with and so on. So we put this in this program, which is, when it's ready, it's going to be open source. I hope. It's not really ready yet. This is just showing an example. I think this is from Spain. And this, of course, could be anywhere in the world. So basically, you choose your location. And then go in and basically find out and you get some answers or some directions that would kind of enable you to understand how can landscape perform in this space. So right now we are looking at including that and making a plugin for Rhino, which is a program that we use a lot. So it actually connects to the GeoPlant system, which then enables us to then work, for example, in Australia or wherever. That gives us a first hint of what is possible here. Similarly, we have also developed something we called Urban Decarb, which is on an urban scale, defining if we can do transformation, what happens if we do X amount of % in timber, in contrast to concrete, for example, and that gives us an overview which relates to the business case of the client. How is this larger district performing if we are looking at and changing materials for the larger scales of the building, which is of course also super important to understand if it's creating the right yield and so on, and if it's not, how can we still maintain a sustainable answer. So how do we define future challenges together? So basically, I think that it's for us, it's based on dialogue and collaboration. I mean, nothing else, and which is why it seems super obvious sometimes. But of course, if we don't invite our collaborators and so on to get a better understanding, vice versa, in terms of how we work, is going to be very, very difficult. Our three different pillars that we are working within is urbanism, architecture, and landscape. And I think that is what we've kind of decided on, that going from only looking at architecture, we need to include urbanism, and we need to include landscape as well. So that was a lot of kind of engineering, a lot of numbers, a lot of tools. But within that, of course, it's the poetry of architecture, which is central to us. So the combination of the evidence-based design and that kind of sweet spot when those two things meet is what we are looking for. And what we still keep very dear, because we are talking about being having low carbon footprint, we are talking about being sustainable, and so on. And of course, this is front of mind, but we also need these spaces to be something really, really special. This is Harpa in Iceland. All the spaces in this building, which is a performance and art building, are open to the public. In their climate, it's fantastic because it becomes the new living room of Reykjavik. So we said, like, this building is about openness instead of opening hours. This is Moesgaard Museum in Denmark. For us, it's really much about creating a sense of place wherever we go. We study the culture, we study the different aspects of what we can draw in terms of creating a strong narrative around the designs that we are doing. And we are interested in creating the unexpected. So this is a museum about the starting of life, basically. So it was for us, we need to lift and basically invite people down to the earth to then kind of understand what is in there and how did everything start and so on. And of course, this big roof becomes a new destination that we didn't really kind of foresee. So when the snow comes, they go there and play, and then when they are super cold, they can go in and get a warm chocolate in the cafe in the museum. I'm really happy that James had the render from our project in Brisbane, because this was the only slide. Oh, it comes a bit later, but another project that we're working on here, just around the corner, is Cockle Bay Park, and for us, it's also this combination of the two that we've been kind of looking at is somewhat this kind of functional poetry between, for example, the facade and the surroundings. This is by the water. The facade is somewhat kind of, I get back to that, but the notion of glimmering water, it has this kind of connection to a maritime kind of environment. So what's important for us when we are designing a facade, we are relating to the area that we build in. We look at the country, culture, and local traditions and relate to these. And we develop these kind of traditions that are within kind of the facade element further and form new designs. So this is Flaibam School. It's a 300 square meter project that we've done to try to see, like, how can we make a scalable structure with an integrated panel system of compressed straw and wooden cassettes. And this system is what we are now looking at scaling up to a much larger structure. It has actually, the school has air filters of eelgrass, and the interior walls are of clay plaster to support the diffusion qualities in the building. So this has a footprint of 6 kilos of CO2 per square meter per year. So it's a small and very nice project that we are learning a lot from. So the systems that we are implying here or introducing here is something that we are now looking at. How can we scale it up? But when we are working with the facades and the buildings, this is from the facade of Nordea headquarters in Copenhagen. It's a Kastenfester system, so it's a closed cavity system. It relates to the notion of the Nordics, of the icebergs, the mountains, or the stone of the Nordics, and that is basically something that is kind of expressed in the design. So there is again this kind of search for the optimal facade system in order for, in regards to energy efficiency and performance, relating to something that has this notion of storytelling and poetry. Oh, it works. Fantastic. So this was the image that James showed before. This is Albert Street 101 in Brisbane that we are doing together with architects and Eckersley Callan and Robert Bird, among many others. And what was really important for this design was that it was like a new tower ambition where there is this pedestrianized area of Albert Street, which is one of the central streets in Brisbane. And we thought that can we kind of lift and bring that rainforest character up the tower, but at the same time being super conscious about, and I believe these are some of your diagrams, how can we get the optimal performance of the tower regards to solar radiation, and basically have the top of the tower shading as much as it can, but when it comes down and through the high-rise kind of cityscape, you don't have to shade as much, so you can be much more transparent. So depending on different kind of locations of the facade, that basically changes a bit how this facade fins are performing, how much they are kind of coming out and growing out, and when they kind of peel in, the lower you go, the more transparent you can have your building. So that kind of enabled us with this kind of conceptual idea of having this very dynamic first 8 floors that kind of invited the rainforest, which is like a special character for this part of Australia in our minds, and creating these fantastic kind of diverse terraces, and then suddenly basically peels off and breaks off as the facade actually becomes deeper and starts to shade from the sun. So it's this kind of duality combining nature and building, where you have this quite very elegant, simple silhouette of the tower from afar, standing right in the center of the CBD. And then when you come out of the new metro station on Albert Street, this is what actually welcomes you. So this really kind of diverse and dynamic lower part of the building. Another example is Canberra Theatre Centre that we've just won together with Architectus and Arab in Canberra. We were super inspired by the geology around the site, and that was for us somewhat like how we could kind of anchor the project locally, and also what is in the bedrock around and what has been there before in regards to the rivers and so on. So that became this really focus for the expression of the building, that it needed to be kind of elemental, needed to connect to those stones, it needed to be locally sourced stones that we were working with, but with buildability in mind. And when you see these kind of cracks and so on, it also became some of the motif of the facade, that these cracks is something that, of course, brings you daylight, but when the nighttime comes, it's also something that then changes and becomes something that is illuminating from inside. Those were some quick examples, and I think the last one is Cockle Bay Park, which is just around the corner from here, down in Darling Harbour. This is in 2019, and we, in the competition, there was something that was sticking out for us, which was this kind of page from the community-led process that they've had in this document, and it was that they have said, like, well, this needs to be the people's harbour. So what does that mean? For us, it meant like bringing back public life to the harbour. At that point in time, we found that this is quite a long span of a harbour. Is it possible? Is there also a lot of visitors there? There's a lot of tourists there. Can we get some authenticity back somewhat, which would also enable Sydneysiders to come and visit that part of the harbour? So bringing public life by the harbour, being conscious about these really special laneways and this special kind of small-scale interventions that is within Sydney. Sydney doesn't really have a centre, it has many different centres. So could we kind of create a piece of the city that also was really in contact with, for me, like a strong identity of Sydney is the access to nature. So really kind of create a piece of Sydney. So we really kind of endeavored on then making this human-scale podium, instead of one podium that then kind of, you have one entrance or several entrances, but there is a big wall, there would be a sense of a village 3 floors high. You can easily kind of feel that you can access it, but that connected to a tower that then connected to the city scale. On top of that, we have 6,500 square meters of park, and I think it's the largest park that is been going to be constructed in Sydney over 100 years' time. So the whole project is actually consisting of, we have a retail kind of podium, we have the lobby, which is basically the heart of the building, and then we have the commercial tower on top. And what we thought was really, really important for us was to have this open public path throughout the podium. So there was open air. You could actually enable people to cross through it without buying anything. But for us, the tower wasn't that really important. It was important to do this as a public or as a urban planning exercise, which would enable people to go from Piermont Bridge over to Druid, and from Tombalang Park over to Sussex Street over here. So there was like this cross, and right in the middle was the lobby. So it was really a duality between commercial and public drivers. How do you actually kind of get that to work? So this really became the harbour village. And here you can see how the public route actually peels off from Piermont Bridge and then cuts right through the whole podium. We have 3 circulation nodes down the harbour and 4 clusters that connects to the harbour. And in behind, you have a different setting connecting to the public path going through, and the park then on top, which is a mega land bridge arching over the Western Distributor. And creating this space to a totally new access point for the Western CBD. You have really fantastic vistas towards the water. There you have the circulation node leading up to the main park area, which is really kind of hugged by the city around. So it becomes really a fantastic pause in the city. Overlooking the harbour towards the other view. But even though that there is a large park, you also have these kind of intimate spaces with the tower just standing right in the center of this kind of lush park. Going into the lobby, we have a side core which actually enable us to have these great views to the harbour coming in from the main entrance, and to the right you have the views towards the park. So this is also where the epicenter of public and commercial drivers are meeting. So when you come into the lobby, you also see the public street down below, which is what cuts through the podium. And if you take those stairs down and go to the left, because you want some food or something, basically this is then this more kind of intimate retail street that then connects further down to going through to Tombalang Park to the south, for example. So the street in itself is a sheltered area, so of course it has a possibility to open right up to the water. If there is a prevailing wind, then you close off the facade towards the harbour, and this is much then creating this space where you could kind of refuge to and use. So when we started looking at this, and this is from the competition actually, the wind became the design driver for us. It became our friend and our enemy at the same time, because we didn't know too much about Sydney at the time, but we started to investigate what is the impact of the different prevailing wind directions when it comes to kind of breaking up the podium. And what we then kind of discovered was that the more we can mitigate the breaking up of the volume, the better, of course, it breaks off the wind. So the wind takes the fastest route, and this is the comfort mapping. Actually, not the comfort map, but this is the wind map that we used then when modeling the podium. So it was a game with finding the right proportions regards to the human scale as an inviting kind of gesture, together with the park that then would be nestled in, together with the different terraces and so on. And that together with some different facade types that was integrated into the village. So we have the guillotine facade. We have retractable fabric awnings that is also working really well with this kind of small human kind of scale. It gives this kind of richness to it. We have the header panels that is kind of supporting regards to both getting more daylight, but also kind of sheltering from the wind. Venetian blinds that are behind the guillotine facade, so they're not blaffering in the wind. And then the timber awnings that, of course, for the outside is creating good shelter from both wind and downdraft, and also with the PVs on top regards to the sun. So there's an orchestra of different facade typologies relating to climate views and operability, also to a certain extent regards to disassembly. So there's a huge kit of parts that is then kind of combining the facade altogether, giving this kind of richness of different typologies, of different usages, and so on for the project. Now the tower, we also had to design the tower, of course. And it was a really large large volume that we needed to kind of break up in 4 different clusters. And then together with kind of, getting the village going up, we also needed to kind of combine it with a cityscape in behind with Harry Seidel's building. So that's basically where it breaks up and goes up towards the sky. And the facade was basically the standard module 1500 by 3850 that we broke 4 times. So working really closely with Arab in terms of how we could kind of lean the glass so we would minimize the solar radiation, we would peel it out so it would make a shadow on the next module, and so on and so forth. It gave us this kind of rich facade that in times of a standardized facade with the same module would give us 16% less sun exposure in totality. That pattern was then kind of developed in order to kind of maintain the right views from the inside and so on, getting the right transparency, finding the right balance regards to the peak loads and so on, but maintaining this kind of richness and how it also changes during this fantastic light that Sydney has. But the glimmering of the water and the body of water in front was the main inspiration. So how this glimmering water was connected to this kind of passive strategy of the facade was really this that became the kind of functional poetry of the tower, which would also accelerate, this quite fat envelope becoming a quite slender tower in the end. I want to leave you with this, because I think we have like this collective responsibility of our different professions and to co-create and innovate and find better solutions and smarter solutions for her, basically. And I want to leave you with this global strategist that I don't know if you heard about, which is called Parag Khanna. He's a geopolitical futurist. I want you to imagine the world as a body. So this would be the skeleton. This is our transportation system. And I want you to imagine our vascular system that powers the body. So this is our oil and power lines. And I want you to imagine the nervous system, and this is our internet and communication systems in the world. And it's just to point out that we are part of one system, one world, and we need to think holistically when we design. Thank you very much.
Thanks, Viggo. So now we're going to have our first panel session. And I'd like to invite John Perry from FJC Studio, who will be moderating on Library at Liverpool Civic Centre.
I'll start talking and maybe the voice will come with me. I'm pleased to say I've got the graveyard shift today, the one that everyone wants us to get finished on time because we're keeping you from your food. I think I am on that, hopefully I am. Who's going to say I'm on? Yes? No? Yep. Good. So firstly, what I'd like to recognise the traditional owners of the land and to recognise pay my respects to the elders past, present and emerging. Today we have a slightly reduced panel. Sean unfortunately has had to fly to UK and slightly ahead of schedule. So Dan is taking over that. Dan Brandt from Built Developments. I'm also pleased to have Alex Cobbler with us from ELAB, who was the sustainability consultant with us, and Ali Khalil from Charvain, who are the current wall contractors. And hopefully up on screen behind me is Lewis Betancourt, who was actually the person that did all the work for whom I'm going to take all the credit today, as ever. So I'm going to start with asking a few questions. There's a lot of stuff in our presentation. You can see the the people that we had there. Move on to the agenda. I'm talking about this building, the library today. We are. We're going to run through those things. I'm going to start by asking Dan to tell us a little bit about how this project came into being, and what the program was and how we won how FJC won the competition.
Sure, thank you, John. So Dan Brabant from Built Development. Built have been involved in this project since 2015. There was an open market tender for the site, and Built with FJC were the winning proponents back in 2015. So two-stage project. First stage is actually due for completion at the end of October, which you can see on screen. 17,000 square metre commercial office with council chambers and childcare centre. And primarily what we're here to talk about today is the library. So you can see on your left-hand side, 2015, the market brief was essentially a mixed-use development, twin towers, and a very much, a generic response to the site. And the award-winning proposal was on the right-hand side, where the library really became the landmark building. It was drawn away from, the balance of the envelope. And next slide. So basically, the genesis of the building was a response to the Georges River and the eddy form. So the river has been, a place of gathering for people for many thousands of years out in the Liverpool area. And also the form, being the eddy form, has created this circular building with, call it FJC curved building. They love a curved building, and also the circular windows, which everyone kind of fell in love with at that point in time. So here's some shots of the public plaza. Another key element of the design was the public plaza. Another key move was really pushing the library space down into the kind of a basement level, which there's a sunken courtyard, and there are the skylights in the plaza itself. So you actually end up with this 5,000 square metre, kind of very elegant above ground, light-filled from all angles of the building.
So one of the things that I recall was the fixation with the building's appearance.
Yeah, so we were really looking for a dynamic and active facade, both inside and out. So highly transparent, not a dark building where people could, you're going to see the activation both from inside and out.
I think there was at that time, we already recognised very early on that some form of operable facade was going to be critical to this process. And we came up with lots of different ideas. Now, Alex, I'm turning to you. Everything was going well to this point, and then we came up against reality. So you might tell us a little bit about what you saw as reality.
Yeah, thanks, John. As always, it's the engineer's job to crush the dreams of any developer and architect by trying to put an overlay of reality into things. The library, we wanted to ensure that we could get that depth of daylight into the space, but we are constrained by the minimum requirements that we have for things like Green Star, Section J, immovable barriers that, for good reasons, will stand in the way of any progression. So John and the team had started to come up with these great designs that were pushing 90% glaze. We wanted, 60, 70% VLT, and we kept saying, well, no, we want to talk about 60% glazed and try to bring in the shading. So we were trying to put that layer of, this is where we think it's going to end up. And to FJC's credit, they were very passionate. They said, no, stop telling us that we can't do it. take us on the journey. Let's see what do we need to do to make it work. So our goal was to set some targets and some performance criteria that we thought they couldn't meet, and that was the journey as to where we started saying, well, okay, well, let's work towards these ridiculous performance criteria and give us the hoops to jump through, and we'll work with you to get there.
I think this was the first version of the operable blind. It's the rotary blind. And Dan, I might ask you how you reacted to this and the team.
Yeah, so, I mean, I've only been on the project 2 years, and one of the first things I saw was, what the hell is this? You know, I can imagine the first one breaking, the second one breaking, the third one breaking in a closed cavity facade, and how we're going to have this kind of forever ongoing maintenance issue. However, that being said, you know, I did recognise that it was very important to, you know, retain the activation of this facade, and I think what we'll demonstrate today is that we've gone through a very thorough journey and design testing and prototyping, etc., to still achieve the same outcome.
I wonder if this is going to work. I seem to be fated with technology. In FJC's office, whenever I walk towards the IT guy, he tells me to put my phone on the table and walk away. And miraculously, the moment I walk away, everything returns to normal, and it does. I think today is no different. I think that highlights the difference between aspirational projects and ones that actually work. Now, we were given a lot of latitude on this rotary design, and I should at this point also acknowledge we had surface design, Rob Moisey, involved heavily with this, and enabled us to go out to market and talk to and do a prototype of a rotary blind. Never been done before. We had so much fun doing this, and it was only years after the time that they actually said, actually, we knew it was never going to work, but you were so keen that we just felt we'll go along for a while and see where it takes us. And it did take us a long way, because it took us to the next point where we still wanted to achieve this clear vision zone, but we knew, and we still knew, we had to have some form of automation to control heat and to control daylight. And at this point, Lewis, I'm going to turn over to you to start to talk us through where we went.
Yeah, I think as John pointed out, we wanted to maximize the glazing and connection to the interior, and at the same time control the glare for comfort. So while meeting the Section J compliance and 6-star Green Star rating. So yeah, those were all the challenges that we had to face. And along, as you said, along the way of compliance, we scrapped a few options. One of our favorite ones, the rotary blind, and we started building up this facade that was composed mainly by 3 layers of glass, 1 circular cutout to achieve that high VLT that we were targeting, and then 2 layers of coating and 2 layers of frit, and the last, the blind that created that connection between the user and the facade, and that obviously wrapped all the envelope of our library.
So, Lewis, a quick one here. This is as it was last week, I think. Tell us more about this double glazed, triple glazed unit, because we haven't really pushed that just yet.
Yeah. So, as I said, we needed that 3rd layer of glazing in order to achieve the performance requirements, but we were determined to create a portion of that facade that had a clear view out and framed the views, and that's how we introduced that circular ring that cut out the external pane of glass. And then we carefully, I think later on the presentation, we'll explain how that glass is composed, because it has different layers, and where we put the coating and the frit was determined by the performance of the facade. And I guess if we move on to those initial, we went along the process of the execution of this process from the early concept to the delivery phase that we are now on. And we wanted to wrap the entirety of the library with this facade. And if we move on to the design intent drawings that we sent to Chavain. That was our initial. You need to go a little bit back. That's where we reviewed the VMU panels. So those early design intent drawings marked up the plan for Chavain to start working on it. So we wanted that connection with the human scale. The way we positioned the circle was in order to be able to view out if you're sitting by the facade studying or if you're standing and looking out. And then the different layers of frit framed the views out and the light that was coming into the building. And if we move on to the next slide, we can start and see how that facade reacts to the activity that happens inside as a dynamic active skin. And then that responds to the program of the facade and ties in with the furniture around it, creating this activated perimeter that overlooks what's happening outside, highly permeable. And then the validation of this system was when we first inspected the VMU in Faveri's yard. I think you can see all the happy faces there. I think we didn't really knew what we were going to be inspecting, and we were impressed with the final product. So
I'm going to break in here. I think one of the challenges was we had a very clear view of what we needed to achieve from a performance point of view, but at the beginning we actually didn't know how we were going to get it to look right. And this process of getting it to look right was where I think without Chavain's help in getting us early curved samples, and I forgot to mention, this building is curved in plan, so the units are curved in plan. Then you've got a circular hole cut out of it. So the glass itself is as messy as hell as a product. And I'm going to shoot to you, Ali. There are two components here. We had, just to put the numbers on the table, we needed a system U value of 1.64, a system U value. That's a typical centric glass U value for most people. And we also needed effectively a 0.19 solar heat gain coefficient averaged across the whole panel. So we have this building that needed those. Ali, tell us a bit about the curtain wall and your confidence, because we gave you drawings like this, which are architectural representations of an aspiration. And you came back with drawings like this, but lead us through how you felt at the time.
So the facade design here presented unique challenges, and I think it is all the parts are curved. So, and we have we have the fret, 2 frets. We have two low E coatings, 2 pieces of lamination, and a circular cutout in the external piece of the glass. I think that the design for manufacturing and assembly also, it had to be in the concern about when we were talking about the manufacturing of this panel. So this is where Boris and Shangen excelled at doing this, and they were pushing our manufacturers and suppliers to do this curved panel. So it was very challenging. And it took us 6 months to produce one panel and get the VMU done.
We might not mention that 6 months time frame to get the first piece of glass.
Yeah. That's correct. So.
The curtain wall itself, though, is part of your ongoing development of curtain wall systems themselves. And so the detail you're very familiar with, but you're expanding it to new areas.
Yeah. The first time I've seen this detail, I told myself, how we are going to achieve this. I got shocked. So
we had all these discussions with Chavain, and I have to say they're remarkably easy to work with, because we always say our first response to anything is almost always, well, I think we can do better than that. And we had a real hang-up about overflows. We don't want to see overflows in the outside of the building. And so they developed this, what I think of as the best overflow I've got. And I know I can be a bit geeky, but this is through the movement joint as well,
yes.
The parapet.
It is a dummy movement joint. Yes,
So that's the bit I didn't pick the first time. So the glass itself, there are 2 layers of frit, there are 2 layers of coatings, there are 2 laminated panels, and a single glazed panel in that lot. And the outer panel is split in 2 because we couldn't actually cut out the circle. So these are from the factory. Tell me what your glass supplier felt like at the time.
Yeah, so of course he said this is crazy, we're not going to do it. So yeah, we were so fortunate, we have good relationship with them, so we pushed them to do this innovational facade. Yeah.
Yeah. I think that's actually one of the key things that we found on this journey, was that the strength of the relationships that existed from the client through to the developer, the trust that gave us the flexibility and the opportunity to do this research, which had gone for a long period of time, right down to that long-term relationship that Charvain had with their glass supplier, that meant they were willing to trial these. Where the glass split ended up, I think, took several iterations.
Yes, that's correct. Yeah, we had to it is, yeah, iterated process. We had to make sure that the external glass is going to be structurally well, and I think that we ended up using 13.5 mil external layer or external piece of glass for the lamination. Yeah.
Yeah. This is the crux of the entire thing, so I want you to study this sketch carefully. If any of you can read it, that would be helpful, because it's my handwriting, and generally I have to go and ask someone else what I've written. But hopefully you can see that on that red dotted line, that's actually where we ended up, with a low iron glass on the outside, followed by a frit, followed by a coating, followed by argon, another layer of glass with a coating, another layer, another argon zone, and then the internal frit. So that was a diagram that we produced. I think, Alex, how did you feel about that at the time?
I guess it was the culmination of every question we've been asked. Can we achieve the performance with a frit? No. What about a coating? No. What about argon? No. What about shade? No. Well, what if we give you all of them together, and we just keep adding to and putting it all together? And we were like, what are we looking at? How do we start to put numbers and assess this? But then when we start to see the genius of it and really start to look at how it works and how the different elements speak to each other and achieve the overall holistic goals of the facade system, we realized that we could have it all.
There was a solution there somewhere. And that was the final solution. That's the coating stack there, glass 1 to 4. You can see it through there. Ali, this was all, we didn't have a coating at this point. We just had performance values. Do you recall how many bits of glass you went through, or would you prefer not to?
No, I prefer not to, yeah.
Suffice to say that we ended up with these areas, and we're trying to get both colour and performance right. And at this point, I'm going to go back to you, Lewis. Talk to us about how we came to the view that it was going to look right, because to be honest, at this point, I was starting to panic that we're going to have a performance building that didn't look great.
I think we all were panicking, and I have to say, when I approved, I think that 10th sample for the glass, I was really relieved. I think Ali was even more relieved than I was. But yeah, then we started the process of testing the frit and understanding how it works three-dimensionally, because we've got such a thick glass that the way it's perceived from the inside is determined by that thickness, and we wanted to control the views out. So depending when you are standing in the building, you get more or less views out. We had a really engaging process with Richard there on the kitchen of our studio, testing everything on a mock-up panel that we had on our terrace. There was a really dynamic process, printing some frits on like a sticker film, gluing it into the glass, and then understanding how it's seen. It was really, really fun to do. And we had only a little time. I think we developed the frit over a 4-week period. And I think the films always took like a day or two to get printed and delivered to our office. So I think we did well for the amount of time we had. And if you move to the next slide, you'll see the final prints of the frit. So as said, we've got 2 layers of frit, and they overlap so that they control the sun that enters the building. And obviously we have no frit inside that circular cutout, and the upper circle has a lower density of frit so that you can view out and see the sky, but at the same time you can control the glare that enters the building through the last component of our facade, the blind that we'll see later in the presentation.
I think there's one spin-off benefit that comes from using so much frit, and all of you who think about where the sealant goes and that it's black will realize that from the inside looking out, there's actually quite a lot of black, but fortunately with that final layer of frit, you hide all of the sealant zones and you fundamentally see the white. And that was something that we hadn't predicted or even thought about that turned out to be phenomenally powerful in terms of keeping the overall tonality of the facade. This is last week. I think everyone can see that it's been quite successful. It's a remarkably friendly on the eye space, even without the blind. And I don't think I'd be too keen on reading a book in the space, inside the zone, but fabulously so. Let's talk about the blinds. Do you want to tell us a bit about this as well, Lewis, what the thought process was and how it works for the building?
Sure. So that's like the icing to the cake. The blind is the last component that we developed, but we always knew that we wanted it to engage the user of the building with the facade. So the blind is controlled by the BMS, but out of sunstrike condition, you have actually a manual override button that allows you to move the blind up or down. It has 6 set positions. So if you're sitting by the facade and want a bit of privacy from whatever's happening on the square, on the public space next to it, you just press the button and deploy the blind down. Or if you just want to, enjoy the views out, you pull it up. And that generates, if you move to the next slide, a dynamic facade that's ever going to be changing, because some blinds are going to be going up and down because of the sunstrike, and the areas where the building is in shade, you can either pull them all the way down or up. And I think it's a really nice way of engaging people with the facade. And yeah,
I don't think we mentioned at the beginning, this was a very conventional roller blind, albeit printed. I'm still hoping, so if there's anybody out there who has a burning desire to do a rotary blind, let me know. We think we know how to do it now, thanks to a little bit of sponsorship from our key client. I think you need to give us a bit more statistics.
And I think this is,
Lewis, for you.
This is the final validation. Yeah, this is the final validation. So we finalized the whole process. We like the looks of the components, and then this all went back to Alex, right? All the final areas for him to validate that everything was working. So
I'll pass this on to you,
they modeled
Alex,
everything on CAD.
We'll pass this on to Alex to tell us about how pleased he was, because I prompted him to say that.
Curved facades are a disaster in the first place, and then we've got curves in curves for round holes and 4 or 5 different window performances in different scenarios. So we had a lot of fun, and it was over 20 iterations to get to a final position that was incredibly complex and incredibly dynamic, but we finally got a model that we could have confidence with, and we could rubber stamp the performance of the overall system against what we needed to maintain a performance that would achieve that 6-star green star and as well as the minimum code requirements there. So it was definitely an iterative journey, and it was while not the biggest model, one of the more complex and with the most moving components that we've ever done, that's for sure.
I just wanted you to see those figures. We did end up with a system value of 1.64 with that combination of triple and double glazed. I know if you look at centric glass for argon filled triple glazed, you can get 0.6, but there's a lot of perimeter zone in this, so you rapidly degrade. But it wasn't a particularly complex thermally broken curtain wall. It was very conventional. Ali?
No, it wasn't very conventional. I mean, the first time when I joined this project, I looked at the shop drawings. I told myself, this is the wrong project to start with. So I just started to look
But
at.
you did well, Ali.
Thanks, Lewis. So yeah, I just started to look at the tower typical drawings, typical curtain wall, just flat pieces, flat curtain wall, that's it. And so just to get out of the shock and getting back to the library again, starting to understand the system and how it has been designed and how to make it. So yeah, I think that it is something. At the end of it, we feel comfortable that we have designed something we are comfortable with and we are familiar with, and it's just taking us a step forward to make it. Yeah.
I think that point about a step forward is an interesting one. We in FJC spend a lot of time to innovate, but it's very easy to take one step too far. I'm not going to admit that we ever have, but it's possible that we might be considered to have. And how do you decide what is an innovation that's acceptable? It requires a fair bit of self-belief, a lot of analysis, and a huge degree of trust from the people that commission you. Turning back to you, Dan, and we're well ahead of schedule because I'm quite hungry. What do you think at the end of the day? Is this what you're expecting to get? Is it better or worse?
Look, I think definitely the initial vision for the project has been maintained. The team's put in a whole heap of hard work. You know, Liverpool City Council, to their credit, kind of also put their hand in their pocket to continue to push improving the thermal properties of the facade and the ESD credentials for the library as a standalone building. And look, I'd just like to say thank you to the project team for pushing the boundaries. It's not without people like yourselves that you achieve great projects. I know this isn't Copenhagen, 100,000 square metre building, but it's a beautiful sculptural building in the heart of Liverpool that is not only the facade. Like if we actually step inside the building and walk through the library, and at the end of this year when it opens, people are going to be wow. It's going to be one of the best in Australia in terms of a civic project and a council library in New South Wales.
Thanks, Dan. I do agree with that. One of the things that we were very keen to do and have been supported all the way through was to deliver a building that you could both look out of and look into. And as a number of people have said, there are always unexpected views. And one of the really unexpected views is when you're 2 stories underground, as it were, in that small cavity around the library, what you get to see is truly extraordinary. And the amount of light that you get down 2 stories down into the library space is also very significant.
The cladding is also challenging for the project. Yes, yeah.
The cladding?
Yes, the cladding, apart from the glass. Yes.
Okay, you're not going to mention the curved cladding as well, are you?
Yes, of course.
Okay. I was actually I'm quite prepared to throw this open to any questions from the floor today, if anyone wants to do it. We've said what we wanted to say today about the building. As Dan says, it's not a huge building, but it's an important building for Liverpool. It's an important civic building, and it's what we believe is essential. Communities should be given the best quality civic buildings. It's what makes us a society. So I'm more than happy to take any questions. But equally, very happy to head off for a bite to eat, 15 minutes ahead of schedule and almost back on schedule. If there are no questions, I'm happy to call it a day. Ahmed, are you happy with that? Okay, that's great. Well, thank you all very much.
Thank you.
Thank you, everyone.
Thanks, everyone. Everyone is hungry, I can tell. Are we having photos?
Could we please have the speakers from this session back here for a photo? You'll get mementos presented by Ross from OBEX. Okay, let's begin. Welcome back, everyone. We're here for session 3. We'll just get straight into it because we're already running a bit late. First up, we have Rafael Contreras, who has a problem about soulless foxes. Please welcome.
Hi, how are you? My name is Rafael Contreras. I'm a director and co-founder of Contreras Earl Architecture, which I'm sure maybe you haven't heard yet. We have a small company, we are based in Queensland at the moment, in the Gold Coast. And I'm going to show you what some of the projects that we are developing at the moment. But I'm going to start with something just to tell you a bit the whole story. So in this image, you can see the reality of approximately 95% of our cities in the whole planet that are being populated with these buildings that lack of architecture, let's say lack of soul, soulless buildings, just extrusions that has nothing to do with, no consideration with the environment, no consideration with the people, no consideration with the function, no consideration with anything. And it's a very big problem, and I think we as architects need to address this in different ways. I'm going to show you the way we do it. So we base the foundation of our company in two words, in evolution and nature. Evolution. Architecture has been stagnated in time during the last 100 years. So everything we see, there's very good architecture out there, but it's the same thing every year after year. I think that there is no much concern of evolving our career. There is no much concern of looking to the future. And I think we need to be aware of that. That's bringing problems to other industries. For instance, construction. We are in the era of artificial intelligence, internet, and everything is developing so fast now. And it's a bit weird and a bit, let's say, silly to build a tower of 40 stories in 3 years or more than 3 years. That's something wrong there. It's something we need to work together in order to change this. So we believe architecture needs to evolve parallel with technology in order to be able to contribute to the evolution of our cities and the evolution of our career and also other industries. And then the second word is nature, and nature is very important. We are humans, so we're animals. We come from natural environments, and we really need to integrate architecture with nature. We cannot separate both. They need to blend together. It's good, like, we have too many 90 degrees everywhere, but we need to also inject a bit of nature in our buildings, of natural shapes. I'm going to talk about maybe we cannot show all of our, the most, let's say, relevant projects I would like to show. It's not possible at the moment, but for confidentiality issues, but I'm going to show you some projects that are going to kind of linked with those two words that I've been talking about. So I'm going to start with this project. This project is in Port Douglas. It's a building that is a conservation facility for corals. Corals, as you know, are dying now. Like, they're going to go, as we speak, they're going into extinction. And I think not many people are aware of that. And it's a very big issue. And this client came to us to focus on developing a conservation facility. It was a competition. And we studied the whole brief, and apart from presenting only a conservation facility for corals, we thought it was important to also educate people and to make people aware of the importance of this problem. And we proposed a building that does much more than that. It also educates people. It also includes a research facility, and also it will be an asset for a community. Everything you see there in this building is a high-performance building. There is nothing random there, and everything has been done for a reason. It's a really amazing piece of engineering, and the sustainability that we work in this project, we work together with Arup and Werner Sobek, which is a company from Germany. we work on a holistic approach because it is not just about retrofitting the building with solar panels and batteries. It's much more than that. Sustainability is more than that. Sustainability needs to be needs to involve the place where the building is, needs to involve the economy of the place, needs to go beyond the building itself. So we work on this project with the 17 goals of the 17 development goals of the United Nations, which is a very thorough sustainability approach. And as I said, it is, I cannot go into detail now, but it's a very clever and interesting engineering approach. These are some images of a building. The building is basically, this is a weird, it's okay. So the building, as you can see, it's a circular building, has a central atrium, and from the central atrium you can basically see everything that is happening on the building. So all the coral balls are located on the lower levels, and here in this level is a level where people can come and see. This is the central atrium, the circular central atrium, and you can see everything happening on the building. And on this vault, that is the most secure part of the building, is where we have all the 800 species of corals. All of this works in a circular shape, and in the center of this, we have the research area, which is here. This is the central atrium, so you arrive to the building, you go up and arrive to the central atrium. As I said before, you can see everything is happening on the building, and on the top you have the research area is below with all the coral balls, and on the second level we have an aquarium where you can see the corals in the real environment, and on the top we have like a convention center. So this again, what you see here is a high-performance building that is inspired basically by nature. In nature, you can see that every animal or insect or anything every shape, color, size has a reason to be there because it responds to different parameters, different functions. And we're trying to mimic the same into architecture. It's not as easy as it sounds, and we cannot achieve 100% efficiency on that, but we are trying to get that as much as we can in every project we do. This project is a mixed-use project in the Gold Coast. So you can see here the Gold Coast is developed mostly on the coast. You see all the towers there, and then these buildings are on it's placed like an interface between the high-rise towers and the lower density of the city. So in this area, there's going to be it's like a small ecosystem. There's going to be a retail precinct in here, and then we have the two towers next to the retail precinct. So the first level of the towers there are 300 units. All the first levels are amenities plus retail, and as I said, connected into the center with this retail precinct, which is being built at the moment. And what we did here is we work again trying to achieve like a high-performance building. In this case, we work with the columns, and the columns just instead of being just an extrusion and a simple, conventional, traditional column, we work with the column to create, it's a high-performance column, create, first of all, an interface within the function of the lower levels, the function of the upper levels, which are the apartments, and more special, and more importantly as well, it creates a very pleasant scale while you're working next to the towers. You walk next to these towers and you don't feel that they are as high as they are. That gesture brings the size of the towers to the ground, so it feels that they are much shorter than what they are. These are some images of all the technology and how we develop this project some images of the construction of the molds for these columns. Also, it's important that all of these columns are directly related with the internal layers of the apartment, so it works perfectly with that, and also frames the balconies, and also works as a shading device for the tower. These are some images of the construction process, and these are the towers. This is only photos of stage 1, but now stage 2 is already finished. And as I was telling you, this nice, pleasant interface between the function that happens on the first level and the function of the second level. This our photo is showing that. So you create a sense of scale, and you create a special connection between the building and the people and the residents and the community as well. So it's very rewarding to see this building there and the effect that has on the city. Some images of for instance, this is one of the balconies. All of these columns are concrete, and all of these photos nicely taken by John Gollins, which I'm sure you know him. This is another project in Gold Coast as well. It's currently under construction. It's a multi-res tower. Beachfront is in Main Beach. And again, here, the project tries to connect with nature, connects with the beach as well, has these natural forms, natural shapes. In order to build this, again, we need to achieve efficiency, because every project we have, since the very beginning, since the concept design, we know how much it will cost. We present the client, since the concept, a preliminary cost of how much the project will cost, and we always work like that. We don't come with surprises at all whatsoever at the end of the design development with a number for these projects. All of this is very well controlled, and that's why we are, developers trust us. So all of this, again, technology we use to develop efficiency, similarity between the panels, otherwise could increase the cost considerably. And these are all of the detailing that we develop as well with the consultants, and some photos of some of these panels in construction. This apartment was sold out before even we had the DA in place, which was very good. You know, in Gold Coast, it's a bit crazy at the moment, a bit crazy situation, and the costs as well are huge. But also we develop, small projects, like we work mid-rise towers at the moment, high-rise, but also small projects, and we don't mind about the scale of the project, but we mind about the ambition of the project. This is a house in Palm Beach in Gold Coast as well, and the same. We are very lucky to be able to work here in this amazing environment, and trying to kind of create a connection between architecture, between the community, between the architecture, the user, the people. And at the end of the day, all of our projects are, as I said, a result of how the project responds to different parameters: structure, user, city, context. And this project is a very interesting project for us. It's basically our first commission, and small but very special. It's also located in the Gold Coast, in Mermaid Beach. The project this area is called Hedges Avenue, and between the tower and the ocean there is a park, and that park, it's a special park. There's lots of activity there, lots of people walking there, lots of people commuting, doing exercise, and we need to have something really, again, to give something to the city. So most of the towers here, or not most, but many in this city, they are very expensive towers, and they like to enclose the towers because of privacy. They want to make it not too much, let's say, integration with the rest of the city, but what we wanted to do here is completely the opposite. On one side, you can see here these sand patterns formation that we have on that area, which are beautiful, and on the other side, the materiality, which we try to use a material that could reflect, not in that way, that's like a mirror, but we wanted to reflect that dynamism of the site. And images of the design process, we start as well using all of these tools. We draw a lot, we discuss a lot about the projects, and we use technology to develop them. Similar, some tests of the materials, the reflection of the materials, and here again, how we rationalize that geometry in order to be able to be easy to build. It wasn't, so you can see, this is all some images of the construction processes. And this is an image of the interior of the project, which is we tried to create it like an eroded natural cave there. And it was made out of 300 panels. And this is also some studies that we have about the structure, how we're going to be able to build this. So again, since a very preliminary concept design, we know what we wanted to achieve here. Some images of the BIM building information modeling, because this is critical for this type of projects in order to coordinate with all the consultants. And this is a photo of the type of structure we use for this specific project. So we wanted to use, we used what is called monocoque structure, which is the same structure that cars and aircraft use in their manufacturing, which is very interesting because it uses the less resource, the less material possible to give you a very strong, but most importantly, lightweight structure. This is a photo of those panels pre-assembled in the factory in the Netherlands, because we couldn't build this in Australia. Back in 2018, there was no company that could fabricate this here, so we needed to go to Netherlands. But then, as you can imagine, when Hutchins took the job, they really hated us and wanted to kill us, and they were telling the client, guys, you're crazy. How come you're gonna do this? And the client said, no, let's try. Hutchinson's brought 3 different contractors, or 4, I don't remember exactly, and with different options, but they couldn't achieve these monolithic pieces of 9 meters length, and the complexity as well of achieving these perfectly sharp edges. The welding is very tricky for this, to achieve this. The client, so the best alternative was one alternative from one contractor, but they had too many joints, like hundreds of joints, so we couldn't achieve that. So the client said, no, we were very lucky, of course. And the client said to Hutchins, no, sorry, we want this, and it needs to be like that. And Hutchins says, yeah, we cannot do it here, so sorry. And fortunately, the client really told them, yeah, we need to do it, otherwise there's no contract. And unfortunately, we made it. Hutchinson accepted, and they engaged these guys in the Netherlands. So it was a great experience, and there was lots of tensions between them and us. But at the end, the result was great. The most rewarding thing for me is that those companies that tried to bid for this project back in 2018 and they couldn't make this, now some of them are able to fabricate this. So this is what I was talking about. We challenged the local construction industry in that sense, and they are now able to build this type of structure here. On the other side, Hutchinson's understood the power of the prefabrication. All of this was pre-assembled on site, high quality control, amazing. Therefore, they have in their schedule months to assemble those panels on the tower, and when the panels arrived, they were assembled in days. So they were amazed. And when we ended up being good friends. So now one of the projects we have under construction is because of them. they recommended us to a developer, and we're constructing one tower because of them. So it's great relationship. We really love that synergy. We learn a lot from them, and then the work that they do is great. This tower, every detail is very tidy, very well done. So yeah, as I'm telling you, what you see, the joints, you could measure them like from the top to the bottom, exactly 18 mil, is millimetrically amazing. And that's why, that's because of the high quality control you have in a factory. The interiors were done by a local company, very brave team. They never did something like this before, but they did an amazing job. It's a glass reinforced gypsum. Amazing job, and yeah, so what I was, again, trying to say here, evolution and nature, and trying to evolve our career, trying to bring hope, hope for the new generations. When a kid is looking at architecture, we need to make them excited, to make people excited and happy and motivated. That's what architecture should do. That's the power of architecture, and we are working towards that. That's the base of our company. And now I'm going to talk to you, just to finish, about the future, which is these are the air taxi drones, which you may think is crazy, but they are on its way. They are some of these companies are already getting certification in less than 2 years. They want to have been certified. And most of the helicopters operators are going to transition first into this technology. So the client came to us and asked us how we could design these terminals for air taxi drones. And then we started thinking about the same thing, how we can build this. So the clients, because in order to build this, some of the terminals are going to be retrofitted in all buildings, some of them in land as well. But whenever we need to retrofit this, I don't think this will be a good solution, right? To bring builders and try to retrofit an old building with a new concrete building on top. So that there's no way that would happen. And what we are planning to do is to use exactly the same system, the monocoque structure, in this case, aluminum. The other case was stainless steel, but this is aluminum, and that's what we're planning to do. So we're planning to create a modular system in aluminum monocoque structure, prefabricated plug-and-play components. So even the toilets or every service will be fabricated will be prefabricated, all done in the factory, and our ambition is to make these buildings self-sufficient. We don't need electricity or anything. It will be completely self-sufficient. So this is a module, the module that we work on. We are working with Arup, again in this project, with TO70 Aviation, with Skyports, and some other consultants, an amazing team. And we're planning with this module to allow these terminals to grow. In some cases, they will need to grow in an easy way. And yeah, the ones before was some iterations of how this could grow. And this is the photo of the first one that is in Melbourne, which is the aluminum monocoque structure. And everything you see here again is everything is a high-performance building that responds to the structure, to the function, to sustainability, to different parameters. So we never design a building just to try to make it nice, to look nice, and just to have that as a result. This is another project, and another similar iteration of that. But in this case, this is a small vertiport which we are developing in Sydney. We will be publishing this in maybe 3 weeks, 4 weeks. I cannot disclose where it is, but it is a small vertiport. But in this case, the aircraft can land on the roof of the project. And it is made of the same structure technology that we have done in the building in Gold Coast, which is the monocoque aluminum structure. And all of that will be prefabricated and will be brought to site and assembled in days. So just to finish, that's what I was telling. Yeah, we need to look into the future, try to evolve our careers, because it's a serious problem. We cannot continue being stagnated in time, and we need to really work to create a better human and livable places for the new generations. And yes, thank you so much for your time. And, sorry, I forgot. Not forgot, but I didn't forget. Can you put it back, please? And this is our team. So thank you to them as well. We are a small team, but very strong team at the moment. And all of these guys, yes, all of us working very hard to try to contribute to the evolution of our cities. Thank you very much.
Thank you, Rafael. As an engineer, I know architects love the word organic, so we definitely saw some organic shapes there. Okay, now let's get some insights on sustainable glass solutions with Cameron Mccleery.
Hello everyone, my name's Cameron Mccleery from AGC. I'm the marketing manager for glass products in Australia. Today I'm going to share with you the topic of sustainable glass solutions for carbon neutral buildings. But first, a brief introduction about AGC Group. AGC was founded in 1907 and our headquarters is in Tokyo, Japan. Today we have more than 55,000 employees and are located in 3 main regions around the world: Europe, Asia, Oceania and Japan. We have 4 main business groups, being chemicals including life science, electronics and displays, and ceramics, and also glass for architectural and the automotive segments. Our regional headquarters for Asia Pacific is based in Singapore, and our float plants are located in Thailand and Indonesia. We have representative offices all around Asia Pacific, including Australia, Vietnam and Taiwan. Now let's look into the glass carbon emissions impact on a building and how the world has evolved towards clean renewable energy. Firstly, to understand this better, we need to look at the World Green Building Sustainable Development Goals. By 2030, the World Green Building Committee calls for all existing buildings to reduce their energy consumption and eliminate emissions as fast as practical where applicable. Also, for new developments and major renovations, are to be built in a more highly efficient manner and to be powered by renewables, with a maximum reduction in carbon emissions. As you can see here from the infographic, we all stand to benefit from this way of thinking. Green buildings can improve our way of health and well-being, and green buildings can help our well-being, and green building designs can also spur innovation and contribute to climate-resilient infrastructure. Green buildings, importantly, also help to combat climate change through producing fewer emissions. In 2016, the Paris Agreement was introduced. The purpose of the Paris Agreement is to hold the increase in global average temperatures, as well as to strengthen the ability of countries to deal with the impacts on climate change. As you can see here, these targets are quite challenging to meet. Australia's commitment to the NDC is to reduce the greenhouse gas emissions by 43% below 2025 levels by 2030. Buildings account for 39% of total greenhouse gas emissions. 28% is contributed by operational carbon and 11% from embodied carbon. Green buildings can significantly reduce the greenhouse gas emissions simply by installing low-E glass. Energy efficient glass can play a major role in reducing energy consumption and associated greenhouse gas emissions. At AGC, we also have set our own environmental targets. By 2050, we are looking to achieve a net zero carbon goal. We aim to do this in 4 areas. Firstly, to reduce CO2 usage. Secondly, have zero wastage, whereby we're utilising all materials for production. And we're also looking at more sustainable production processes whilst conserving our natural capital. We aim to reduce the greenhouse gas emissions by 30% by 2030. And we're doing this by identifying and implementing better practices in manufacturing whilst understanding better our products, usage and applications. We are committed to reducing carbon emissions in 2 aspects. First, to reduce the environmental impact of our glass production processes that attracts embodied carbon. And secondly, to develop innovative glass product solutions, such as high-performance coated glass that increases operational carbon in green buildings. Some of our activities to date can be seen in our manufacturing plants in Indonesia and Thailand, where they've recently have done extensive upgrading of furnaces with the most advanced technology, energy-efficient technologies. And in 2008, heavy fuel oil usage was completely phased out from both of these facilities, delivering significant reductions of around 25% of greenhouse gas emissions. Other examples include we are now utilising oxygen combustion technology for our furnaces in France and Japan. And ammonia combustion technology is one of the alternative fuels now being considered, as ammonia does not produce CO2 when it's burnt, has already been used as a fertiliser, and has the same storability and transportability as propane. EPD is key to declaring embodied carbon. We have seen an increasing need for the environment and product declarations from global stakeholders and certifiers to comply to green building rating systems and their local energy codes, like Singapore's Green Mark, US LEEDs, and Australia and New Zealand's Green Star. AGC is also proactively arranging EPD certifications globally and have done so in Europe and the Middle East. And recently, as far as close as 2022, we also had our EPD certification set for Asia for our float glass and interior glass products. Now we look into advanced energy strategy solutions for facades. These are the reduction strategies for high energy consumption buildings with a goal to achieve lower energy consumption. One way this can be achieved is by using energy-saving glass to reduce the high energy consumption. Another is by using energy-generating glass to offset the energy consumption. Together, it will reduce the dependence placed upon energy grids, lowering the operational carbon being generated. Energy-saving glass with low E coatings can significantly reduce the demand for heating and cooling, thereby reducing the energy consumption and associated CO2 emissions. There is a wide range of solar control and low E coatings that all meet varying requirements and are suitable for residential, commercial, and industrial segments. AGC has world-leading coating technologies, allowing us to offer a wide range of coated glass options, such as StopRay, Synergy, and Planabuild. Our solutions include both hard and soft coating products. Each of these low-E products meets different requirements and can be used on projects all around the world. Further still, AGC still also offers on-site renewable energy generating architectural glass. To have on-site renewable energy, most of us would think of solar panels on roofs, amongst a whole host of other HVAC equipment. Building integrated photovoltaics, or BIPV, is a better solution. Solar cells are embedded in an interlayer and two pieces of glass, becoming a laminated architectural glass. BIPV is highly customizable, has a wide range of applications, and also contributes to net zero energy buildings. Not only can we utilize BIPV solutions commercially, it can be beneficial for residential housing estates. The versatility of BIPV allows it to be used in canopies over walkways, as shelter over barbecue areas, or within the dwelling itself as a skylight or on balustrades. This type of thinking goes a long way to meeting the new NCC 7-star ratings, whereby housing estates and homes are undergoing huge amounts of change. With BIPV solutions, we can reduce the need to encroach on waterways and land to make way for solar farms, substations, and transmission grids. We can do this with the introduction of on-site renewable energy that will be generated within the building itself for greater environment sustainability. BIPV also has the ability to act as an emergency power source in the event of a natural disaster. One example of this application is in our Kashima plant in Japan, which is a net zero energy building completed in 2018. For this project, 130 square metres of vision striped glass product was installed in the front of the main office. The building still maintains a transparent look whilst producing high efficient power, generating an additional 13.4 kilowatts, achieving a 114% reduction of the actual energy consumption in the building alone. Now it generates energy that goes well beyond its requirements and still maintains its aesthetic appeal and design intent. AGC SunnyWatt BIPV has a wide range of options, includes both transparent and opaque products. Each of these products can be fully customized for different specifications and requirements. Each example of this can be seen in the Hikari building in France. AGC Vision Square application was used as a double skin to cover part of the facade. It is the first positive energy building in Europe that comprises of offices, retail, and apartments. Other customized projects include Thailand using BIPV as a canopy, and a project in Belgium using Art Light Active as a light bulb design that provides power to the building. Melbourne's RMIT Design Hub and a project in Belgium have used AGC's Vision Square product harvesting solar energy. And an office building in Malaysia is using Vision Stripe for their requirements. So let us give you the peace of mind for your next project. Our team can assist you from the design stage by providing you with all the required data, including energy studies, as well as energy generation properties and glass performance, such as SHGC, U values, and other light properties for your facade calculations. So the future is in your hands. Be the driving force for the future of buildings and the environment. Getting to carbon neutral is difficult and challenging, but still possible. Everyone can be influential in helping others to achieve our net zero carbon goals. Thank you very much.
Now please welcome to the stage Rami Akkaragalla, Francesco Facchinetti, and Oliver Turner to discuss facade shading and automation systems used on the amazing One Sydney Harbour.
All right, good afternoon, guys. I'm Oliver Turner, one of the project managers at CRE. Alongside me is Rami, one of our senior engineers, and Francesco from Permasteelisa, who's one of their project managers that has been working on the One Sydney Harbour project. So today we'll be discussing the One Sydney Harbour project, specifically facade automation and shading systems. So it's quite a niche area, but something that's very important to the energy efficiency and performance of these big buildings. So a bit of an overview of the expectations that were expected for this project. So we were working in a very high-end residential space. The blind was being installed in an open cavity facade, which is the first of its kind in Australia. We had to, I guess, use a very specialised outdoor fabric that was developed with our friends from Serge Ferrari. And there was a few design considerations that had to be considered. One was quite a simple one from Renzo Piano that basically outlined that he wanted the facade to move or react with the sun and the light. So that kind of dictated how our control system was implemented for this particular building. We'll go into the stages. So this particular project involved a number of different stages, from design and project planning, and then into the integrated control system. So I'll hand over to Rami, and he'll discuss the design stages, and then we'll roll into the rest.
Thanks, Oli. So this is Rami here. So during the design stage of One Sydney Harbour, we went through with 3 design phases. So the stage 1 was we took the off-the-shelf external roller blind system and put it for the wind tunnel test. And at the first go, it failed in the wind event. So, and then we went back to the drawing board and we took the zip system and did a bit of modification and put that one for the wind tunnel test, and it did fail as well on the wind event. It could not retract due to the heavy load, heavy pressure on the inside the cavity on the fabric, so it could not retract. So that was failed again. So then we went back to the drawing board again and took the tension system, and due to the complexity of the facade and the space constraint on the facade, we did the modification and did the bespoke tension system and put it for the wind test tunnel again, and it ticked all the boxes, and we, architect and designers were pretty happy, and so that's how we got into this customized or bespoke product, and obviously a lot of components were sourced from different parts of the world, like motors from Germany, fabric from France, parts from UK, and extrusion was done locally here in Australia, and obviously we assembled at the end of the for the product was locally done in Sydney. So for the project planning, I'll hand it over to Oli again.
Thanks, Rami. So we roll into the project planning stage of this project. Now, the space that we're installing this blind was extremely confined. So we had to, I guess, tailor the particular blind to fit into that particular space a few times after the design stage had already been signed off, because, again, the space was quite confined. Again, as you can see in some of these photos, it sort of shows you where we were working and what was involved. Basically, again, all the components were custom designed for this particular project, and yeah, it was extremely tricky. I'll bring in Francesco here because there was a bit of value engineering that was done with Permasteelisa in order to, I guess, make the installation a bit smoother and quicker. So, Francesco, I'll ask you to speak of your involvement here.
Hi everyone, Francesco from Permasteelisa. Then, thanks Oliver. What happened was, just to give a big picture, we are talking about more than 15 1,000 panels for R1, R2, R3, all produced in our facility in Thailand, next to Chonburi. And at that time, COVID was a reality. Then a lot of issues with the increasing cost of logistic, material, and labor. And then we sat around the table and we thought, what can we do to mitigate this impact? And then we came up with this plan to install 30-40% of the components directly in a factory. It means that even if the cavity is 173, the space available is 150. Once you have the panels that is lying horizontally without the door, you can easily access to all the corners easily and install all the bits and pieces, pulleys and hinges. And these help us a lot and reduce also the installation time that was initially considered on site, and then it helped us in increasing efficiency.
Absolutely. There was a consideration to install the entire blind or system in Thailand, but the risk was too great with respect to the shipping. So there was a few components, as Francesco said, that were installed in Thailand, and then the rest were installed in Sydney. The good thing was that the parts that were installed in Thailand could also be, I guess, retrofitted in Sydney should there be any damage or whatnot during the travel. I guess another aspect to that was COVID and the ability to train those guys over there to be able to install these particular components. Initially, we were going to send a team over to Thailand to install, but that wasn't possible. So we had to run that training remotely. And a credit to Permasteelisa and Francesco's team that they had the skill to be able to install those components on our direction via online training. Now, if we reference, so basically the next stage was the control system, which is, I guess, where CRE can, I guess, add a lot of value. I'll bring Rami back in here to discuss the control system that was implemented for One Sydney Harbour.
Yeah. So during the design stage, we considered a lot of future proof as well. In the means the cavity was so confined and future serviceability and stuff like that. So with the control system, obviously the spec came as complete automation with a sun tracking and wind sensor included with during the pressure or the safety event blind could retract and some sort of override for the tenants. And we started with a remote control. Due to the complexity of the radio signal transmitting between the apartments, so we could not take that approach. So we had to integrate the override into the Creston home automation system. So yeah, this is one of the strong point of CRE where CRE can integrate into any sort of home automation. So, and then obviously the motors what was used was CRE digital motor communication network, so which integrates pretty well with any of the integrated systems. So that was the control side of it, and obviously we got the wind sensor up on the roof during the certain wind events. On the if tenants are not in the apartment or something, like it could still retract and be the safety to the facade. Yeah, so that was the design on the control side of it. So
yeah, and I guess the ability to be able to integrate each of those sensors back into that Creston home automation system was crucial for this project to be meeting the design intent. Now, the collaboration between, we touched on it earlier, between PISA and CRE had to be very, very, very well done in order for this to be delivered, because there's a number of different aspects or different rollout aspects that had to be considered. Now, Francesco, I'll bring you back in here with respect to the initial VMU and design.
Yep. Then we had a VMU, as we can see, then, and this was for R1. The challenge, of course, was the fact the cavity itself is really small, and then the requirement requirement was to fit a canister, a pull-lace system, and all the components there. But with a good partnership, we were able to integrate those systems for the sash and for the OCF doors then. And as we said, some of the components, the critical one, installing in Thailand really help us during the installation on site.
Yeah, absolutely, Francesco. Now, Rami, I know you were involved with that design and testing process as well with the architect and Lend-Lease, and I know there was quite a bit of back and forth to get that right.
That's right. So there were quite a few stakeholders from PISA, Permasteelisa, architect from Lend-Lease. There were quite a few, like 5 different revisions we went through with. We did the design, we did the prototype, installed it in the VMU, and then there was a few design change of the like a light gap and like the head box and the canister fitting and stuff like that. So there were quite a few intense design.
Yeah, absolutely. So then we moved back to site, and I guess again, PISA had their rollout program for their facade panels. CRE had 2 teams running. We had an electrical team roughing in the cable for the control systems, and then behind them was the blind installation team. So all three teams had to be working quite closely together in order to meet the deadlines of the builder and allowing us to be installing these products in an efficient and timely manner. Again, a couple of photos here from on-site and the cable installation, where some of the guys were installing the blinds. Kind of nice view, but yeah, quite tricky. Now, I guess just to summarise, I guess what CRE and CRE's point of difference is, comes back to the bespoke systems that we can offer our designers and architects. We specialise in shade facade engineering, and as you can see from what we've just discussed, none of this was off the shelf, so it had been designed over the course of 2, 3, 4 years with PISA, with the architects, with Lend-Lease, in order to achieve the desired result. So, yeah, like I said, we're an Australian owned and operated company, and yeah, it was a very interesting and impressive project to be a part of. So for any more information on this, come and have a chat to us. Feel free to come and have a chat to us at our stand. We also had a little bit to do with the Liverpool project that John was speaking about before, and we appreciate his enthusiasm when it comes to blinds. So like I said, thanks very much. Thanks to Francesco and Rami for taking the time, and yeah, thank you all.
They also have a booth out there for you guys to check. Now, our next stop is weatherproofing, and I hope you all love it as much as I do, even though it drives us crazy a bit. Let's hear from Nick Roach from Europe. Thank you.
Hello. I'd like to start by acknowledging the land that we meet on today is obviously the traditional land of the Gadigal people. And I'd also like to tip my hat very quickly to Mother Nature, who provides us with all of the wind and the rain that our facades have to deal with. Without Mother Nature, of course, we wouldn't be in a job. I think we've been pissing off Mother Nature a little bit over the last few years, so we need to do a little bit better at thinking about Mother Nature when we're building our buildings. So, where the tightness of the envelope, this particular presentation potentially has it has the potential to be one of the driest presentations in the session. Thank you, Dom. It started with a question for me. This was a hospital project in 2018 where the architect that we were working with said, can you provide us with a performance solution relating to FP 1.4 of NCC 2016, weatherproofing. So we hadn't done one of them before, but we said, well, you know, weather tightness, that's what we're always trying to achieve, so I think we can do that. We'll look into it. So we refreshed our detailed knowledge of the NCC, And at the time it was the 2016 extract. I'd just like to say that I'm using the term FP 1.4 in this session. Of course, that has been updated in the 2022 revision of the code to F13, yeah. But I'm going to refer to it as FP 1.4 in this report, in this session. So this code extract is from the 2016 NCC, and FP 1.4 is a pretty simple performance requirement to meet. Essentially, you don't want your building to be unhealthy or dangerous and have a loss of amenity for the occupants, and you don't want that incoming water to cause undue dampness or deterioration of the building elements. So you can achieve that with a deemed to satisfy solution or a performance solution. Using the performance solution, there's assessment methods, and then there are a number of ways to meet those assessment methods using different evidences of suitability, including potentially a test, potentially certificates from engineers or appropriately qualified persons, and other assessment methods like expert judgment. So the door is wide open. It looked fairly easy to do. We didn't really know what we were doing, and when we actually look back at our FP 1.4 report from this project, it's different to what we're producing today. Then that's when it started. So architects, PMs, owners, they all started asking, can you provide us an FP 1.4 report? How much does it cost? Is it already in your fee? It's in this other facade consultant's fee. Why isn't it in your fee? Why did we suddenly need FP 1.4 reports? Before we answer this question, we really need to delve back into a little bit of recent history in the Australian building industry. So it's a little bit uncertain when cracks started appearing in the Australian building industry, but probably in the early 2010s, maybe before that. That's when we started to see not just cracks. It's a bit of a gag there. This is an art piece. It's not a real building crack. But all sorts of defects like water leaks, minor structural defects, even thermal issues and thermal defects. Our firm certainly had our fair share of expert witness requests from lawyers. It's not the kind of work that we like to do. We'd rather have a good building in the first place. It did feel like many of the defects that we were being called on to investigate were in the lesser scrutinised areas of the industry, so the apartment parts of the industry and also some private custom houses and build to sell apartments. So it's definitely in that end of the market. While many in the industry were aware of the issues, it's really one specific type of defect that gathered the public's attention, and that was, of course, combustible cladding, which really raised the alarm. So everybody's familiar with the Lacrosse fire, which happened in Melbourne I can't believe it's actually this long ago. It's nearly 10 years ago now. It feels like only a couple of years ago. But that happened in 2014, and that sent the entire industry into a bit of a head spin. Certainly all of the fire consultants and facade consultants started to get very worried. There was also the Grenfell fire in London, which was devastating, where 72 people lost their lives. It was probably the Grenfell Tower fire that was really the incident that spurred the Australian authorities into action. But there were some other ones. The unfortunately named Torch building in Dubai that caught fire not once but twice, and Neo 200 in Melbourne. I don't think there was any loss of life from either the Lacrosse, Neo or Torch projects, but there was certainly in the Grenfell one. So this started to stir the politicians into action, and specifically politicians that were sitting on the Building Ministers Forum. So I'm not sure if everyone's fully across how it works in Australia, but we have effectively state-based legislation, and all of these relevant state ministers that are responsible for legislation relating to buildings, they get together, and they have done ever since the 1990s, which is just after the first edition of the Building Code, which was in 1988. And the purpose of this forum is to make sure that that issues that they see within their states are integrated into the building code. So it's an opportunity for input into that. After that fire, very shortly after, there was Peter Shergold and Bromlin Weir were commissioned to write the Building Confidence Report, which was completed very quickly in 2018. That report found a lot of different issues. So, and it made a series of 24 recommendations, and a lot of those recommendations were including registration of building practitioners and professional development for building surveyors, and that those professionals are more proactive and effective regulation, independent reviews, adequate documentation for performance solutions. So the performance solution that I put on the screen before, there wasn't really a method outlined in the NCC about how to do that, so there was a recommendation to do that better. And the good thing about this report is that a lot of those recommendations are slowly making their way into legislated requirements and new versions of the NCC. An example is in New South Wales, the Design and Building Practitioners Act, which I think we've got a panel on shortly. So that will be an interesting discussion. How on earth did we get here? How did our buildings become so bad? I don't think necessarily they were bad, but I think a lack of oversight let us slip into a place of lower quality. I don't think it was necessarily a single factor, but perhaps many factors that were built up over time. The rise, of course, in the miracle material, composite aluminium cladding, the go-to cheap flat cladding, which was introduced into the building industry in Australia in the 1970s. It wasn't really probably used extensively until the early 2000s. The move from municipal building certifiers to private certifiers in the early 90s, I think, had an interesting effect, because suddenly you had what was a function provided by a fully independent body now being undertaken by someone that was paid for by the developer. So there was a potential conflict of interest there. Capitalism is fantastic. It helps to drive efficiency, but some of the negative aspects of that is a decline in quality. So the demise of the clerk of works, commoditisation and the rise of design and construct. I'm not saying design and construct is a bad thing. It's an efficient mechanism to deliver buildings. And the benefits of, in fact, capitalism driving efficiency is we got cheaper buildings. It might have been that we just went too far. There is another really interesting thing which I think might have been a factor as well, and that was that up until 2005, the Australian Institute of Architects had a fee guide, and that actually helped to kind of set the standard of fees for architects. And I think ever since that time, there's been a reduction in the documentation that architects potentially once used to do. So those are some of the factors. But back to the question, why do we actually need, why did we suddenly need these reports? So that the Shergold and Weir report certainly helped to precipitate change. So the deemed to satisfy provisions of these two statements are just two of many within the report. But I think the key message here is in these two ones. The first is that the performance-based solutions weren't really being done properly, and I think they were mainly referring to fire performance solutions here, but it extends to waterproofing. And then something that I was saying before, the private building surveyor regime has led to a culture of complacency. So the other thing that was kind of happening as well is, as I said before, building defects were also on the rise. So not just the issue with combustible cladding and fire issues, which was front and centre, but the number one defect on apartment buildings, high-rise apartment buildings, is water leaks, plus mechanical plumbing issues, structural issues, like in the case of the Opal Tower. And then on top of all of this, suddenly the people who were insuring the building surveyors were taking a lot of notice and either cancelling their insurance altogether or putting enormous increases in onto their professional indemnity insurance. So I also asked my building surveyor friends, why are we suddenly getting all these requests? And they said that one particular reason was this, that in 2019, in Amendment 1, this part 4 of A2.2, talking about the performance solution, it gave you a method to do the performance solution. And so what they probably in the past didn't scrutinise heavily, now they were making sure there was a much more rigorous process so that everything was fully documented. They were asking for those performance solution reports. So 2021 was the year that brought us a blocked Suez Canal, COVID vaccinations, a new older US president, and FP 1.4 performance solution reports, infinitum. So they're here to stay. They're not going away tomorrow. The question is, though, who should do them? And if we're going to do them, do they even create more weather-tight buildings? I'm not sure. I'll touch on the first one first. Who should actually author an FP 1.4 report? I dug into the code again, and the 2016 version of the NCC says, experts. They can be with qualifications and experience, professional engineers, or appropriately qualified persons. That's quite a broad definition. And then NCC 2019 sort of moved further to define what an appropriately qualified person was. A person recognised by the appropriate authority as having qualifications and or experience in the relevant discipline in question. And appropriate authority is typically the building surveyor or building certifier charged with the statutory responsibility to determine the building compliance and issue the building permit. So pretty much anyone that the building certifier says they're happy with can write the FP 1.4 report. So who do building surveyors recognise as qualified and or experienced to write these sorts of performance solution reports? Are they professional engineers? Are they structural engineers? Or are they weatherproofing engineers? Is that a thing? Are they registered architects? It seems like a good solution. There's a registration process in place to become an architect, but do they actually want to do this, or do they have the skills? Facade consultant engineer seems like the right choice, but how do you know if they have the skills? A weather tightness consultant, that sounds good too, but I don't know where you get one of them. So the first two are recognised pathways. The second two are known within the industry, but there's no sort of recognised formal qualifications in Australia for those. So do we need formal qualifications or for building facade experts, or is it just technical architecture? I'm not sure. Seeing as you've all been sitting down for quite some time, I'm going to get you all participating now. Firstly, I'd like anyone who has authored an FP 1.4 report, don't be shy, just stand up. Come on. There's a few. Okay. Now, of all of those who are standing up, are there any architects that have, would you call yourself an architect and you've done that FP 1.4 report? No, okay, right. Oh, we've got a couple. Okay, fantastic, that's good. Okay, now, everybody who thinks that FP 1.4 reports actually create weather-tight buildings, stay standing. Well done. Okay, we've got a couple. Okay, so what are you writing them for? What's the point? So I think the answer on this, you can sit down. Thank you very much. Thank you. Do FP 1.4 reports create more weather-tight buildings? I think the answer is partly no and partly yes. I think if it's a tick-the-box exercise, it's completely pointless. It's a waste of time. I think they can actually be useful if the process is used to genuinely investigate the performance of buildings and conduct expert reviews of weatherproofing details and then incorporate those comments by the expert into the design. So I think they can be used properly, if they're done properly, to actually improve the design of a building. I think that just that review process helps. So if we have a good performance solution report confirming the design works, done by Jared, it's all good. Is our building going to be watertight? Well, maybe. Curtain wall system contractors are good, but I've tested curtain walls and seen them leak on site. So You can buy pre-tested proprietary systems. There's quite a few great ones out there. They're good, but not always necessarily tested and proven on each individual project. And then there's the question of the interface. What about the interface? So it seems to be the interface is the area of contention. I've just got this diagram up on screen here of what is a curtain wall, detail and cladding by others, and the architect's detail here, which is at 1:10 scale, and it's identified the different components, but there's no, you can't see any detail around how those systems need to junction and how they're weather tighted. So is that the cladding contractor's responsibility, or is it the curtain wall contractor's responsibility? Is it the architect's responsibility? All I seem to have learned in my career is that when it comes to the interface detail, it seems to be someone else's responsibility. So whether that's the system supplier palming it off to the facade engineer or the architect saying it's the contractor's responsibility. I am, in the old days, when it took twice as long to design a building and architects were paid fees to do so, they produced details like this, where they were fully coordinated and they grabbed that system information from the curtain wall contractor, they integrated it with the surrounding structure and took full responsibility for the details. So getting back to our problem, if we have a design which is fully documented, we've got a performance solution report, we're all coordinated, is our building now watertight? Well, again, maybe. It does depend on construction and what quality systems we've got in construction. So are there any quality plans in place for the fabrication and installation? Who is actually coordinating the trade interfaces? Does the builder have enough staff to coordinate the trade interfaces, or in the case of design and construct, do they have enough knowledge on how to do that? Is there any independent scrutiny of that construction? So imagine that we did have all of that. We have a fully documented and coordinated design. We've got our FP 1.4 report. We've got quality control systems in place for both the fabrication and the installation. And we've got brilliant independent checking and scrutiny of our construction on site. Then just maybe we might have a weather-tight building. So I think we need to go further than just realising that the FP 1.4 report is the solution to all of our problems, and we need to be advocates to the wider industry to let them know that it's great, we can do this report for you, but it's not going to do much in isolation. So if we're really serious about weather tightness, we kind of need three things. I think we need a registration framework for building envelope experts beyond building surveyor discretion. I don't know what that looks like. It might be a junction between Engineers Australia and the Institute of Architects in the States. Auckland Council has taken it into their own hands because there is no such thing as a qualified facade consultant. And so the Auckland Council has put together a producer statement author register for exterior envelopes. I don't know if it's necessarily the best system in the world, but it's better than nothing. If we're serious about weather tights, we need quality design and quality review processes. So an FP 1.4 performance solution can help if it's written properly and you actually use it to undertake that process of design. Jared, well done. There are other initiatives, though, that potentially could help. I don't know how the DLP Act and what the New South Wales government is doing at the moment might help, but I'm interested to see how that plays out. We need authorities with genuine teeth. And we also potentially need to move away from procurement that relies on D&C to solve everything at the last minute. And my third and last point, if we're serious about weather tightness, we do need systems to check construction. So again, our Kiwi friends who have had their issues with leaky buildings for many years, they're sort of 20 years ahead of us in this, and they have guidance on construction monitoring levels depending on the type of asset that it is. So certain types of assets obviously have a higher degree of quality control and site checking, but at least there's some guidance in place. And back to the very first question that I did ask, so just remember those 1, 2, 3 things. Who is actually responsible? I suppose, strictly speaking, in a design and construct procurement environment, the D&C contractor is ultimately responsible for weather tightness. Of course they are. It's not us, it's the D&C contractor. But they might assign part or all of that responsibility. But if you leave the contract to the side and you put the lawyers to the side, I think practically speaking, we're all responsible. So that's it.
Thanks, Nick. I wanted to pick up on your point about capitalism drives efficiency and plug BG&E. We also do FP 1.4 and F1 through F, whatever it is, that thing. Don't want to start a fight here, so please let's have Lette from Lysite, and he will talk to us about features and benefits of steel cladding.
Thanks, everyone. I'm going to make it really easy for you this afternoon. It's not a wordy documentation. It's pretty much a lot of movies and pictures, so this is going to be quite easy for this time of the afternoon. So a couple of little word slides to start off with. So a lot of people know Colorbond, they know BlueScope, they've probably heard of Lysite and the Fielder's range. Traditionally, the company sort of covered your roofing, walling, rainwater goods and associates. So like I said, I'm not going to spend a lot of time on sustainability. At BlueScope, we've got a strong future for steel. Yeah, so it's all about strength, it's about durability, it's about adaptability, and it's about recyclability. We've got many initiatives. These are only a part of them. So if anyone wants to see further, you can obviously go to the BlueScope websites. So here's where the easy part starts for you guys. That's a little bit of a snapshot on some of the projects that we've done. What is Azure? It's traditionally what we came in for was I've spent a lot of time in the aluminium game as well, and I've come to steel, and what we've done is we've created a panel that essentially looks like what you guys are used to in ACP and solid aluminium. So it's about creating a large format, really, really simple design, something that goes up really, really simply, something that's engineered, and something that's going to last, something that's very, very high impact. It's about design. So some of the key points here are about being at large. The one question, or the one thing that we're providing a little bit more now, backwards. The red light's not working, but can I go backwards? Sorry? Should be one above or below. No, it's going forwards. It's still going. Yeah? Back. No, you got a quick shot of the video. I just want to get back. Keep going, keep going, keep going, keep going, keep going, keep going. Okay. I was trying to use the laser pointer, but it didn't work. So manufacture, what we do is these are also produced by a robotic machine. So I don't know if anyone's come around to the stand that we've got in the corner, but one of those little panels, 40 seconds to produce on a robotic folder. They are robotic, so they don't have, I've been out the night before, I'm not in the mood for it today. Generally, I'm not saying that with every machine, but Generally, this thing, you sit there, you punch the panels in, and it just does the same panel over and over and over. So you're getting the same look all the time, you're getting the same panel, you're getting the same accuracy. The details. So here I'm not going to spend a lot, but what we've done is we've tried to design a panel that's effectively 25 mil. So it's there to design to fit into what's already there. So from a reclad point of view, or from what you're normally used to with composite panel systems, they're usually a 25 mil panel. I designed it 25 mil just to make it easier, because everyone was complaining that, especially when I've worked for architects that are in retail, every little millimetre counts. So 25 mils where we sort of sat. The machines, we can go up to 4 metres. They can be up to 1200 mil wide. Generally, most of the panels are only about 1 metre wide, okay, because BlueScope only produces a 1200 mil coil, generally, standard. So we produce the whole panel out of that coil. We did the last job where we've done a case study on this, and this was a job that we got specified, and it was with a brand new installer. And this particular installer had never done a high-end facade before. It was with a brand new builder who had never used the product before. It was with Hassel, who it was their very first time to have a go with it. And I sat there and put my hand in my face and thought, well, here we go. But the way that we've designed this, the way that we've worked through this, the amount of effort, the amount of shop drawings and things like that. So something that generally a lot of suppliers don't get into is the shop drawing. Yeah, they leave it up to the contractors. But because we fabricate them, it's something that I have to do. So it's something for me to sit there and control the process. So I'm actually there to help the installers all the way along. So we have a very, very high touch in this type of product. So I will let Hassel explain a little bit further.
As part of Brisbane's ambitious Cross-River Rail development, Queensland Rail is constructing new train stabling, a staff facilities building, and associated infrastructure in its main complex.
We were conscious that this was one of Queensland's largest infrastructure projects built in quite a while.
Leading global architectural firm Hassel Studio has played an important role in designing and shaping the functionality and aesthetics of the precinct.
We wanted the design of these buildings within the yard to complement such a city-shaping project.
Particularly the staff facilities building.
Queensland Rail had some fairly prescriptive guidelines that we needed to follow. The original prescription was for a corrugated iron profile, but we thought that something more contemporary along the lines of a flat panel would have been suitable for this area, as well as being able to maintain and clean it a lot easier. I came across the Azul product. The large format flat panels seemed to suit the requirements that we needed, as well as providing that contemporary look with the express joint and that clean flat profile, as well as a range of selected colours that we could choose from.
Manufactured from Australian-made 1.2mm colour-bond steel from BlueScope, the Azure facade panel from Lysart is light, strong and durable. Each individual Azure panel is custom manufactured to the requirements of a project, providing for an efficient construction solution as there's no need for on-site adjustments or cutting.
Given some of the sustainability benchmarks that we had to achieve, having Lysart as a local company providing support to us was great in meeting those benchmarks.
Yeah, we've had some really fabulous feedback from the QR staff now using Main Complex A, but also from some commuters. They've all said that the building looks beautiful and sleek and really contemporary. I think it's definitely the Azure cladding that has allowed us to achieve that result.
Okay, I'm hoping that a lot of people saw them, but everything that we do with these panels are a face-fixed screw. Okay, so a lot of people, when you sort of see, when we come out and we show you the panels and they're a face-fixed screw system, the screws are actually all colour-coded. So they're being a 25mm deep recess, they actually hide in the shade. So it's very, very hard, unless you're really, really close and less than 1 metre, to actually see the screws. And that's the benefit of this. This job was really, really well done. Unfortunately, it's on the QR rail site, and it's for the train drivers. And you know, this thing has movie theatres, it has quiet rooms, PC rooms, social media rooms, medical rooms, relaxation rooms. Yeah, it's all for the drivers of the trains. I think sometimes when they actually get into that building, they don't leave. But we also have done, all your traditional cladding. So this is a really, really simple system. Again, this is a cork system. It was only because we did a cork job and therefore had to replace it with a cork system. These are all dry joints, okay? So no silicon, no backing. So that already sits there and makes the panel sort of look really smooth, very, very clear and very crisp. And you don't have to worry about any wet trades. And here you can sort of see, and I'm just going to run through some pictures to give you an idea. Now, the same flashing material that you see around the doors and around the windows and around the parapet cappings are all made out of the same material, which we've designed. And this is more of the Cross River Rail. Now, everything lines up. It's a 15mm gap. It doesn't matter if you've got the foot moulds, you've got the parapet capping, you've got the side moulds. Everything lines up perfectly. Because these are pre-drilled, pre-cut, pre-done, everything. The staller only has to sit there, grab a screw gun. We pretty much do most of the work for them to sit there, get it to this point. All they have to do is unpack it and put it onto a wall. Comes, obviously all backed with a BlueScope warranty. And these are some of the panels that we've done. These are a 600mm panel. They're nearly 3,800mm long. So they're quite a large flat panel. We've had a lot of people come. We've also, through with the site, you can see with the column, we've actually cut that and it's curved exactly. So when you blow this picture up, it is exactly the way. And that was, the job was in Sydney. And we had, the designer was in a state and the factory was in a different place. And we've actually cut them around. So it's quite adaptable to sit there and fit most projects. So it's a really, really simple project. Now, something that a lot of people haven't done before is that this panel here, 1, 2, 3 pieces, 3 faces, all done in one sheet. All folded like a pizza box. And it's remarkable what we could do with a steel panel. If you sit there and maintain the radiuses, somebody can't just come through and bend some of the colour bond. It's 1.2, and then if you sit there and you bend it with really, really, really tight radiuses, you're going to crack the paint. If you're going to crack the paint, you're going to crack the coating. If you crack the coating, you're going to have corrosion. So it's all about how we bend and how we fold and how we maintain the radiuses. Ceilings. This was a job that I actually designed, and how we actually did that corner panel was that if I can actually nearly fold it on a origami, on a piece of paper, so we're making these things out of stick-it notes as to how to produce it, I can sit there and put it on a wall. So we can get right down to fine points. Again, this was a face-sealed system. So it's not to say that we're averse to face-sealed, but you don't necessarily have to do it all the time. This is where the Cross River Rail, I should have known with the sawtooth, but you can see from the tender drawings and with the design intent was always 1 metre, 1 metre, 1 metre, 1 metre. The best thing about producing a really, really economical panel system for it was that once after we got the architectural and engineering models, then we've put everything together and then we've realised that it's not quite 1 metre. They were 995, 997, 103. And so these panels were moving all between, we had 330 panels, 280 of them were unique. The robotics gets a little bit confused when you start to do that. So what you try to do is I suppose the crux of where we can be of benefit and where we can get in really, really early. So it's more like an ESI, so more like early supplier agreement, is the earlier that we can get in and help you design this, the easier and the quicker and the more economical the system becomes. We sit there and we work out everything from your design layouts, your installation layouts, your scheduling, the whole lot. And then from that point, we get it signed off and we take it straight through to fabrication. Pretty much what I just said then. And with Lysart, we can sit there, we've got your warranty support, your maintenance programs, everything needs to be clean these days. It's all part of any painted surface. Through the panel fabrication, detailing and things like that. So high quality, high accuracy, it's a strong engineered product. We've got fantastic experienced support. You get all of that, you get a happy project team. So, and I mean, every project that I've done for the last 4 or 5 years with all these things, it's all worked out really, really well. People didn't think so at the beginning. They thought it was a lot of work. So my system is a little bit more like a curtain wall. Yeah, if we spend the effort in the beginning, I can sit there and make this system a very fast, very, very quick and easy system. Thanks.
Thanks, Michael. Itay Shimony is now going to talk all about engineered stone cladding.
Use this one? Yes.
I have no idea.
All right. Good afternoon, everyone. My name is Itay Shimony, and I'm working for Costantino. Costantino today is considered as the biggest corporate in the world dealing with stone. Everything stone. Coming from natural stone, what used to be called in the past engineered stone, but it's not going to fly anymore in Australia, which moved to be mineral surfaces with lowering the amount of crystalline silica. But today we are going to talk about Decton. Decton we consider as the next generation of product. 20 years ago, we are working a lot with natural stone and different kind of stone. We had a vision, we have a dream. We wanted to find a product that will allow architects to change the skyline of cities. Product that will be durable enough on one side, but will allow a freedom of design. And then Decton came to the world. I want to start with the next video.
Behind every good architectural project, there's not only good architects, but also good clients. And I said to him, try me. So we did like really, well, not scary, but let's call it scary sketches. And they loved it. It's a bit of a miracle to do sketches to scare the client and 5 years later to be interviewed about it, and it's there and people work here. You don't need a passport to go from one discipline to the other. Still, architecture is architecture. Does it have sculpture element? Yes. I do both.
So what's Decton? We consider it as an ultra-compact stone. By using 20 different minerals that are coming to the world of clay, different silica, silica zircon, silica amorphia, and pressed together in about 25,000 tons per slab, and then going through a sinterization process, basically pressing and heating, we are creating a new product, a purely inorganic, that a new product is not the sum of its raw material. It's basically a new raw material. So again, talking about different minerals that allows us to create a product with a lot of versatility. 5 different thicknesses, can go as thin as 4 millimeter, and can go as thick as 30 millimeter. Big dimensions, from 3 meters and 50, as wide as 1.6 meters, in any color, in any possible color, any possible design. For commercial projects with enough volume, we can get any sample from the architect, from the designer, and to create Decton out of it. In many levels, after dealing with stone for so many years, we were able to create a product that takes everything that we love from stone but fix all the deficiencies. As I said, durability, non-combustible, stability of color, non-dilatation, doesn't change the size, big format, multiple thicknesses, and color and texture personalization. From the sustainable point of view, Decton is a purely carbon neutral product, certified as a cradle-to-grave product, and through the circular economy that we are working with and making sure that we are working with the product by using only recycled product mainly, using only renewable energy and recycling more than 99% of the water that we are using in the production of the product. We are creating new Decton from Decton. We are able to crush the product after the use and reuse it for other materials. When it comes to certifications, of course, everything is coming lead. The products come with a full EPD for the product, so a full environmental declaration. Coloring, I said before, any color. We had clients that wanted to be like exodite color or any Corten color, natural stone colors. We had a facade when the client wanted to book match the entire building, it was possible to do it as well. Certifications. When we are working with Decton, it's not just the product itself, we are seeing it as an holistic system. Working with our partners, we certify with the ETA for a full system of Decton as a non-combustible product on the wall. With the ability, with some specific system that I'll talk to today, to reach or to sustain wind load of up to 5 kilopascal. Systems. The beauty about the material, because on one side, we're not talking about, we're talking about stone. We're talking about a very dense material, but at the same time, man-made stone with no resin. So it allows us to integrate it over the surfaces, over the wall, with different kind of mechanical systems. And we are working together with the prescriber, with the architects, in order to define the best system that will allow, on one side, budget, but on the other side, the best mechanical use according to the environment of the project. The project that we saw before, Toha, so 2019 won as the best office building in the world. What we saw was the little brother. Now, the second one with 82 floors is under construction, and we have more than 60,000 square meters of Decton cladded, including at the highest point of about 300 meters up there in the sky, hangs panel of 3 meters by 150. One of the things that we did is that we'll be able to tailor-made the size, more than 10,000 pieces cut to size according to the specific project, and specific color degradation in order to achieve the need of the architects. So we have it in the X panel that we created specifically for this project in order to move all the mechanical system for the first 7 floors, but also in all the ledges across the entire building. It's not just flat horizontal facade. In this case, because we needed to cladded all the ledges and then to go up with the X panels, we needed to find a system that will be able to bear the wind loads that were around this building, but also to allow big size and shifting size of pieces. As I said before, we can work with different kind of materials. The beauty about the product, that it comes in different thicknesses. So we can go, in this case, as thick as 12 millimeters of the facade. There was no need to go more than 12 millimeters or to 2 cm, or as little as 4 millimeters. Thickness is usually between 8 and 12 millimeters. We can use an undercut system that doesn't penetrate the surface of the material. So from the design point of view, we are seeing only the material, but then the undercut system mechanically penetrate the material, in this case, if it's 12 millimeters, 70 millimeters to the depth of the material, and the hanger can come on top of it. So it allows you to play with the orientation of the tiles. If it doesn't need to stick with one orientation, the same facade, we can play with the orientation of the tiles, different sizes, different directions. In this case, it's the Fisher anchors, but it can be the same one, it can be the Kyle one. doesn't really matter. Both of them are tested and works perfect with the material. Or if we need, in some cases, to be even more enforced, then we can go with a grooving system. Again, because the material is man-made stone, it allows us to treat it like stone, to drill it, to groove it, to cut it, to miter it. Just to understand from the final design, so again, playing with the color, we used one tone, but then it created in one color, but then 7 different tones. But then we're able to clad both the X panels and the ledges, the entire building, and to achieve a very accurate result. One of the things that I remember the architect told us when we just approached the project, he said, in a perfect world, I wanted to leave this project just with the concrete, a bare concrete. But I know that this, what I want, and it looks beautiful today, will look very bad in a few years. Find us a product, or find us the Decton, they will look exactly like we cut the Decton with a razor-sharp knife, and we're able to give us this level of accuracy, but at the same time, the concrete look. Different project, this one is a project of the United Kingdom. Again, because it's a stone-like product, we can manipulate it. And in our factory, when we are working according to a cut-to-size manufacturing, we can also build different elements. So as I said before, because it's a stone product, we can miter it. We can create columns, we can create shapes, already pre-assemble it, and then ship it directly on site with all the mechanical fixing included, and then it's easy to just directly to install it, but to create different shapes. In this case, the project that we did here in Canberra, and also a product cladded with different coating, but then with all the need of change to combustible material, they were able to reclad it together with Decton to get the same design, but with a much more durable product. We are not bound to straight lines. We can cut to size the product however we want. If you want to integrate lighting boxes, if you want to create different shape or size of windows, whether we are using the reveal with the product itself or combining any other material. Whether we want to clad just the ledges or the balconies, whether it's underneath, on top, or the entire parapet. On the right side, you see that we can basically create also the ceilings. Freedom of design. You might like it or you might not. But here, a project in Sweden, they wanted the same look of natural stone in the 3 different buildings, but in totally different color, 3 different colors. So the base was a natural stone, a black with veins, and then I wanted the same thing in green and in red. So there are no limitations to anything to work with now. Think of a product that will never wear and tear. That everything that comes is vandalized, graffiti, or pigeon stools, smog, fog, doesn't affect the material. The materials in entire is absolutely non-porous, which basically allows it to regenerate, to clean itself just with the rain and the wind. Robust as stone, absolutely non-combustible, and you can shape it and design it to any size and to any look. Until now, we talk about ventilated facade or rain screen systems. Next level is curtain walls. We are integrating Decton as part of the curtain wall module. When there is a clear need today to decrease the amount of glass that we are using on the facade, the best solution is to integrate Decton within it. Because we are getting the product flashed together in the module, but then in any look, in any color. Think that the building basically gets the same properties as the glass, because Decton the flexural strength of the material is 67 Newton, which is the closest. Porcelain is about 20, natural stone is 10, 15, but to be as closer to glass. Another short video that I will share with you now to show a complete project from basically our factory in Spain to our partners that create the curtain walls or the modular walls in this case until the installation on the construction site. There's a little bit of the details of how we integrate Decton into the curtain wall. But let's see the video. All right, our time is very short today. We are going to redo this presentation tomorrow in our showroom in Elizabeth and Liverpool. You can come outside to our stand. We'll share with you more information about the full presentation tomorrow. But just to summarize, we are involved from day one until the last tile was installed on site through all of these services. So when you want to do something different, when you want to preserve on one side durability, but freedom of design, think Decton. Thank you.
Thank you very much. We're going to go for our last break of the day now. I just want to ask our speakers from session 3 to stay back. And I would like to call Tom Francis from OBEX that will be gifting the mementos to them for the photo. Could you guys come over here, please?
Break.
To the stage?
Welcome back, everyone. File in. Just while we're getting settled, oh, that was really loud. Someone has lost a car key. It's a car rental from Hertz. It's an Audi car. So if you've found it, can you please hand it in to someone at Zak or hand it in to us at the front, and then we can return it back to the person who has rented the car. Still a few more stragglers. I think we'll start anyway. Okay, this next session is going to be a banging session, so there's going to be a lot. Oh, come on, that was funny.
Last people.
The first of the last session is a case study on the new law building at the oldest university in Australia, Sydney University. I just want to put an aside. Sydney University, we think, is the Australian version of Hogwarts. And we love that place a lot because we love Harry Potter. Anyway, please welcome, I got some laughs here. Thank you. Yes.
Thank you.
Please welcome Alberto Sangiorgio from Mott MacDonald.
Thank you, Claire. Thank you, Natalia. I'm also a fan of Harry Potter, so I like your joke. So good afternoon. So we are towards the end of the day, so I'm really conscious that this is going to be hard for me to go after all the fantastic presentation that we've seen today, so please bear with me. But today I want to share some thoughts about the application of digital workflows to facade retrofit. So I think that to a certain extent, we all have seen the use of these digital tools being applied to new building. And, but in my opinion, there is a lack of good case studies in the industry and also in the academic literature that look at their potential impact on facade retrofit project. So with this presentation, I would like to contribute filling that gap and showing the case study of F10 for the University of Sydney. So this project saw the collaboration between a number of disciplines, including facades, digital, and sustainability. And we quite like working on this type of project because they allow us to deploy the advantage of working in a multidisciplinary team where we can leverage each other's expertise and achieve optimized design solutions. So facades, sustainability, and digital technology are included in what we call engineering sciences, and an area of practice that in Mott MacDonald includes 7 disciplines in total. And in Australia, the engineering sciences practice includes 60 members spread across 4 offices in Victoria, New South Wales, Queensland, and South Australia. And just to name a few projects where we are deploying our engineering sciences capabilities, we have the Sydney Biomedical Accelerator, which is a 450 million facility for the University of Sydney and health infrastructure. And the architect here is Denton Corker Marshall. And as shown in the picture, one of the main challenges is the design and optimization of this north-facing facade and the management of the shading and the reflectivity aspects. So this is Barangaroo CBD station, where we are working with architects and Foster and Partner to bring the station up to 100% detailed design. And the disciplines involved here are mainly facades and structural dynamics to resolve the bomber blast and vibration requirements. And this is a Victoria Cross integrated station development, where we are in partnership with Arcadis and working on both the station and the overground development. So the architects here are Bates, Smart, and Cox architects. We also like to be involved in some research and thought leadership pieces. For example, we have been the technical partner for the Green Building Council of Australia in the development of this practical guide to upfront carbon reductions with focus on structures, mechanical services, and facades. We are also supporting the University of Sydney in some publications and projects. For example, this is EcoActive, is a multidisciplinary research that spreads across the faculties of chemistry, engineering, and architecture. And the aim is to investigate the potential upscaling of nanotechnologies from other industries like computer hardware and clothing into the built environment and specifically to facades. So we are also industry advisor for University of Sydney in the research part of University of Sydney in this research grant that was awarded by the Victorian Building Authority in the development of guidelines for the observation, measurement, evaluation and rectification of damages caused by water and moisture. So the project I actually want to focus on today is not quite the typical facade scope of work that we are all familiar with, and it was developed in only 2 months. So we really use this project to stress test some of these digital tools I'm going to talk about in a second, and digital workflows. that we have developed in the last couple of years. But most of you probably know this building already, but for the one of you that you're not familiar with it, this is F10 New Law School. It is a multi-awarded building that sits in the University of Sydney campus, and its construction was completed in 2009. And one of the main features of this building is this wonderful double skin facade, which includes a set of dynamic shading system, which is rotating and made with plywood. And unfortunately, there is now a fire safety order that is pending on the building and mandate the replacement of these fins with non-combustible material. Also today, the majority of the fins, unfortunately, are not working and are locked in random positions, causing low comfort and poor working environment for the building users. And so last year, we've been appointed by the University of Sydney to address these and other maintenance items and redesign the dynamic shading as fixed elements. So despite being quite a small and, as I said, really fast project, redesigning the external shading from dynamic to static revealed to be really a complex problem with some knock-on effect on the internal comfort and mechanical services. And as a result, despite the short time, and there is quite a big team that contributed to it. So starting from the right side of the slide, there is a university infrastructure team. In the center, the Mott MacDonald team with contributions from facade structure, building services, and digital. And then on the left side of the slide, the team led by Dr. Anastasia Globa from University of Sydney, as we, in collaboration with them, we developed some virtual reality environment, but I'm going to talk about this in a second. So the vertical fins obviously constitute a really important part for the facade for two reasons. Firstly, they give the building its distinctive character and texture. And secondly, the fins act as the main shading element for the whole facade. And considering the orientation of the building with predominant east and west orientation, they work pretty hard to manage the direct solar radiation and daylight and glare. And each facade features each bay features two arrays of fins, one at the top and then a smaller one at the bottom. And each array is activated by a motor that is linked to both the building management system and to the user override switch that sits inside each office. So the vertical fins obviously constitute really, the external skin consists of external glass that is fixed to a set of cast stainless steel outrigger, which are linked to the structure behind the internal skin, and are hung from the top through a set of stainless steel hanger rods. And the fins are fixed to a set of aluminum transoms that span between outriggers. So the dynamic system allows to simultaneously rotate each array of fins from 0 to 90 degrees, and each bay can be rotated independently. So if we zoom in, we can see how in the existing design, the movement mechanism is beautifully concealed inside the aluminum extrusion. So the movement is originally created by a motor and then is transferred to an aluminum profile that runs inside the aluminum extrusion. And this aluminum profile have a number of serrated bars that are fixed to it, and then these serrated bars then transfer the movement to a cog reel that then generates the rotation of the fins. So on the left, you see a hint of what went wrong with some of these fins and why today some of them are not working anymore. So in order to address the scope of the project, we have investigated both the refurbishment of the dynamic shading, and then focused on the option that was more appropriate or made more sense for the university, which is the replacement of the shading fins with a set of fixed fins. And this revealed to be a much more complex task. So if you look at the main performance parameter of the facade, meaning daylight quantity, glare, solar radiation, and view, a dynamic shading, if working properly, can easily outperform a static one. In fact, a dynamic shading can achieve the best balance between these competing parameters, adapting to the ever-changing condition of the external environment. Vice versa, a system with fixed fins has to compromise and between these competing parameters. And for example, if we were replacing the existing fins with completely open fins, the result would have achieved optimal level of daylight, a great view, local good conditions in winter, but the user would surely suffer from overheating and glare. So overheating in summer and glare. And if we were replacing these fins with a set of completely closed fins, then the design would obtain the opposite results with office space too dark, cold, and with a scarce view or no view at all, but of course without any risk of overheating and glare. So if we put the problem in these terms, the optimization from a dynamic to static it doesn't look like a trivial problem at all. In fact, the most optimized option is not immediately evident. As we've seen in the last couple of slides, it is surely not completely open, not completely closed, so it's not on the extreme, but it is somewhere in the middle. The question is exactly where. So in order to understand exactly how the most optimized solution look like, we have tested what we call our 4-step digital workflow that employ a computational design, computational approach that was aimed at combining the benefits of what we define as a qualitative and quantitative analysis. So the first step was to understand the hierarchy of the performance requirement, meaning daylight, glare, solar radiation, and view. And this is something that usually is done by the designer. It is just a decision that the designer makes. But in this case, being this an existing building, we thought it was a good idea to seek the feedback from the building occupants. So we have created a 13-question online survey, and that was aimed at understanding the preference of the users and their level of satisfaction and comfort in the current space. And the questionnaire was sent to 100 users within the building, and we have received 40 answers, 40 people returned their answers. And a quick analysis showed how, in average, the users prioritize daylight, view, and thermal comfort over glare and privacy. So once we have established the priority between parameters, we shifted onto a quantitative approach and looked into setting up the problem in a way that was possible to resolve using computational tools. And for each parameter, we have established a set of performance indicators, and using the Rhino Grasshopper suite to calculate each one of them. So for example, in order to assess glare, the script calculates the percentage of the surface area in each room that exceeds the requirement. And a similar principle is applied to the other parameter. So for each one of them, we have established minimum baseline target for compliance according to established best practices, as well as project-specific baselines. And in agreement with the university infrastructure, in order to maintain the look of the building as close as possible to original, we have kept the dimension and the location of the fins and the shading as per the original design. And we just set the script to investigate only 2 variables, so very simple. And the first variable is the rotation of the top fin, and then the second variable is the rotation of the bottom fin, working with a 10 degrees increment, and we slightly adjusted the angle. The original was between 0 to 90, and in this case, we are working with minus 60 and plus 60. And as a result of this shadow box analysis, for each possible combination of design variables, namely alpha and beta. The script returns a set of, is an output, a set of values established for each performance parameter. And the study was done for 7 rooms that were representative of the whole facade. And instead of computing a handful of options, as usually happens with the traditional modeling tool, the use of this shoebox analysis allowed us to compute results for all possible options. And this slide, I'm just showing indicatively 4 combinations, but at the end the combinations were much more, and at the end we had 10,000 data points to analyze, which was a bit of a problem, but to facilitate the management of this data, we use our own dashboard that allows to filter the information by variables or performance outputs. And firstly, we use this to filter out all the options that were not matching the required baseline values that we have established before. And we did that for each parameter. So secondly, we then looked into the best performing option for each parameter using the hierarchy that was established by the user in the step 1. So as you can see, the dashboard allows you to compare and investigate the model in really a great detail, and where necessary, also investigate the partial values distributed across the floor plan, like in this case, or on the vertical surface. So for each reference room, we have shortlisted 5 best performing options to allow university infrastructure and their internal teams of architects to deploy different options in different adjacent bays. And this was done to recreate the original texture look of the building and maintain the integrity of the original design intent. And this is just for comparison, a snapshot from our dashboard web page taken from a much more complicated ongoing project in pre-concept stage, where we are currently working with 5 design variables and 9 parameters. And for this other project, we are currently looking to include outputs on embodied carbon and cost as well. So that would be interesting. But getting back to this project, after having shortlisted the 5 options for each reference room, we could have stopped there, but we wanted to go to add another piece to the puzzle and close the loop with the qualitative analysis with a pre-occupancy assessment. So this third step was done in a partnership with the University of Sydney, and was done testing the 5 shortlisted options with a virtual reality environment using a VR set inclusive of goggles, headphones, and a couple of handles. So the assessment was done with the purpose of engaging with a sample of users as well as with the heads of the law school, and allow them to experience firsthand the shortlisted options. So on the right, there is a video showing the capabilities and of this virtual reality environment that was developed using Unity, and that features a completely customized user interface. And so with this user interface, the user could easily change and evaluate the 5 shortlisted options that we have selected in the previous stage. But also the user can adjust the time of the day, can adjust the season, and even the condition of the sky, from sunny to cloudy to rainy, in order to explore different light conditions. So through this exercise, some of the shortlisted options were deemed inadequate from a qualitative perspective, and then were swapped in a 4th step for this digital workflow. You can hear the rain in the background. So before we look at the conclusions, on the right side there is a video that is showing one of the options that we have developed amongst many iterations to fix the fins to the existing extrusion. So this is probably not the prettiest iteration, if you ask me, but something that I like about this option is that it gives the opportunity to adjust the orientation to ease the maintenance operation and also to future-proof the design to become resilient to a change. That could be a change within the internal environment or the external condition. So in an industry where the diffusion of dynamic system will certainly increase in the future, I believe that the principle of designing resiliency and designing for failure will be the key to make sure that even in case of partial or total failure of these dynamic systems, this active system will be able to provide adequate minimum performances for the building user. And I personally look forward to a future where Façade will be active and smarter. I think that in order to avoid any issue, it would be important to have an honest discussion between clients and designers about the cost of maintenance and maintenance regime and operational budget and so forth. So yeah, sorry, I took a bit of a tangent here, but just going back to the project, the four-step digital workflow was highly appreciated by the university, as it allowed them to have a meaningful engagement with the user. And the use of VR, I think in particular, was thoroughly appreciated by not only the project management, but also by the head of the school as a way to evaluate the output of the project, and to the point where they asked us to also use it into other projects we are working on with them, like the Sydney Biomedical Accelerator that I showed you before. And regarding F10, the project is currently at the beginning of construction documentation, and we are currently exploring opportunities to reuse the plywood fins inside the campus, and possibly organize a design competition with the students of architecture to maybe, hopefully, enable some learning outcomes on a real project. So in conclusion, I must say that this project was a lot of fun, and I would like to thank everyone that was involved. And if you have any question or feedback about the project, just top of my shoulder later, and I'll be really happy to have a chat. So thank you for the attention.
Thanks, Alberto. Very insightful. Now, please welcome to the stage Nancy Wang from Changing North Glass to talk about the global trends of architecture glass.
Good afternoon. I'm very happy to be here to give a presentation about the Tianjin North Glass. So, firstly, I want to briefly introduce about the North Glass Group. North Glass was founded in 1995. So we have 4 companies which are based in Luoyang, Beijing, Shanghai, and Tianjin. But we have 2 main products. So the first product is glass tempering machine, which is used to temper or make the glass to be tempered and to be heat strengthened. So we sold like 6,000 tempering machines to all over the world, as well to Australia. And the second product is the glass procession. So I am coming from the glass procession company. So yeah, glass procession company is the Tianjin North Glass. So Tianjin North Glass is focused on the high quality, high-end glass procession, and the jumbo size glass and 3D curved glass. So I want to show some glass possibilities and some capabilities through the every project. So firstly is the jumbo size glass. So this photo shows our procession capability. So the maximum size we can produce for flat glass is 24 by 3.3 meters. For curved glass, we can produce is 18 by 3.6 meters. And for others, like IGU, lamination, and heat soak, all can be 18 by 3.6 or 24 by 3.3 meters. So maybe you are thinking that how to produce such big glass and where those big glass will be used. So next, I will show you some project reference. Okay, So this is the Guangzhou Commercial Center, which is 23 meters. And you see from the left photo that the people is standing there. So compare with the glass is very big. And the glass is 6 layers, 12 millimeter laminated glass. The right side is the glass is installed, and that is the job site photo. Yeah. So next one is the Beijing Taikang Tower. So this is the 17 meters glass, but the client applied the World Guinness record for this project because the glass weighs 51 square meters for one panel. Yeah, during that time, this is the biggest glass. They can get the World Guinness record. But after you see the Guangzhou Commercial Center, now the Guangzhou Commercial Center is the biggest glass. And okay, so I want to, for the Taikang project, I want to show one more photo. This is the ninth floor of the Taikang project. This glass is 17.5 meters, but which is a horizontal installation. So from the inside wheel, you can see that without joint, no joint, and the wheel from inside is very good. And this is in a very good location of Beijing. From this room, you can see the Tiananmen Square or the Forbidden City or many famous plans of the Beijing city. So, also for this kind of the horizontal installed glass, we can make it to be curved. So this one is 17 meters, which is flat, but to be curved, we can make it to be 8 meters by tempering or heat strengthened. And for if we do by the cold bending, we have the possibility to make it to be 15 or even more bigger, because we have a project now in China local, which is 15 meters arc length. Yeah. So the next one I want to share is the Beijing Library, so which is the world's largest structural glass project. For this project, there are 10,000 square meters flat structural glass. So for this glass, the total building is 20 meters. But during that time, we don't have the coating machine which can produce the 20 meters coating, like single alloy or double alloy coating. So the client has no choice to supply divided the glass to 2 pieces. So one piece with 15.5 meters, another one with like 5 meters. But now, at this stage, we can produce 24 meters coating. And this glass is very thick. So you can see this photo. We have 5 panels outer to be laminated and 2 panels inner. So totally 7 layers of 15 millimeter glass. And for one panel, it's like 10 tons. Okay. It's yeah, it's too heavy. It's too heavy, and yeah, 10 tons. So yeah, because we are specialized in the jumbo size glass. So we have special suckers to move to handle those glass in our factory. And for this project, sorry. So for this project, you can see that the glass with bevel edge. So after the glass build, it's like the zigzag. So the glass edge, they have like 30 cans of the bevel edge with different degree. Sorry. Okay, so let's go for the next one. Okay, so this is another project reference about the jumbo size. Yeah, so we are lucky. We are one of the supplier of the Apple, and the left side is the old Sanitun Apple store. So during that time, that is 8 meters glass. but in last year, it was rebuilt to the right one. The right one is 12 meters IGU glass. But you can see from the photo that that glass is totally a structured glass without the glass fins. So 14 years before, the left one with the glass fins. But now, many projects without the glass fins, it can save the space in the room. And also, this is another jumbo glass reference. So, yeah, we supplied the glass to the Apple Park in Cupertino. The penthouse, door glass, yeah. And during that stage, we built a big coating machine because for this glass, the size is like 16.5 meters for the roof and for the facade as well, the similar size. So we built a new coating machine for such big size glass during that time. And the very amazing is the door glass. Yeah. So one door, this is a big, very big sliding door. So one door with 10 pieces is something like 100 tons. Yeah, very heavy. Yeah. So this is 16.5 meters glass. Yeah. And all those glass for this building with coating. Okay, so we provided many jumbo size glass all over the world. Here are summarized of some projects. So next, I want to share some about the curved glass from our company. So as you know that for the curved glass, some curved glass with very big arcness, some curved glass with very small radius, but some curved glass is 3D curved. So, but we all can produce those curved glass in our factory. So we have 10 curved tempering machines for different radius and different coverages. So this is one project reference in America, which is Washington M Street. So this is a concave curved glass. So the concave means that when we do the tempering, we need to make sure that this glass with coating. So during the tempering, we need to make sure that the coating is not touch the tempering ruler. So without touch the tempering ruler to protect the coating surface. So we have our tempering machines for this special concave curved glass. Yeah, okay. So this is a mock-up for this project, for the Washington project. During that time, we make, for each project, every project, we make a mock-up in our factory. And for this project, we used the mock-up to compare with the finished glass. Every panel we need to compare with the mock-up to make sure that the color and everything is the same. So the left one is the client is doing inspection for this glass. This is a new performing arts center in Australia. So we are currently just send all the glass to here, but I think it's not opening. So you can see from this rendering that some glass are concave, some glass are convex. So they have also with coating. So, but the very special is the glass is 7.5 meters tall, and the arcness is 3.3 meters. It's totally a half circle glass, but this is a half circle glass and heat strengthened. And radius is 1 meter. So the very important for the curved glass is we need to make sure that the glass without or minimize the distortion. So otherwise, when the people see the glass, the people will feel this or feel not good. So you can see from this photo that from this reflection of the glass, the distortion is very good for this glass. Here is a video for inspecting the glass from the inside of the glass. So you can see the distortion from this video. Okay, so this project is a National Speed Skating Hall in Beijing for the Winter Olympic Game. You can see from this rendering that the outside, like many ice ribbons. So this is a design conception. So these ice ribbons are all the lighting box. Okay, this lighting box is made by the glass. This glass is 4 meters height, but the radius is 175 millimeter radius. Yeah. So the very important is this glass is a heat strengthened glass. So, but this is not the minimal radius what we can produce. So even we can produce the minimal radius to be like 150 millimeter. Yeah. So this lighting box will be made by 2 panels of half-circle glass to be the lighting box. Okay, so this project is a Huawei ride-baying project in Shanghai. In Shanghai. During the design stage, so Huawei is worried about that maybe this glass cannot be made because it's like a beam, and all the glass is 3D curved glass. So we were involved in the design stage with Huawei, and we told them, don't worry, we can make it happen. So yeah, you can see from this photo that some glass are concave, some glass are convex, but all the glass are the 3D curved glass. So for the glass of this project is in precision now. Here is another job reference in Qatar for the Lusa Tower. We produced the glass for the podium, only for the podium. The podium is 11 meters IGU glass, 2 layers outer, 2 layers inner panel. So you can see from here, the one corner, this color is like 312 millimeter rest. But for all the glass, maximum is 400 millimeter rest. So this is a finished glass. Okay, I will be quickly. Okay, so the glass like a twist. Okay, so this is the opal, which is in precision. It's a 40,000 square meters 3D curved glass, the opal. And you may ask, for such big size, how to transport? So I want to also share some information about the transportation, our experience. Here is a video. So this shows the transportation by truck because this project is located in Hong Kong. So normally for the glass, which is size is smaller than 11 meters, we can use a normal container like a 40 feet open top. But for the glass, which may be bigger than 11 meters or like 17 or or 16 meters. So we use another kind of transportation. We call it rural shipment. So you can see this is what we have done for a project in America. We have shipped such big size, 16 meters, to European and to America already, like 10 years before. Okay, so the glass will be packed by the wooden box, and then we put the glass on we call it, that is a Murphy plant. Yeah, the packed glass we put on the Murphy plant and transport to the port. Yeah, then you can see the truck will drive directly into the boat, and the glass will be fixed on the ground in the boat. So you don't need to worry about the transportation about such big size glass. Okay, so I will share some other project reference as well in Australia. This is the first one is 280 Georgia Street, which with CFA mesh is IGU glass, and the next one is 388 Georgia Street. Okay. Okay. Yeah, this is a Japan project, which is the biggest, the highest one. Okay. Okay, so lastly, I will say thank you for your attention. Yeah.
Thank you, Nancy. Can I just say it sounds like North Glass is bending over backwards to bring glass to new heights.
Just shake it and then you can announce.
Thank you.
You can read out what we are doing now, the OBEX one.
Anyway, thank you for everyone who entered the competition at OBEX's booth just outside. We're now going to draw the prize. Well, not me, but OBEX will draw the prize.
Just a rule, the person needs to be in the room, right?
Yes.
Yes, yeah, to be in the room. If it's not, sorry.
Can I do another reference? It's
Go
like
ahead.
Harry Potter's Goblet of Fire.
Where's Maxim? Okay. I'll give it to him.
No, you. He's going to give the award.
Okay.
You were
I
pick.
wasn't looking, sorry. Paul Godsen?
Godsell?
Paul-
Godsell?
Crawford, are you here, Paul?
Woo!
Woo!
Come over now.
Crawford Architects.
Come on down.
You have 5 seconds.
So what does he win?
He wins 2 tickets. Congratulations, Paul, on behalf of the OBEX team. 2 tickets are yours to an AFL match. Congratulations.
Thanks, OBEX, for this generous prize.
There are 2? Sorry. There are 2.
Oh, 2, okay.
So there are 2, right? 2 winners. Okay.
Okay, I wasn't looking.
Oh, photo. Excuse me. Sorry, Paul.
Paul, come back, please.
You got a photo. Sorry. If you can just come over here. We'll take the photo first. Up the front.
Carl? Cat card? Sorry, guys. Oh, come on.
I think we need to improve our handwriting.
Congratulations.
My boy will love that.
Just the photo, please.
The photographer is there.
Excellent. Thank you all.
Thank you.
Thank you. Now, as you can see, it's time for our last panel session. I'd like to close out the amazing day today and invite Neil Kendrick to the stage to moderate the very exciting, long-awaited panel session of DBP.
going to be very short. I know you want to get to have some drinks, but I'm going to introduce the panelists, if you'd like to all come up and join me. We've got Craig Burns, Technical Director from BVN. Pete Hartigan from Apex Façades. Mariana Yanis from Mervac. James Aspinall from Toga. And Sarah Gilder from Hassel. Yep. Excellent. Before we start, I'd like to acknowledge the traditional owners of the land that we're meeting on and pay my respects to their elders, past, present, and emerging. So today we're going to talk about the impacts, challenges, and opportunities for Class 2 buildings following the introduction of the DBP Act, much easier to say if you say Design Builders Practitioners Act, and the Residential Apartments Building Act. It's interesting because this week one of my former fire engineering friends in the UK posted on LinkedIn about the introduction of the Building Safety Acts in the UK, which, along the similar lines of these two acts, he reckons that it will be at least 5 years before anyone can have any confidence that they fully understand what the acts actually mean. And I'd say about the same for these acts as well. Beware of anyone claiming to be an expert. The nature of how the regulations came into effect means that it probably took at least a year before anybody really understood what the letter of the law meant. I luckily wasn't in Australia when they started, and I haven't. I'm just going through my first projects at the moment with it. And before you can consider yourselves competent, you need to at least learn how to apply those regulations in practice. Given most project cycles, that's at least 2 years. I would say that interpretation of how those acts are applied is probably, as we said, about 5 years before it becomes embedded in the industry. And it's not hard to believe that we probably end up with 10 years of turmoil in the industry while we work out what all the challenges and the interpretation of the practical application of those acts is. And to touch on a subject that we'll hopefully talk about later is I don't think the consultant engineers and architects who will truly understand this legislation have actually even entered university yet. And I'm not sure who's going to teach them about it. Given that, 2 years in, how are we looking, guys? I'm going to ask you first, so we can have a little bit of a heads up from each one of you. Your top 3 challenges or opportunities, and I want at least one opportunity, if you can give me one, in how you're addressing the New South Wales Acts.
Everyone seems to be looking at me.
We'll start from the furthest one away from me.
Okay.
Go, Craig.
Yeah, we've been dealing with it for a while, and I was a bit involved in it as it was turning into legislation. Like you say, there's a really important thing that this is probably 10 years worth of legislation, which was put together in 2 years. We're going to end up with, I think, better buildings because of it, but there's going to be turmoil as we go through the process of learning what it means and what its implications actually are. I think from our perspective, from an architectural perspective, in relation to facades, it's not as onerous on us as some of the other elements that it affects. But by the same time, one of our biggest challenges is to do with a level of clarity on who does what and when, who declares things, when do they get declared, and what level of responsibility do each of us have. Facades are probably the part of a building which has the most designers' hands on it. So you'll have an architect doing something, then an architect in conjunction with one of the millions of facade engineers in the room, the consultants. Then it'll go to a contractor will have their engineers, they'll have the people doing the shop drawings and things, all of whom are designers of this stuff. So that makes it slightly difficult in terms of how the Act recognises that inherent marriage of different designers. It's not typically designed to do that. So that's an interesting one, particularly because, and the DBPA isn't new as far as this is concerned. These are things that we've dealt with in projects a lot in terms of whose scope goes where, who's doing what, who's signing things off, who's doing the F3P1 reports now, all that kind of stuff. So those things just get amplified under the DBPA. I'd say the other challenge, time. Time's an important one from our perspective, because the checking and review processes that we go through for things associated with the DBPA are more onerous than normal. The key thing about it isn't just requiring that your design is compliant, it's requiring that it's fully coordinated and fully integrated with everyone else's designs that might have an effect on it. In order to sign something saying, yes, it is, and I can put my hand in my heart, that one, saying yes, it is, you have to check a lot of stuff. You have to check more than we normally would, and you have to know that you've got all of the other consultants' information up front. It's all there. They've seen ours, we've seen theirs. That takes time. And the iterations that it goes through is something which we're learning the hard way at the moment, how to make sure that that stuff all gets done. And there's a level of pressure that obviously that comes on, and the fact that that takes time during a process. It also takes resources, because the people checking this aren't the people we would normally have checking it at project architect level. This is, technical director level, principal level who are checking things. So that adds to the costs involved in it. So one of the things that we'll get to, I think, in 10 years or 5 years, I think it's 5 years, but that we'll get to a situation where everybody understands really what the scope implications are, who's providing what the fee uplifts might be involved in that, and everything kind of settles down. But at the moment, that's still all being negotiated. It's a case-by-case basis. You're trying to make those things happen.
Any opportunity?
Opportunity. Listen, the opportunity one, I think, is actually fairly easy. I think the entire Act in itself is a fabulous opportunity, and that I'm an architect. My mission statement is to improve the experience of everybody who comes into contact with the building I'm involved in designing. That's a pretty easy mission statement to be able to put forward. That's what we do for a living. The Act is trying to make buildings better for people to use, to live in, to work in, to play in, all that kind of stuff. And we can't disagree with that. There's nothing in that we would say is a bad thing. That's a good thing. We're going to get better buildings out of it. The opportunity there is that people will be more confident in what they're building and what they're buying, that it reflects well on everybody sitting here and the different things that we all do. That makes the industry better. That makes our professions better. So I think there's a huge opportunity there if we can just get through the muddle at the beginning. So I think that's probably my opportunity. It's the one big opportunity.
Excellent. Pete, your top three to kick us off.
I might start with a few positives and then one challenge.
That's good.
So I think we're close to the end of 4 projects. So one with Mariana, one with James, well, in fact, 2 with Toga, and then 1 with Lend-Lease. So yeah, 2 years in. So I suppose the first positive, by your introduction, Neil, in 3 years' time, I'm going to know what I'm doing. So I think that's quite positive. Be a first.
How many years has it taken so far, Pete?
35 so far. So in 40 years, I'll know what I'm doing. No, but seriously, I think one of the big opportunities, if you're going to sign a declaration, you obviously need to be confident that that design works. I think one of the traps for facade consultants doing performance-based design is you draw a concept, but you don't necessarily get the experience of designing it and signing it off. So you don't necessarily take the design all the way through to its conclusion. And so there's a gap in your knowledge, because you only learn properly by doing. And so I see one of the opportunities is simply to have that experience and to learn from it and to become a better designer. Because certainly in my practice, you learn what you learn at a job, you apply it on the next one. And so, if you only ever take the design to a certain point because you're doing performance-based designs, you never really become a fantastic designer. I suppose building on top of that is the fact that I would say a lot of residential systems, so think brick veneer, think a lot of cladding systems with sarking, perhaps even some standard sliding doors, they're originally designed and conceived for low-rise buildings. And what we see is they're being applied now on 10, 15, maybe even 20-story buildings, where the wind load is, and the exposure to rain is much higher. So there's a further learning opportunity, which was to be able to extend the application of these systems and to really kind of dig into that. And just to draw on the projects I've mentioned with James and Mariana, all those projects had brick veneer with sarking in them, and we did a big piece of work which was actually shared across the projects, where we looked into the application of that on sort of 15 stories. And one of the big concerns, I'm not getting into detail, but I think I found it interesting. One of the big concerns is the brick ties tear the sarking as it flaps backwards and forwards over 50 years. And there was no data on it. The sarking suppliers did not have the kind of observed what happens over the life of a building. So we did a research piece around that and figured out, yes, there is a problem and what to do about it. So I think there's a great learning there. So there's 2 opportunities, or 3 actually. I think one challenge, I think, which Nick kind of really nicely teed up in his discussion about who's responsible, is the fact that now most of waterproofing, according to this act, the sign-off is being done by engineers. And traditionally that would have been a senior system designer working within a subcontractor, and they usually wouldn't have been an engineer. They'd have started a draftsman, worked their way up, and after a number of years they've had sufficient experience. Now that's been shifted. I think there's actually quite a few issues associated with that in terms of the skills that Nick talked about, and I think also what happens if you make a mistake. A subcontractor would get paid quite a lot of money to design and build, and within that they would have a margin for going to fix the odd mistake. Consultants don't have that facility. They've got a PI insurance policy. So I think the Act has shifted the responsibility for waterproofing, and I don't necessarily think it's been worked through and that risk apportioned in a way that is kind of consummate with, I could go on here and I would probably stop that. So we'll come back to that.
Well, obviously, Mariana, one of your opportunities has been working with Pete on the projects, but if you can give us the other 3, or maybe it wasn't an opportunity.
Yeah. Challenge? So I guess for me, when the Act came in play, we were about to start basement structure, so we didn't have 5 years or 1 year. We had a couple of months to understand what it meant, and everyone was very nervous, trying to kind of understand what it was and what it meant for them, and how to manage risk. So we had some designers trying to design out the potential of poor workmanship, for example. We had certifiers trying to police the Act or interpret it when it wasn't really for them to do. That's for the design and builder practitioners' obligations. We had the builders with the typical, we've been doing this way for 30 years. So it was very difficult, but I think we all had to come together to the table and find a way forward. And I think that was one of the better opportunities that we found, that collaboration piece that helped the process a lot.
Yeah, that's good. Yeah. James, same again. Obviously, you've had the opportunity of working with Pete as well, so that's your opportunity out the window.
So I'm from Togo. Togo's a private property developer. Probably most in the room don't know Togo, probably haven't heard of Togo, but we've been doing Class 2 buildings for 60 years now. So I'm working on Surrey Hills Village with Pete. Surrey Hills Village, in its former life, was affectionately known as Murder Mall, if any of you have heard of Murder Mall, but we're turning it into a true mixed-use development, so it'll be a hotel, residential, commercial and retail. And of course, with the DBP Act and the scope amongst that, all of the different uses come into that, not just residential, which has been a serious challenge for us, definitely. And I think, Nick, also to your last slide, about giving authority more teeth and D&C subcontractors and the ability they've had over the last 10 years to probably reduce the quality somewhat. I think the DBP Act and the RAB Act are there to address those concerns, and I actually think they're actually doing a pretty good job. I mean, one of the opportunities with the Act is certainly that the quality of facades is improving, undoubtedly. And I think how we're seeing that play out is that the expert consultants, probably most of you in the room, to be honest, are having more influence over the design. And unlike a D&C subby, are not incentivised to reduce the quality or reduce the cost. Because of course, when a subby is going for a project, when they're coming to us in a tender, they're looking for value engineering options to win the job. But once a consultant's on board, a consultant is actually there, you know, largely a part of their business, protecting their PI and actually trying to bolster the design and strengthen the design. So I think it's that balance of power, or the incentive structure that we're seeing change as part of the DBP Act, which is the biggest opportunity, and the challenge that I think you've all sort of touched on there is trying to get the delineation of responsibility right between the facade engineer, the architect, the structural engineer, the subcontractor. You know, this is a brand new process, and Pete, we spent during COVID hours on the phone trying to work out who's doing what, and it was pretty much near on impossible. I think after all those conversations, we still didn't get there, but we're working through it. But that's definitely one of the challenges that we're seeing as well.
Yeah. And Sarah, you obviously got a big development going on at the moment.
Yeah, I'd reiterate Craig's architectural perspective. Definitely have challenge coordinating and understanding our scope of works between the consultants. In terms of the client, the challenge will be to deliver in our time constraints and the program that we have ahead. Yeah. And opportunity, again, as an architect and as a person who sees it as an important thing to deliver sustainable, innovative and livable housing that's affordable at the end of the day, for the long run.
Fair enough, excellent. Sticking with that, what opportunities to deliver better building facades for Class 2 buildings do you think have become apparent since the Acts have come into force, maybe?
Yeah, so we're at Hassel, we're working on the Harbourside project, which is the project that we're working through at the moment. And so I think the major opportunity and something that's been very progressive and productive for that project has been the opportunity to tie the design to construction where we are now, moving into the construction phase. For the last few months, we've been working, initiated by Mirvac, with an early works contractor for the facade. And the process has been really productive, working with Pete. We're navigating the multiple inputs of architecture, facade engineering and the contractor, but it has been a really productive process. They're very professional and really engaged in the design, and I would like to really encourage and hope that that's a really considered avenue for more projects under this Act, because it's really a great opportunity to work closer with how the building will be built at the end of the day, in many regards. So,
yeah. If I can build into that, I think collaboration, it's been enhanced with the Act. So the mix is there, all the diverging factors are there, profit, cost, buildability, design, aesthetics, and robust engineering. And the new thing to the mix now is the Act. And I see it as a platform for collaboration, to turn those challenges into opportunities with early subcontractor input, everyone coming together to the table, workshopping a detail early enough to make sure that it's practical or resolving the unpracticalities of that detail. Prototyping as well, we've also found it's very good to bring everyone there and look at it, make sure they're comfortable with the end result from all diverging factors. So I do think there's an opportunity for, knowledge sharing or know-how sharing, as Pete said, between designers and builders.
I think that one of the challenges with that is actually trying to bring the subcontractor's voice in, because as the subcontractor has been pushed, not necessarily to construct only contracts, but certainly the influence of the design has pushed consultants. That's definitely one voice that is starting to leave the room in that early phase of design development. And I know, Pete, you mentioned it before, but innovation, how do we now drive in the facade game innovation over the next 10 years? We're certainly bolstering quality at the moment, and we're certainly giving the design responsibility to the people who are the most educated and arguably the most experienced. But I think innovation is probably one of the challenges moving forward, particularly with cost.
Yeah, I think that, there's kind of a couple of interesting points I'd like to build on. So that one there, to the point about consultants protecting their PI, there is a thing there, because we don't have the financial resources to send a team of people down to fix a couple of leaks that were, whether they're workmanship or design, So there is a risk that we become overly conservative. I think there's prudent design that is not overly reliant on workmanship. So we're not just trusting that everything will be done perfectly. I think that's prudent. But there is a risk around over-conservatism, and that, building on the points from Simon and Jeff this morning about embodied carbon, if you get too conservative, you're putting more material in there, up goes the cost, up goes the embodied carbon, and that's not what we want. And your point around the subbies, they have traditionally been the driver of, let's say, cost and buildability-focused innovation, and we don't want to lose that, because, we'll end up going backwards. I think building on one of Mariana's points, class 2 buildings, there's obviously a lot more trades at a point. And if you think about a balcony, you've got a membrane, you've got concrete tolerances, you've often got an opaque wall, you've got glazing types. So there's 5 different trades at least, internal finish, 6 trades, they're meeting at a point. And often all those
How many hours do we spend in front of a prototype?
And often those parties, some of those parties might be in the room when you're kind of setting out the parameter or drawing the detail, whatever it is, but they're definitely not all there.
No.
And so that, I see one of the roles of the facade consultant is to sort of be the integrator between those trades and deal with tolerances. And Nick's point, effectively Nick's point around interfaces. I think there's a really important role there.
It's all about the interfaces, always has been. And Pete, do you want to talk a bit about things that this act has sort of helped in improving the way you do things in the...
So tricky question. Improvements suggested we're not doing things very well. I'd like to reframe.
That was the aim of the act, was to improve our building facades.
So I'm going to say change.
Constant improvement.
Constantly improving. So one of the things that the ways we
perhaps
operate, one of the things that we used to do that we're a bit more nervous around doing is it's about giving partial advice. So we want to know, what's the compliance pathway here. I think that's important for everyone. It's essentially one of your earlier points there. In terms of, when we do a design, we're obviously doing a lot more work now. We're drawing to sign off. We have to understand all the nasty little 3D junctions. And we always tried to do that before, we just didn't have the fee to do it. So I think, we're doing a lot more drawing work, we're understanding and documenting a lot of those interfaces. So I think that's I see the positive change. We do now often have this separation between design and installation. So in the old D&C model, that all lived with the subby. And so a facade designer could design in a way knowing how it would be installed and knowing the level of competence or preferences or whatever that their installation teams would do. We don't as a consultant, we don't have that. So again, this point about sensible sort of, let's say, prudent design that's not overly reliant on workmanship. So I think those are, and definitely more site inspections. You know, I'm a big fan, and if you spot a mistake while it's being built, you can fix it and avoid a mistake forever. I'm not a believer in, there's a kind of school of thought that says if you don't go to site, you don't attract site liability. I don't buy into that. But I certainly wouldn't like to see that extrapolated to the point of engineer signs off the construction, which is a change I've heard is coming. I don't think that's the right direction.
It's surely going to be the B of the DBP Act.
Yes, I personally don't think that's the right direction. I think there needs to be an onus on the builder to build the design, and the responsibility should stay there. So I think those are some changes.
For the developer, to build on that maybe, and this focus on interface and junctions, it used to be the fact that there was probably little attention paid to it. You know, the architect would provide the concept, and then it gets handed quite quickly over to the subcontractor cohort, who are then all trying to figure out how all these different parts go together. Whereas now, we get Apex coming along and actually thinking about these junctions. In the past, pretty similar to your graphic, Nick, you just get all of these different subbies pointing at each other. You know, it's not the window guy's fault, it's not the brickie, it's not the petition guy, it's, you know, who knows who it is. For the developer, now we can look to Pete, who's had a site inspection, and you know, we can.
I'm not allowed to do that anymore.
Just one person.
Yeah, we can point to Pete. I mean, no, but I think the point I'm making is that at least there's some serious educated thought early on in the phase with the architect, and so if there's some concessions that need to be made as part of the design process with the architects, they can be made early on, and an alternate solution can be brought about that's actually still delivering a really quality product, aesthetically, quality build, all of those things. So it's that part of it's a great result.
Actually, one thing I haven't properly thought about is, I mean, the fact that we do a lot of work with Mirvac and Toga and Lend-Lease, they're all integrated developer, design manager, builders. So all these upfront discussions around, I don't know, what sort of concrete tolerance, I mean, to pick on a trivial but actually repeating and really important factor, you know, how do we want to build it? These are such fundamentals. And usually what we find is there's quite a lot of pressure to do the regulated design by CC, which actually comes very early in the piece. So the ability to manage some of that by tapping into the in-house buildability expertise, I think, is I'm finding it really beneficial.
Yeah, well, the integrated developer builder model, it's pretty, when there's an issue, both end up paying for it. So it's not like at a point in time there's no builder and the developer's working with the consultants and all the risk is getting pushed down the line. I think with the integrated model, the risk is there no matter what. And so there's probably possibly more prudent decisions made in that forum. But it's interesting to see how standalone builders are managing this process as well. Yeah. There's a lot of risk on them.
Yeah, I think one of the interesting, sorry, Marianne.
No, I was going to say, we have Mirvac, we have all three, so developer, builder, and design capabilities in-house. So this forward thinking, it's pretty much every day. And even with the Act, we found an enhanced process or how to improve it, but there's a lot that we kind of feel was already there.
I think one of the things that strikes us is that part of the intention of the Act was almost to try and squash D&C as a process for doing buildings. That they kind of seen that as being the prime cause of the kind of defects that they were seeing. Whether you buy into that or not is neither here nor there. But it's kind of saying what we really want is the designers design it, the builders build it, and it happens as a linear thing. Originally, you weren't supposed to be able to stage development when the Act was actually envisaged, and they took that away at the last minute, allowed staging to still occur, which is not necessarily an issue much for facades, but that's a huge issue that we're dealing with across multiple projects, is how you do stage CCs and stage declarations for things. It's really, really messy. But it's as if, in a way, we all know that facades have always been something which are designed in conjunction with a contractor. You can't do it without, I can't design a facade. As Pete's saying, the opportunities that he gets
in
to
3 years,
design a facade, they're rare as well. It takes all the people in that chain to be able to do it, and I think that's part of where the issue is coming from in terms of lack of clarity or understanding amongst all of us about how you actually go about doing that, is that the Act was never really envisaged to recognise the fact that that's what happens, that you can't not D and C a facade, So I think in a way it's probably been left to us. Actually, it's the people in this room actually who put your heads together and figure out how we make this work.
Yeah.
What's the best way that actually we can make it work for all of the players involved? And I suspect that if we as a group could come up with that as a solution that we all agreed on, then the building commission would be very happy. And that's always a good thing, as we all know.
I think that the timing of the CC I found is really problematic. So we're being usually asked to provide a reg design at CC, and that often happens before the subbie's involved, or maybe the subbie's only been involved for a month. So a lot of the decisions that need to be made around how you're going to install it, what's your preferred set of materials and what have you, and the cost innovation that they bring, it's not on the table. And so there's an inefficiency in trying to rush something and then redesigning it when the subbies are involved, and that's certainly happened to, I'd say not massively, but to some extent on the projects we worked on. And I think teasing that out is going to streamline things a lot.
We've had discussions around. Sorry, John. No, I agree.
One of the biggest dangers of this act is actually almost obliging you to make a false declaration. Unless that changes, this will go nowhere.
Yeah, I mean, and we've found ourselves being, and actually Mariana was fantastic on Channel 9 in helping us navigate that situation. So we're finding a lot of pressure from the certifiers to say, right, you need to do it, because, and I'm not sure why, to be honest, it's my ignorance perhaps. I don't know, Mariana, maybe you can educate. Sorry, I'm not meaning to hot potato you here, but I don't understand where that pressure comes from. It's my ignorance.
Yeah, look, it's I think it all started with we need all designs, everything together before CC. I think that's not practical. So what we did was we tried and be strategic about it. We wouldn't force anyone to do a fake declaration. We will force people to, because the deliverables for regulated design are not the same as the deliverables for a CC. All they need to see is that the CC documents, there is a CC document, be an architectural drawing or an elevation or a section, so it's declared. So probably you'll end up with, I don't know, like Pete was saying, 50 details, 60 details, and at CC you have 10. But provided those 10 are well thought and are considered and are coordinated, that, in my view, meets the requirements. There's going to be more drawings, there's going to be more development, there's going to be shop drawings that will potentially change things slightly, but none of those really affect the original resolution or the original strategy that was put in place. So, in my view, in that particular project, and I don't know if it's a good example, because as I said, we only had 2 months pretty much to figure it out, and we were well into construction documentation when the act came in place. We had to be strategic. But I think now, if we can, we just need to program these milestones and these deliverables with sufficient time to resolve them. That would be my approach. And again, getting early input from the builder or from the subcontractors as early as we can in this case, making sure everyone's comfortable with what they're doing.
Can I just jump in on that one a little bit, Mariana? And it goes to John's point. The AIA's DBPA working group have had some sessions recently with the team from Fair Trading, so Matt Press and the auditor crew, about that issue. What do you expect and who's doing what? I don't think that it's all bedded down by any stretch of the imagination, but one of the key things that they were saying was shop drawings is what you declare. So the architect can't declare at CC with a minimal amount of information because we can't say it's compliant. We can't say, we tried the argument of saying, well, okay, is it something we say this is our documentation is not non-compliant, or it's capable of achieving compliance, or something along those lines. They say, no, the Act doesn't let you do that. The Act says you're signing on the bottom line with everything behind you and a jail term if you get it wrong, that it's compliant. So we're saying as architects we couldn't do that because we're not remotely capable of the expertise to be able to do that. And say, well, who does? And so we've gone through and shown them, on a particular project, here's my drawing of it. Here's, funnily enough, Peter Hartigan's drawing of it. And that's just coincidental. And here's the subcontractor's drawing of it. Those are the three things there. So we can give you that drawing, and we can declare it in saying that it's, as far as our expertise is concerned, it's compliant, but we're not saying it's absolutely compliant. And then they say, okay, well, the facade consultant's doing that. And we say, no, the facade consultant isn't doing that. The contractor's doing that. They're the one that's finally telling you the design works, and they can do all that. But for them to be able to do that, they need those two steps first. It also gets us back onto a conversation there about what constitutes construction. We've had saying that facades are like fridges. It's a piece of construction when it's installed in the building, not when it's fabricated in the factory. You're buying a product effectively, and you're not having somebody constructing something on site. So there's the semantics of how that actually applies. Is it something which you think has to be compliant when it's installed in the building? Absolutely. When it's sitting in a truck about to be installed in the building, does it have to be compliant? They say, well, its compliance is baked in at that point, so it is considered to be construction. Say, well, how far back do you go with that? So you go back to the factory before the glass is installed. Is it construction? Before they put frames together, is it construction? When you cut the die, is it construction? When you do the shop drawing to do the die, is it construction? And you have to audit all of those processes. So that conversation was interesting, and I think they're still thinking about aspects of that. It seems to me that ultimately the only way you could make that work is saying it's considered construction when it's in its final position in the building, and up until that point it's a product. How they end up managing that, I'm not entirely sure, but they seemed fairly keen that it's shop drawings is what gets declared, and you can't get the construction certificate for a facade without the declaration. Is the kind of the key part of it. So, you can't do a CC until you get shop drawings, if that's the way that it pans out. So, yeah.
Like I said, maybe 5 years at the start, but maybe more.
What I'd recommend is that in the discussions that we had with the building commissioners group, we say actually as architects we don't have a huge axe to grind one way or another here. It's not something which is a huge impost on us. The one that we're scared about is the bit where someone says, of those three drawings, now that we've got that shop drawing, you now have to go back and change every one of your drawings to reflect what's on that shop drawing. And we say, so there's a certain benefit to us if we're not declaring anything, then we'd have to change a drawing. It's great. But I don't know that's really what is actually going to be the best outcome industry-wise if architects aren't declaring anything. So it could go a number of ways. But what we did say was, you've got to go and talk to Mirvac. Go and talk to Mirvac and see what they think about this. Go and talk to Lend-Lease, talk to Maltese, talk to all those people and see how they feel about that, because we're not the people with the biggest, the big sacks to grind on this one. There'll be pain or pleasure one way or another in a small sense for us, but it's much bigger for other players. So I would like anybody in the room who's got a thought on this one strongly one way or another to try and contact them and start those conversations going. And I think ultimately it probably needs to have a broader forum with almost all of us sitting around with that group, talking it through and accepting the fact that there won't be a resolution for another number of months when everybody gets their heads together and really gets into it in the detail, because it's a hard one.
It is, yeah, because the building, what we don't really have in the room, because I represent the development business, not the building, your design, but what we don't have in the room is the building practitioner voice, because effectively they're the ones who are committing to building as per the design that's declared. So if there becomes a difference between, the facade consultant, the architect, or, the principal consultants declaring, and their subcontractors who are flooding the project with thousands of shop drawings, then they're taking that risk on, because effectively the design practitioner will go, you've departed from my declared design potentially. There's a number of different scenarios, but they're taking an enormous risk in this process because builders aren't resourced currently to deal with the amount of admin required to check all of these different drawings at all times. God forbid there's a modification, the developer changes the design at some point, which Toga loves to do to create value along the journey. Of course, and that completely throws a cat amongst the pigeons because it changes the whole thing. And then you've got to wait for council to approve the change, and then you've got to go through the whole process of redeclaration, updating your CC.
Because we can't declare something that doesn't have a current approval. If it doesn't have a planning approval, if there's a mod that hasn't been approved yet, then we can't sign a declaration on it.
Yeah, exactly.
Yeah.
That's a big challenge in the industry at the moment.
Yes. Yeah. So I'm going to move you on a bit, but it sounds like one of the questions I did have is, do we think it's working effectively in delivering better quality facades on Class 2 buildings? Probably touching back to Nick's point, you can have an FP 1.4, but the building can still leak.
One of the thoughts I have is if you look at the net cost or the total cost, which would include the cost of going back to fix mistakes. So if you average that across the industry, I'm hoping that it's a net benefit. It might cost some projects a little bit more, but averaged, hopefully it's an improvement. I assume it surely must be, because the cost of repairs is massive.
The initial work that they'd done when the Act was coming out, looking at, first of all, there was the UNSW surveys that they'd done looking at defects in the building industry and what was causing them and where they were coming from and all that sort of stuff, and looking at potential values kind of led to some things. But then the exercise on a couple of high-profile projects right when the Act was coming out, which were stopped because of major wet area defects, not necessarily to do with facade stuff, more to do with balconies and bathrooms. But the analysis they were doing there was basically saying, okay, if you imagine it costs to have done this right, to have done this balcony right, or done this bathroom right, costs £5 grand. To fix that before you hand it over to somebody costs you 10 grand. To fix it once it's been handed over to anybody costs 25 grand. So there's like a factor of 5 in there over the initial cost to actually get it right to begin with versus the rectification cost. I mean, I've heard discussions about, you can't do this stuff, it's going to kill the market because, the markets can't deal with, people won't pay that money and it'll get passed on to the house buyers and stuff. I think if you go to house buyers and say, would you spend 5,000 more on your apartment just now? Or else would you like 2 years of sitting in something that's wet, having haggles with lawyers, and then pay 25,000? Which would you prefer?
Yeah, I think there's more costs associated with getting it right because of the processing. So I think it's more than that, but I still assume that when you add all the costs in of getting it right and, uplift in PI and processing costs, I'm hopeful it's a net benefit.
Yeah, I believe it will still be a net benefit as far as that's concerned. I think we're still getting our handle on what consultancy cost uplift is and how much it actually costs us to do these projects, with the level of checking that goes on above and beyond what you would be doing normally, the administrative stuff. And there's almost a little exponential thing where you say, if you're doing a project which is a lump sum, but at the end you've got a simple planning approval, and there will be there's one CC that gets done for the whole thing, then the cost is this, and it's not going to kill anybody. So as soon as you do multiple mods or section 455s into it, and you put 10 staged construction certificates into it that you're making up as you go along, then the costs become exponentially higher, a huge amount higher, because that ability to understand and coordinate and integrate between things which are at different stages of design and development across a project is incredibly complex, really complex. I can't stress enough how difficult that can be to manage. And
That's
how
why
much
you need a project design manager.
Sorry?
That's why you need a project design manager there, making sure it's all dogs in the row.
You'll just tell him to coordinate his drawings, though, Marion.
Thanks.
We're coming towards the end, so I'm just going to go through one quick little comment from each of you. What would you like to see change for the future in the acts, or in the way the acts are applied? Or so.
Where do you want to start?
I'll go this way. I'll start it that way. I'll come back.
I think it's going to be adaptable and flexible for all the scales of Class 2 buildings. It's quite a range from the 2-lot houses to the massive constructions that we have, which is Harbourside example, and it has to suit the wide range. So over time, it's got to be reactive and proactive to assist on all those projects.
I think in a world of escalating costs, certainly not just focused on the DBP Act, but across the whole construction industry, I think there needs to be some thought on how we do manage cost as part of the DBP Act, and probably bringing in some sort of subcontractor innovation into the fold. Don't know how we do that, but I think that's
challenge. Okay.
It's certainly something that I think, and we think at Toga, is an opportunity for this part of the industry.
Great. Mariana.
I think the amount of administration is just over the top. There must be a better way to do it. I think someone was thinking about it and it seemed to make sense. But when you do it practically, you realize it's just huge amounts of admin for, I don't know if real benefit. So it needs to be streamlined somehow.
Can I be greedy and go for 3? So,
3?
Yeah. So removal of personal liability. I think that's quite unfair, actually. I'd like to see clarity around how you manage repairs. So at the moment, you have to regulate a repair. And it's like, if you take the gaskets out of a window and replace them, it might work, but you have to sign it off. If that's an old window, how do you know that it's compliant? And I think just some guidance from government on how to interpret the Act when it's not clear what you're supposed to do.
Yep. Last but not least.
I'd go for a time machine. I'd just like us to be 5 years in the future and it'll all be settled. And we can get on with
Are we saying 5 or 10
innovative
now?
stuff. I still think it's close. I think we'll get 80% of the way there in 5 years, and the last 20% will take a wee bit longer, as with everything.
Yeah.
But that's kind of where I expect it to go. But if the more groups like this can get involved in conversations amongst us and engage with it, then the faster that will happen.
Okay. Excellent. Well, it's time for beer, so we're going to...
just have a seat.
Okay.
Give a round of applause.
I know that the discussions around the DBP Act can go on forever, and there are many people in this room who had their 2 cents. But thank you for the discussions today. Yes, thanks, John. As the saying goes, all good things must come to an end, but great things end up with a networking session next door right after this.
We would just like to give thanks now first to all of you guys for coming to this amazing event today. Thanks to the speakers for your captivating presentations and discussions. Thank you to the sponsors for enabling this amazing event again. Thanks to Zak. Yes, and a hug, perfect. And thanks to the Gadigal people and traditional owners of the Eora Nation here. Thank you.
Thank you all for taking time out. I hope you enjoyed this year's edition. We aim to return back to Sydney February 2025. Also a round of applause for Claire and Natalia. I think they did a great job. Thank you, ladies. As I mentioned this morning, we have recorded this event, so the presentations we've got permission to share with you. We'll send that via YouTube link. You can then review it a week from now. And also it'll come with a feedback form. Please do share your feedback with us so that when we return next time around, we can have a better event. Next two events in Australia are in Brisbane on the 15th of February and in Melbourne, September next year. Hope to host all of you later. And now we can proceed to the networking session in the exhibit area. We'll take some photos and join you there soon. Until next time, thank you.